Hello everyone. In this lesson, we're going to be covering chain rule to find derivatives. This lesson does also include implicit differentiation, but I'm actually going to record that as its own video so we can really kind of hone in and focus on that. So our chain rule says that if we have g of x, which is differentiable at x, and fu, which is differentiable at g of x, then f, which capital F, is equal to f of g of x is equal to f of g of x is differentiable at f. That is to say that if we take the derivative f prime, this is going to be equal to f prime of g of x times the derivative of g of x. So what this means is that if we have dy dx, we can actually use what's called U-Substitution, and this will become dy du times du dx. And I'll talk later whenever we get into implicit differentiation and stuff like that, why this is true. Now, most people just generally think of the fact that if you were to cancel this du and this du, then it'd be dy dx. This works, but it's not actually true. And again, I'll explain later on why that is. But what we're going to be doing is we're going to be using something called U-Substitution, where we're going to take whatever this inside term is, and we're just going to replace this with a u. So this would pretty much be f prime of u times, of course, the derivative of g of x. Now, for longer chains, we have if ht is differentiable at t, and g of x is differentiable at ht, and fu is differentiable at g of x, then we would have f of g of h of t. If we take the derivative of that, this is going to be, so if we have f of g of h of t, and we take the derivative of this entire thing, this is the same thing as we are going to take the derivative of the outer term, f of x. So this would be our fu, right? So this would be g of h of t times. Then we take the derivative of the middle term. So this would be g prime of h of t times, and then we take the derivative of our most inside point, so h prime of t. So you could also think of this as, suppose that this g of h of t is u, and h of t is going to be v. This would be the same thing as saying f prime of u times g prime of v times h prime of, in this case, t. So what we're really doing here is we're saying that dy dx is equal to dy du times du dv times dv, in this case, sorry, this shouldn't have been dx, this should have been dt, dt. And again, like I said, you can't just cancel them, but in essence, it does work. So of course, du's, dv's, and this would leave us with dy dt. Again, I'll talk later on about why that's not actually the operation that you're doing, but in the end, it does kind of work when you're just trying to think about how do you figure out what is your actual derivative that you're taking. Our actual derivative is dy over dt. Now, before we do a bunch of examples about using the chain rule, I first want to talk about taking exponential functions. So if you remember, the derivative d dx of e to the x is just going to be equal to e to the x. And this is going to be using our chain rule. We can actually derive what f of x equals some constant b to the x is when we take the derivative when b is not equal to e. So first what we're going to do is we're going to start with b to the x. And in order to do this, we're then going to take the exponential of this, but anytime, just like with a square and a square root, the thing that cancels out an exponential is the natural log. So we're going to change this to e to the natural log of b to the x, which, if you remember your rules from natural logs, you can actually take a power and you can pull it out of your natural log. So this would end up being e to the natural log of b times x, where b is just some constant. So therefore, when we take our derivative of this, d dx of b to the x, this is going to be the same thing as taking the derivative d dx of e to the natural log of b times x. Well, when we take the derivative of e to some power, this is just going to be e to that some power, natural log of b, times. Now we're going to take the derivative of the inside, right? Because that's our chain rule in this case, is that it's the outer term, e to the u, and then times the derivative of whatever that inside term is. So when you take the derivative of natural log, d dx, natural log, I'm just going to say of some, I'll say this is u. When I take the derivative of this, this is going to end up being, let's do it u prime, so d du. This is going to end up being 1 over u, and then you're going to take the derivative of whatever was inside of that natural log, right? So that'd be your d dx in this case. So what we're going to do is we're going to take the natural log of this b, right? So remember, this is a b, not a 6. So this is going to end up being 1 over b. So then I'm taking the derivative d dx natural log of b times x. So if you remember, this is actually going to use our product rule. So it's going to be the derivative of the natural log of b, which is just going to be 1 over b. X is just going to be x. And then plus, take the derivative of x, going to be 1. This is going to be natural log of b. So what we're going to end up being left with is e to the natural log of b times x times the natural log of b. Right, I just made it a capital B, again, so we didn't confuse it with a 6. Well, guess what? E to the natural log, this is again just going to cancel, right? So I'm going to bring this x back up to the top, so this will be b to the x. So this is just going to be equal to b to the x times the natural log of b. So whenever you have some constant to some exponential, in this case x, it is just going to be that term, b to the x, times the natural log of whatever your base is. Okay, and we're going to have an example later on where we're going to do this as part of our chain rule examples. For our first example, we have the function f of x is equal to the square root of x squared plus 1. And we want to figure out what is the derivative. So before we do that, as always, first thing I'm going to do, I'm going to rewrite this. So this is going to be x squared plus 1 to the 1/2 power. This is going to be our u. So when we take the derivative, f prime of x, this is going to be f prime of u times, and then the derivative of u, whatever that inside term is. So I'll just call it u prime. Okay, so first things first, let's take the derivative of the outsides. This is going to be 1/2, leave the inside alone, x squared plus 1, and then this is just going to be power rule, right? Think about this. This is u to the 1/2. So this would be 1/2 u to the, and then you subtract 1 from it, you get negative 1/2. So this becomes 1/2 x squared plus 1 to the negative 1/2 times. Now we take the derivative of the inside. We have x squared plus 1. So that's the derivative of x squared plus the derivative of 1. Derivative of x squared is just going to be equal to 2x plus 1. Derivative of a constant is equal to 0. So we're going to get 1/2 x squared plus 1 to the negative 1/2 times 2x. So if I bring my 2x over here, I get 2x over 2. That's just going to leave me with x. And then if I look at this term here, x squared plus 1 to the negative 1/2, the negative is just going to bring it to the denominator. This would be over x squared plus 1 to the 1/2. Or if I want to put it back in terms of my original function, which was a square root, this is going to be equal to x divided by the square root of x squared plus 1. For my next example, I actually have two different functions that I want to take the derivative of and kind of just compare them. So the first one we have is y is equal to sine of x squared. And the second one is y equals sine square of x. So if we were to take the derivative of this first one, in this case, my fu in this is going to be sine of u. And my g of x is going to be this middle term, x squared, right? So it's chain rule. Take the derivative of the outside as sine of u times the derivative of the inside term, which is g of x. So my y prime is going to be f prime of g of x times g prime of x. So pretty much what this means is take the derivative of sine. What are we going to get? Well, this is going to be equal to cosine of u times. Now we take the derivative of g of x, x squared. So this is going to be times 2x. We take our u, which in this case is just going to be x squared, and we plug it back in. We get this equal to cosine of x squared times 2x. Or if I wanted to write it in terms of having 2x front, it would be 2x times cosine of x squared. Looking at our second function, what we have is y equals sine square of x. So in this case, our f of u is just going to be u squared, right? Because if you think about whenever we take the derivative of sine, so d dx of sine square of x, what you can actually think of this as is this is going to be d dx sine of x squared. So in this case, this is going to be our u. So it's going to be u squared. And our g of x is going to be sine of x. So now, whenever we take our derivative, this is going to be equal to f of g of x, so f prime of g of x times g prime of x. So first thing first, we take the derivative of, and by the way, you can think of this as, again, your u. So we take the derivative of u squared. This is going to give us 2u to the first power times, now we take the derivative of our g of x. G of x is sine of x, which means it is going to be equal to cosine of x. And then I just, by the way, this is a 1, not a prime. And then I just plug my u back in. My u was equal to sine of x. So this is going to be equal to 2 sine of x times cosine of x. So you can see here that by having the x squared inside, we actually don't take that square derivative until the inside part of the chain. Versus when it's sine square x, we actually take that as our outside of the chain, and we end up getting a very different answer. We have cosine x squared times 2x versus 2 sine x times cosine x. What about if we want to differentiate y equals x cubed minus 1 to the 100th power? Well, in this case, right, if we have y equals f of g of x, our f of x, or fu, if you will, so fu is going to be equal to u to the 100th power. And then our g of x, our inside term, is going to be equal to x cubed minus 1. So when we take this derivative, what we're going to do is I'm just going to actually jump straight into solving it the way that you all will actually probably solve it, which is take the derivative of the outside, so bring the 100 down, leave the inside alone, x cubed minus 1. So 100 minus 1 is going to be to the 99th power, and then times the derivative of the inside. X cubed minus 1 is going to give me 3x squared. So then, of course, if I bring this 3x squared up front, this is going to end up being 300x squared x cubed minus 1 to the 99th power. What about if I have f of x is equal to 1 over the cube root of x squared plus x plus 1. Now, what you could do, you could solve this using your quotient rule, right? Treating this as f, treating this as g, but that would be a lot of extra steps. So instead, what I'm going to do is I'm going to rewrite this as x squared plus x plus 1. Now, again, we have a cube root, which means that this is to the 1/3 power. And it's in the denominator, and I want to bring it to the numerator, so I'm going to take a negative power. So now, if I were to treat this as my u, right, so I have u to the negative 1/3, when I take the derivative of that, I would get, so I'm going to rewrite it this way. I'm going to write it as d du u to the negative 1/3 times d dx, right? So I'm taking the derivative with respect to x of the inside now. X squared plus x plus 1. So doing this, when I take the derivative of u to the negative 1/3, I bring the negative 1/3 down, so minus 1 over 3, u to the 1/3 minus 1 is equal to minus 1/3 minus 3/3, which would give me minus 4/3, times the derivative of x squared would be 2x, plus the derivative of x equals to 1, and then plus the derivative of constant is equal to 0. So we have negative 1/3 u negative 4 to the negative 4/3 power times 2x plus 1. So I'm going to plug my u back in. Remember, my u is x squared plus x plus 1. So this is going to be equal to negative 1/3 x squared plus x plus 1 to the negative 1/3 power, negative 4/3 power, times 2x plus 1. So now I'm going to rewrite this back in terms of an actual root because I want to get it back into the original form. So we have done the derivative now. So this is going to be equal to 1/3. So I know I have a 3 in the denominator. We have negative 4/3. So this means that the negative is going to bring this down here. So we have x squared plus x plus 1 to the 4/3 power, meaning that this is going to be to the 4th power, and then the 1/3 power means that it is going to be a 3rd root. So this is going to be 3 times the 3rd root. Let me clean that up. This is going to be 3 times the 3rd root of x squared plus x plus 1 to the 4th power. And then this is on the top, so this is going to be 2x plus 1. So we end up having minus 2x plus 1 divided by 3 times the cube root of x squared plus x plus 1 to the 4th power. For my next example, we have g of t is equal to t minus 2 divided by 2t plus 1 to the 9th power. So in this case, g of t is going to be equal to f of h of t. So remember, these function names, f of h of t, right? We're just not using g because it's already our main function. So that equals fu is going to be equal to u to the 9th power, right? So let's leave the center alone to the 9th power, right? So that's this whole thing inside is all going to be equal to u. And then ht is going to be equal to our t minus 2 divided by 2t plus 1. So taking our derivative of g of t, actually, no, sorry. Let's do the derivative of this real quick because we're going to have to, basically what's going to happen is this. When we take the derivative of g of t, this is going to be, we're going to take the derivative of, so d du of u to the 9th times d dx of t minus 2 over 2t plus 1. And we're going to have to end up using our quotient rule for that. So if you remember, our quotient rule is gf prime minus fg prime divided by g squared. So let's figure out what that derivative is real quick. So if this is our f term and this is our g term, this means that we're going to first leave our g alone. So this is going to be 2t plus 1 times the derivative of f. So t minus 2 gives me a derivative of 1 minus, leave f alone, t minus 2 times the derivative of g. So the derivative of 2t plus 1 is going to be 2. And then this whole thing is divided by g squared. So 2t plus 1 squared. Rewriting this is going to be 2t plus 1 times 1. So that's going to be 2t plus 1. And then minus, I'm going to distribute this 2. So it's going to be minus 2t. So minus a negative, so it's going to be plus 4 divided by 2t plus 1 squared. 2t minus 2t is going to give me, that's going to go to 0. 1 plus 4 is going to give me 5 over 2t plus 1 squared. So that is going to be what our derivative is for this inside part, right? So now let's take the derivative of the outside part. So when we take the entire derivative, going back to our original derivative, we take the derivative of the outside, so we pull the 9 down, so this is going to be 9, leave the middle alone, so this is going to be t minus 2, that's my u, 2t plus 1. Now I took a 9 down, we're doing a power rule, right? So u to the 9th, bring the 9 down, 9 minus 1 gives me a power of 8 times. Then we took the derivative of t minus 2 over 2t plus 1, which we just said is equal to 5 divided by 2t plus 1 squared. So next thing I'm going to do is I'm actually going to simplify this a little bit. Because if I ever have, for example, something like this, a over b to some power x, I can actually write this as a to the x divided by b to the x. And that's what I'm going to do here. So I'm going to bring this 5 over to the front. So we're going to get 9 times 5 is going to be 45. And then I'm going to bring this 8th power. So this is going to be t minus 2 to the 8th power divided by 2t plus 1 to the 8th power times 1 over 2t plus 1 squared. Now you'll notice I have 2t plus 1 to the 8th power times 2t plus 1 squared. What happens when you multiply, a to the some power times a to the some other power? You just add those powers together. So this is going to end up being 45 t minus 2 to the 8th power divided by 2t plus 1 to the 8 plus 2 power, or to the 10th power. And so this would be the derivative of our original function, t minus 2 divided by 2t plus 1 to the 9th power. For my next example, we have the function y equals 2x plus 1 to the 5th power times x cubed minus x plus 1 to the 4th power. Now, if you look at this, this is going to end up being our product rule, right? Because we have some function f of x times some function g of x. Now, if you remember, our product rule is that we have g f prime plus f g prime. But because each of these is to a power, right? 2x plus 1 to the 5th power, x cubed minus x plus 1 to the 4th power. When we take these derivatives, we're actually going to have to be using the chain rule. So we have a product rule with a chain rule. So let's do it. So when we take y prime, which means we're taking the derivative of y, we're first going to leave g alone. So this first term is going to be x cubed minus x plus 1 to the 4th power. Now we're going to take the derivative of f. So we take the derivative of this, right? We take the derivative of the outside. So we're going to bring the 5 down. We're going to leave the middle alone, 2x plus 1. And we're going to bring the power down by 1. So 5 minus 1 is 4. Times, now we have to take the derivative of the inside of this function. So 2x plus 1, take the derivative of that, derivative of 2x is equal to 2, and then the derivative of 1, because it's constant, is equal to 0. So we have 5 times 2x plus 1 to the 4th power times 2. Plus, now we're going to leave f alone, so this is going to be 2x plus 1 to the 5th power times. We need to take the derivative of g. So again, leave the middle alone. We're going to bring the 4 down. So this is going to be times 4 x cubed minus x plus 1. So 4 minus 1 takes it to the 3rd power times. Now we take the derivative of the inside. X cubed is going to give me a derivative of 3x squared. Minus x is going to give me a derivative of minus 1, and then derivative of a constant equal to 0. So we have x cubed minus x plus 1 to the 4th power times 5 times 2x plus 1 to the 4th power times 2, plus 2x plus 1 to the 5th power times 4 x cubed minus x plus 1 cubed times 3x squared minus 1. So the next thing I'm going to do is I'm going to combine and pull all of the constants out to the front. So in this case, I have 5 and 2. So this is going to be equal to 10 x cubed minus x plus 1 to the 4th power times 2x plus 1 to the 4th power. The next thing I'm going to do is I'm going to roll this 4 out, so plus 4. And I'm actually going to write these so that they're in the same order as this. So in this case, I have x cubed minus x plus 1 cubed, and then times 2x plus 1 to the 5th power times 3x squared minus 1. Now you might wonder, why did I do this? Well, it's because what I'm going to do now is I'm going to see if there's anything that I can pull out from both parts. So in this case, I have 10 and I have 4. Do they have anything in common? Yes, they have a 2 in common. So I'm going to pull a 2 out. Next thing, x cubed minus x plus 1. X cubed minus x plus 1. This one is to the 4th power, this one is cubed. So I can pull out x cubed minus x plus 1 cubed. Next thing, my 2x plus 1 terms. I have 2x plus 1 to the 4th power, 2x plus 1 to the 5th power. So I can pull out 2x plus 1 to the 4th power. Now, if I do this, when I pulled the 2 out, I'm left with 5 in my constant. Times. I pulled out x cubed minus x plus 1 to the 3rd power. So I have 1 left in this one. So this is going to be times x cubed minus x plus 1 to the 1 power, right? Because 1 and then times 3, that would add to the power of 4. And then that's it for this one. Now we're going to look at our second term. I had a 4, I pulled 2 out. This is going to leave me with 2 times x cubed minus x plus 1 to the 3rd power. Well, that's this entire thing, x cubed minus x plus 1 to the 3rd power. Next we have 2x plus 1 to the 4th power. I had 2x plus 1 to the 5th power. That leaves me with one of them inside still. So 2x plus 1. And then times, this one didn't have anything outside, so this is going to stay the same. 3x squared minus 1. Okay, so now if I could redistribute this back in, right, and I would get back to this original term here. Now I'm going to actually distribute these and see if there's any cancellation inside. So for the outside, nothing changes. 2x cubed minus x plus 1 cubed, 2x plus 1 to the 4th power. So I'm going to distribute this 5. I'm going to get 5x cubed minus 5x plus 5. And then for this one, I'm first going to FOIL it out, right? So first, outer, inner, last. And then I'll just take whatever I get there and I'll multiply it by 2. So 2x times 3x squared is going to be 6x squared. So this is going to be plus 12x, x cubed, right? X plus x times x squared. Now I'm going to do my outer terms. 2x times minus 1. So minus 2x times 2 is going to be minus 4x. Now I'm going to do my inner terms. 1 times 3x squared. So 3x squared times 2 is going to be plus 6x squared. And then last, 1 times negative 1 is going to be negative 1. So times 2 is going to be minus 2. And now we're going to see, is there anything that combines or cancels or anything like that? So again, I'm going to leave my outer terms alone. So this is going to be 2x cubed minus x plus 1 cubed, 2x plus 1 to the 4th. Okay, so now let's look at our highest power. This is going to be the cube terms. 5x cubed plus 12x cubed. This is going to give me 17x cubed. Now let's look at our x squared terms. Well, it looks like I only have the 1x squared, which is going to be plus 6x squared. So that's this term. Now we're going to look for our x terms. Minus 5x minus 4x is going to give me minus 9x. And now I'm going to look at my constants. 5 minus 2 is going to be plus 3. And this would be the simplest form that I can get this into because I was able to kind of cancel out these inside terms. And there you go. So this would be the answer to 2x plus 1 to the 5th power times x cubed minus x plus 1 to the 4th power when we take the derivative. For my next example, we have y is equal to e to the sine of x. So if we were to consider that this is my y equals f of g of x, my outside term, fu, is just going to be e to the u. And my inside term, the g to the x, is going to be the sine of x. So what this means is when I take the derivative of this, I'm going to take the derivative of my fu term, so this is going to be derivative of e to the u, times the derivative of my internal term, sine x. So then if I were to do this, this is going to end up being, right, so the derivative of e to the x or e to the u is just going to be e to the u. So this is just going to leave my term, e to the sine of x times. Now I take my derivative of the inside term. So the derivative of sine of x is going to give me cosine of x. So I'm left with e to the sine of x times cosine of x. What about if I have f of x is equal to sine of cosine of tangent of x? So in this case, I'm actually going to solve it a little bit differently, but basically doing the same thing. Is I'm going to say that this is u, and this, I'll call this v. So if I look at g of x, let's do it this way. G of h of j of x, right? Because we're just doing a higher order chain. Then my g of u is going to be sine of u. My h of, in this case I used v, is going to be cosine of v, and my j of x is going to be this internal term, tangent of x. So what this pretty much means is when I'm taking the derivative of the outside, right, so it's going to be derivative of sine of something. So the first thing I'm going to do is I'm going to take my derivative d du of sine of u times. I'm going to go in one step. I'm going to take the derivative d dv of cosine of v. And then finally, I'm going to take the derivative d dx of tangent x. So when I take the derivative of sine, I'm going to get cosine of x, so cosine of u times the derivative of cosine. So the derivative of cosine is going to be negative sine. So this is going to be negative sine of v times. What about if I have the function g of x is equal to 5 to the 2 to the x to the second power? So in this case, we're going to be doing a chain rule where we have our g of x is equal to f of h of j of x. Now remember, again, these functions can be whatever letters you want them to be. We're just not using g because that's our original function. So our f u is going to be 5 to the u. Our h of, I did z on the slides, I'll keep it consistent. Last time I did v, but I'll use z, is going to be 2 to the whatever, this would be z. So 2 to the z. And then our j of x is going to be x squared. So when we take the derivative of each of these, right? So if I took the derivative of the first one, so d du of f u, remember we talked about this whenever we did our exponential rule. This is going to be 5u natural log of 5. When I take my d dz of h of z, this one is going to end up being, same idea, it's going to be 2 to the z natural log of 2. And then we are going to have the derivative d dx of x squared, which will just be 2x. So this means that when we take our derivative, g prime of x, it is going to equal to 5u natural log of 5 times 2z natural log of 2 times 2x. And then we just plug our u and our z back in. So this will be equal to 5, and we said that our u was equal to all of this. So 2 to the x to the 2, natural log of 5, times 2 to the z, which is to the x squared natural log of 2 times 2x. So we have 5 to the 2 to the x to the square times natural log of 5 times 2 to the x to the 2 natural log of 2 times 2x. So this is how you can do this with using the chain rule and your exponential derivatives. For our last example, we're going to do one of those kind of examples where we know the outcomes of the derivatives of our functions and things like that, but we don't know what the actual functions are. So we have f of x, so capital F of x, equals f of g of x, and we want to find what is f prime of 2. In this case, we have f of 0 is equal to 3. We have f prime, so the derivative of f of 0 is equal to 9. We have f prime of 2 is equal to 2, and we have g of 2 is equal to 0, and then finally we have g prime of 2 is equal to 3. So now, looking at this, if we wanted to take this derivative, f of x, I'm actually just going to leave it as f of x for now. So let's say we took the derivative of f of x. This is going to be equal to f prime of g of x times g prime of x. So if we're looking for the derivative f prime of 2, this is going to be the derivative of f of g of 2 times the derivative of g of 2. Now, we have the derivative g of 2. So the derivative of the g function at 2 is equal to 3. So I'm going to actually plug this 3 in right here. So this is going to be times 3. And then if we look at this, f prime of g of 2. Well, g of 2 is equal to 0. So this is going to be f prime of 0 times 3. Well, f prime of 0, right here, it says is equal to 9. So this is going to be equal to 9 times 3, which is going to be equal to 27. So you'll notice that there was a little bit in here we didn't need, right? We didn't need f of 0. We also did not need f prime of 2, right? These are sort of like red herrings. You had more information, and you needed to figure out of these, right? When I took the derivative of this, I took the derivative of f, left the g alone, and then I took the derivative of g. Then, because we were trying to find f prime of 2, this became f prime of g of 2 times g prime of 2. So we needed g prime of 2 and we needed g of 2. So we needed these two. Once I plugged in this g of 2, which was equal to 0, I had f prime of 0, which means I needed f prime of 0. And then with that, I was able to take all the numbers I needed to solve for it, and I was able to get 27. So that's it for our lesson for the chain rule. What we're going to do now is the next lesson, which is still technically part of the chain rule. We're going to be looking at implicit differentiation. I wanted to specifically keep this one as a separate lesson because this is one where I feel like most intro to calculus students really seem to struggle with. So I really wanted to focus on it as its own thing so it's not part of some bigger section like chain rule. So I'll see you all in the next video, and I hope this has been helpful. Hello everyone. In today's lesson, we're going to be learning about derivatives of logarithmic and exponential functions. So to begin with, we're going to have a couple new rules that we're going to be learning. So the first one is that if we take d dx of the natural log of x, this is just going to be equal to 1 over x. Our second rule is that if we have d dx of the natural log of some u function, which u is just a function of x, this is going to be using the rule we just had with the natural log of x, except for now we're going to have to use the chain rule. So this is going to end up being 1 over x times the derivative of u, which then, of course, we would just write as u prime over x. For the third rule, we have d dx of some log function with base b of x. This is just going to be 1 over x natural log of whatever your b is for your base. And then like before, our fourth rule is going to be if we have d dx of some natural or some log base b of some u function, which again is in terms of x, this is going to be the same idea. It's going to be 1 over x natural log of b, but now we have to use our chain rule. We take the derivative of what's inside the log, and this is going to be u prime, which then of course we can rewrite as u prime divided by x natural log of b. Another useful thing to understand is the number e as a limit. So our number e, which is Euler's number, can be written as the limit as x goes to 0, 1 plus x to the 1 over x power. And then what's happening is as this goes to 0, right, we have 1 plus x. This x term, of course, is approaching 0 as our power is going to 1 over 0, which means that it's approaching infinity. So this is going to get, this term is going to approach 1 as this approaches infinity. And this is equal to, if you wanted to do it in terms of as n goes to infinity, you could rewrite this as the limit as n goes to infinity, 1 plus 1 over n to the nth power, which if you kind of look has the same properties, right? As x goes to 0, this makes this 1 plus 0. As n goes to infinity, this is equal to 1 plus 1 over infinity, which is going to be infinitesimally small, basically 0. And of course, as x goes to 0, this power goes towards infinity. As n goes towards infinity, this power also goes towards infinity. So let's do some examples based on these new rules that we've just learned. So the first is we want to differentiate y equals the natural log of x cubed plus 1. So looking at our rules, whenever we take the derivative of the natural log of some function with in terms of x, this is going to end up being 1 over whatever's within the natural log. So this is going to be x cubed plus 1. And then we're going to take the derivative of whatever's inside. So of course, x cubed, we're going to use our power rule, is going to be equal to 3x, and then plus the derivative of 1, derivative of a constant, is equal to 0. And we're left with 3x squared over x cubed plus 1, right? Because when we did our power rule, we brought down the 3, and then we subtract 1 from the power. For our second example, we want to take d dx of the natural log of sine of x. So as before, when we have the derivative with respect to x for natural log, we're going to take whatever's within the natural log, and we're going to have 1 over that. So 1 over sine of x. And then we're going to multiply it by the derivative of what's inside, again, using chain rule. So the derivative of sine of x is going to be cosine of x. So this will be cosine of x over sine of x, which if you remember, we have that one identity we talked about before. We had tangent of x is equal to sine of x over cosine of x. Well, similarly, cotangent of x is equal to cosine of x over sine of x. So we can actually rewrite this as cotangent of x. In fact, these are the kind of identities that will actually help you show or solve for a lot of the other derivatives we looked at previously, the trigonometric ones, because a lot of times what you can do is you can use these identities to change things like secant, cotangent, tangent into sines and cosines. You can do rearranging things, eliminating different terms, and then getting it in terms of the derivatives that we learned previously. What about if we have the function f of x equals the square root of the natural log of x? So in this case, we're going to be using our chain rule. So first thing I want to do is I want to change this to the natural log of x to the 1/2 power, right? So this whole thing is to the 1/2 power. Now what we could do is we could do our chain rule, which is to say we pull the 1/2 down. So we take the derivative of x, f of x, so f is equal to, we bring down the 1/2, so we do 1/2 natural log of x, and then subtract 1 from 1/2, we get minus 1/2 power. And then we take the derivative of the inside term, which is natural log of x. So we said the natural log of x is equal to 1 over x. So this is going to give us times 1 over x. Now rewriting this, what we're going to get is we have 1 over 2. So I'm going to create my fraction here. We have a 2 at the bottom. Natural log of x to the negative 1/2 is the same thing as saying 1 over natural log of x to the 1/2, which is the square root. So this is going to be the square root of the natural log of x. And then, of course, we have this times 1 over x. So I'm just going to slide that in front of our square root. And this is, we have nothing else on top. I'm just going to put the 1 there. So we have that this is equal to 1 over 2x times the natural log of, or times the square root of the natural log of x. For our next example, we have the function f of x is equal to log base 10 2 plus sine of x. So looking at our rule that we have over here, this is going to be equal to, so the derivative d dx of natural log of base b u is going to be u prime over u natural log of our base b. So in this case, if we were to solve this, our u is the 2 plus sine of x. So this is going to be 2 plus sine of x. This is going to be our u. And then this is going to be times the natural log of our base, which is going to be, in this case, natural log of 10. And then now in the top, we have u prime, which is to say the derivative of the inside term, right? So you can think of this as 1 over whatever is inside times the natural log of whatever the base is times the derivative of the inside, which means we can just put it on top of the fraction. So we're going to take the derivative of 2, that's going to be a constant, derivative of constant is equal to 0. Then we take the derivative of sine of x, we get cosine of x. So our answer for this one would be cosine of x over 2 plus sine of x times natural log of 10. For our next example, we want to find the derivative d dx of the natural log of x plus 1 divided by the square root of x minus 2. And I'm actually going to show you doing this multiple ways because I want to actually show that you can approach these problems different ways and still come out with the exact same answers. So the first way is, before we even touch the derivative, we can actually use some rules of our natural logs, which is to say that if I have the natural log of some function f of x times g of x, this would be the natural log of f of x plus the natural log of g of x. If I have some natural log of f of x over g of x, right? So this would be our f, this would be our g. This is going to be the same thing as saying the natural log of f minus the natural log of g. So we actually could treat this as d dx natural log of x plus 1 minus natural log of the square root of x minus 2. So this is one approach we could take. So now instead of having to do the quotient rule, we could actually use this natural log rule, which allows us to make it a lot simpler. But just to show they come out to the same thing, I'm actually going to also do the quotient rule. So we have, this is our f term for the quotient rule, and this is our g term. And if you remember, this is going to be g f prime minus f g prime divided by g squared. So then if we were to use our quotient rule, we leave our g alone. So this is going to be, I'm going to set it as power. So this would be x to the minus 2 to the 1/2. X minus 2 to the 1/2 power times. Now we take the derivative of our f term. So x plus 1, we take the derivative of that. Derivative of x is 1, and derivative of 1 is 0. So this is just going to be times 1 minus. Now we're going to leave our f term alone. So this is going to be x plus 1 times the derivative of the square root of x minus 2. So x minus 2 to the 1/2 power. So we're going to bring down the 1/2, x minus 2, and then the 1/2 power minus 1 is going to give us to the negative 1/2 power. And now we have to multiply by the inside, derivative of the inside. So the derivative of x is just going to be 1, derivative of 2, because the constant is going to be 1, so this is just going to be times 1. And then this entire thing would be divided by g of x squared. So this will be x minus 2 to the 1/2 squared. Okay, so now let's actually rearrange everything a little bit. So first things first, we have x minus 2 to the 1/2 times 1. So nothing changes there. So we have x minus 2 to the 1/2. Right, so the times 1 doesn't do anything. Then minus x plus 1 times 1 over 2 x to the negative 1/2 times 1. Okay, so what I'm going to do first is I'm going to pull that negative 1/2 forward. So this would be negative 1/2. And then I have x plus 1, x minus 2 to the negative 1/2 power. And then I'm going to just focus on the bottom here for a second. We have x minus 2 to the 1/2 to the to the second power. Well, whenever you're taking something like a to the power to another power, you're going to multiply those powers. So then 1/2 times 2 is just going to be to the 1 power. So this is going to be x minus 2. Okay, now if I were to actually look at this term here, this x plus 1 times x minus 2 to the negative 1/2, this is really kind of the same thing as saying, so we have x minus 2 to the 1/2 minus 1 times x plus 1, so x plus 1 divided by 2x minus 2 to the 1/2 power. So what we need to do in order to solve for this is we're going to have to get this first term over 2x minus 2 to the 1/2 power. So what we're going to do is we're going to multiply this one by 2x minus 2 to the 1/2 power over 2x minus 2 to the 1/2 power. And then, of course, this entire thing is still divided by x minus 2. Okay, so now when we do this, look what happens here. So this entire thing will be over 2x minus 2 to the 1/2 power. And at the top, we have 2x minus 2 to the 1/2 times x minus 2 to the 1/2. You add the 1/2s together, you get 2x minus 2 to the 1 power, so just 2x minus 2, plus x plus 1. And then this entire thing is divided by x minus 2. We can think of this x minus 2 as x minus 2 over 1. Doing fractional division means we're going to do multiply by the reciprocal. So this term is going to come into here. This 1 is just going to go up to the top, which isn't going to change anything. And then I'm also, while I'm doing this, I'm going to distribute this 2. So this is going to be equal to 2x minus 4 plus x plus 1 divided by 2x minus 2 to the 1/2 power times x to minus 2. So you can think of this as x minus 2 to the 1 power, which you add those together, you get to the 3/2 power. So this bottom part is going to be 2x minus 2 to the 3/2. Okay. And then simplifying this, we have 2x plus x. This is just going to be 3x. And then minus 4 plus 1 is going to be minus 3 over 2x minus 2 to the 3/2 power, which will then end up being, okay, so this isn't quite what we were expecting. But if you remember, this is just the derivative for this inside term. And when we have the natural log on the outside, remember, what we have to do is we have to take, when we're taking the derivative, which in this case is going to be d dx, this entire thing, it's going to be 1 over x, in this case, actually u. So 1 over u, I didn't mean to put that x, I don't know why I keep putting x's there. 1 over u over the derivative of u. So this is our derivative of u. So when we take the derivative of the natural log of x, then so this dd u of that natural log of whatever we had inside, which was all of this, right? That's the derivative of the inside, is going to be u prime, which is going to be x minus 5 divided by 2x minus 2 to the 3/2, and then divided by u, which in this case is going to be x plus 1, x minus 2 to the 1/2. So again, we're going to do fractional division. So this term is going to come to here. This term is going to come to here. We're going to get x minus 5 times x minus 2 to the 1/2 divided by 2x minus 2 to the 3/2 times x minus 1. Okay, so now if we look at this, we have x minus 2 to the 3/2 divided over underneath x minus 2 to the 1/2. So we could actually subtract these, right? So we would get x to the 1/2 minus 3/2, which would leave us with, right? So if we had x minus 2 to the 1/2 minus 3/2, this would leave us with 2 over 2. So this term is just going to go to x minus 5 divided by 2x minus 2 x minus 1. And then, of course, if we wanted to make this look like what the answer will look like when I do the other approach, this is just going to be equal to x minus 5. We distribute the 2 into here. This becomes 2x minus 4 x minus 1. So that was a lot just to get this derivative. But now let's go do it this way that we had before. We had the derivative of, we took the natural log of the top term over the bottom term becomes the natural log of the top term minus the natural log of the bottom term. So let me clean this up and let's do that one. And I'll show you that it ends up being the exact same thing. X minus 5 over 2x minus 4 times x plus 1. Okay, with a clean slate, we're back to our starting point. Now we're going to take the derivative of natural log of x plus 1 minus natural log of square root of x minus 2. So we're going to distribute our derivative, and this is going to become d dx of the natural log of x plus 1 minus d dx natural log of x minus 2 to the 1/2 power. So when we take our derivative of natural log of x plus 1, this is just going to end up being 1 over whatever is inside, so x plus 1, and then times the derivative of x plus 1, that's going to be just equal to 1, minus. Okay, so now again, we have a split point where we can do two different things. The first thing we could do is we could do the chain rule for this, right? So we take the natural log of, so this is going to be 1 over whatever is inside, so this will be x minus 2 to the 1/2 times the derivative of the inside. Well, the inside is just going to be a chain rule, so this is going to be 1 over 2 x minus 2 to the negative 1/2, and then we multiply by the derivative of the inside, which is just going to be equal to 1. So now we have our derivative of our first term and the derivative of our second term. So in order to bring them together, what we need to do is we need to get them both in terms of the same denominator. But first thing I'm going to do is we have this right here. We have x minus 2 to the 1/2 power, which is the same thing as saying 1 over x minus 2 to the 1/2 power. So I'm actually going to put this in the bottom as x minus 2 to the 1/2. So whenever I multiply these two out, right, x minus 2 to the 1/2 times x minus 2 to the 1/2, or x minus 2 to the 1/2 squared, this is just going to become x minus 2. So we have that this is equal to 1 over x plus 1 minus 1/2. So it's going to be 1 over 2x minus 2. And this is the place where I was telling you that now I want to get them in terms of the same base. So I'm going to multiply this one by x plus 1 over x plus 1. And I'm going to multiply this one by 2x minus 2 over 2x minus 2. And by doing that, we're going to end up getting 2x minus 2 minus x minus 1 divided by 2x minus 2, x plus 1. When we simplify this, 2x minus x is just going to leave us with x minus, oh, sorry, I forgot to distribute my 2. So this would be minus 4. Minus 4 minus 1 is going to be minus 5, right? Because basically what I did is I took the 2 when I was doing this and I was distributing it, so it became 2x. 2 times minus 2 is going to be negative 4. And then last thing, just put it in the same form we had before. I will distribute this as we move it over. So this is going to be 2x minus 4 times x plus 1. So you'll see that we have the exact same thing we got last time. But we actually could have done this even easier. So let's go back to this step. For the derivative of the first one, we're not changing anything. So this is still just going to be 1 over x plus 1 minus. But whenever you have the natural log of something to a power, right? So let's say you have the natural log of a cubed, whatever a is. What you could actually do, actually let's just make it x, just make it simple. You can actually pull this cube out and this becomes 3 natural log of x. Sorry, x I mean. So what we're going to do in this case is this is going to be the derivative of, so let's rewrite this, d dx of, where am I at? So I'm going to pull this 1/2 out. So this would be 1/2 derivative of natural log of x minus 2. So now when we do this derivative, this is going to be a lot simpler to do, right? Because minus 1/2. When I take the derivative of natural log of x minus 2, it's going to be 1/x minus 2. And then the derivative of the inside is going to be derivative of x, which is 1. Derivative of a constant is 0, so it's just going to leave us with 1, right? Because 1 times 1 plus 0. And that leaves us with 1/x plus 1 minus 1/2x minus 2. And if you look at right here, this is exactly what we had before we did our multiplication. 1/x plus 1 minus 1/2x minus 2. So you actually see that there's multiple steps we could have diverged and done different approaches, and we end up getting the exact same thing when doing a problem like this. Now we're going to add one more rule to the mix. If we have d dx, so we're taking the derivative of our inverse tangent function of x, this is going to be equal to 1/1 plus x squared. So we're going to do one example just to kind of show how we would take this derivative. So let's say, for example, that we had y equals 1/the inverse tangent of x. So what we could do is you could do your quotient rule, right? Treating this as f, which of course you can take the derivative, it's just going to be equal to 0. So it'd be not too difficult, and treat this as g. Or we can take the fact that if we have a negative power, it's the same thing as putting something into the denominator, especially if we have this, in this case, to the first power. So I can actually write this as the inverse tangent of x to the -1 power. So now when I take my derivative, I'm just going to be using the chain rule. So I'm going to bring down my -1, and then I'm going to leave the inside alone. So tangent inverse, or inverse tangent of x. Subtract 1 from this, to the -2 power, times. Now we need to take the derivative of the inside. Well, we just said that the inverse tangent of x has a derivative of 1/1 plus x squared. So this will be 1/1 plus x squared. So now rewriting this, we have -1 in the top. This negative power is going to bring this tangent to the bottom, the inverse tangent. And then we have times 1/x plus 1 squared. So here, just keep it simple so we can kind of keep it situated. I'm just going to put this as 1/1 plus x squared. And then, of course, we could just combine this. I just kept it separated, but realistically, it's the same thing as -1/the inverse tangent of x squared times 1 plus x squared. And that's really all there is to it. I just wanted to show you kind of a brief example of using this derivative in just anywhere that you had an inverse tangent of x. Whenever you take the derivative, whether you're doing it within a chain rule, product rule, whatever, it's just going to end up being 1/1 plus x squared. And then just like any other time, you now have this denominator term. If you're trying to add or subtract to it, like you're doing the product or quotient rule, you'd have to get it in terms of like base. If you are doing something like this, where it's multiplication, you just honestly write it out. So unless there's some cancellation, which there's nothing up top to cancel with, this is our final answer. And that's all there is to it. Hello everyone. In this lesson, we're going to be looking at implicit differentiation. So up until now, what we've been doing is called explicit differentiation. So what this means is that we have been finding a derivative of some y function in terms of just one other variable. And this usually is x for our cases. But now what we're going to be doing is, instead of looking at the derivative of some y equals some function of x, we're actually going to be looking at the relationship between two variables and how they both actually affect the rate of change of some function. For example, let's say that we have x squared plus y squared equals 1. And this is just going to be a circle, right? So it's a circle that is centered at 0, 0, and it has a radius of 1, meaning that it crosses at 1, 0, 0, 1, 1, 0, and 0, -1. The problem, though, is that if we wanted to try to use the derivative rules we've looked at so far, well, first of all, this would actually fail being a function, right? Because if I were to do the vertical line test and draw a vertical line through this, it passes through at 2 points, here and here. So we could actually still do this explicitly, but what we would have to do is we would have to then break this into two smaller functions, which would be, in this case, the upper half of the circle, and then also the lower half of the circle. In which case, if we were to do this, we're going to solve for y in terms of x. So first thing we're going to do, we're going to subtract x from both sides, or x squared from both sides. So we have y squared equals 1 minus x squared, and then we take the square root of both sides, which is going to give us the square root of 1 minus x squared. But we have to consider that this would be true for both the positive and the negative, so this is going to be plus or minus the square root of 1 minus x squared. So of course that gives us this function here, f of x equals the square root of x squared minus 1. I'm sorry. This gives us the function f of x equals the square root of 1 minus x squared, and this would be the function f of x equals minus the square root of 1 minus x squared. So let's look at what this would be if we were to solve each of these explicitly. So the first one, we're going to find f prime of x, which is going to be square root of 1 minus x squared. So I'm going to rewrite this as, so first of all, rewrite this as 1 minus x squared to the 1/2 power. So if I were to take the derivative of this, then what I'm going to do is I'm going to leave this middle term alone, the 1 minus x squared. I'm going to have to the 1/2 power. So I'm going to pull that 1/2 down. So I have 1 minus x squared, and then I subtract 1 from the power. So 1/2 minus 1 is going to give me -1/2. And now, using our chain rule, I have to take the derivative of the inside. So the derivative of 1, which is a constant, is equal to 0. The derivative of minus x squared, I bring the 2 down. This is going to give me minus 2x. So then what I'm going to do is I'm going to put this negative 2x on top. And this, of course, over 2, because I've got the 1 over 2. The negative power makes this into the denominator. So this is going to be 1 minus x squared to the 1/2 power. And then the 2's are going to cancel. I'm going to put this back in terms of square root, just so that it's back to our original form. And I will have that this is equal to minus x divided by the square root of 1 minus x squared. For my other function, it's the same thing, except for now, instead of having 1 minus x squared to the 1/2 power, it's minus 1 minus x squared to the 1/2 power. So let me write this down real quick. This is equal to minus 1 minus x squared to the 1/2 power. So when I bring my 1/2 down, it's actually going to be minus 1/2. Leave my middle alone, 1 minus x squared. Bring the power down by 1, so it's going to be minus 1/2. And now I'm going to multiply by, or not multiply by the derivative of the inside. Again, constant, derivative 0. Derivative of minus x squared is going to be minus 2x. So in this case, what I have is I have minus 2x over minus 2, and then of course I have 1 minus x squared to the negative 1/2. That's going to bring it down to the bottom, so I'll just write it out again. 1 minus x squared in the denominator to the positive 1/2 power. The negative 2 will cancel with the negative 2, and I will be left with x divided by the square root of 1 minus x squared. So you can see now that we actually have two different derivatives depending on where we are on the graph. So if I'm in my upper half, what this means is that when I take the derivative, if I have a positive x value, then I'm going to end up with a negative slope. If I plug in a negative x value, what's going to happen to this? It's going to become positive, right? Minus minus, which means that I will have a positive slope. If I'm on the bottom half of my circle, when I plug in a positive x value, I'm going to get a positive slope. If I'm on the negative, one of my negative quadrants, then when I plug in negative, let's say like x equals negative 0.5, then this would make this entire thing negative. So you can see that in this case, we can actually solve for this explicitly by first breaking it into these sub-functions that are themselves actually functions. So we can solve the derivative explicitly. The problem is, though, is a circle is very easy to do that with, right? We just took the top half and the bottom half. But sometimes we're going to have much more complicated things that we want to take the derivative for, and we're going to need a way where we can find the derivative even though it is in terms of both x and y at the same time. So what do we mean when I talk about explicit versus implicit functions? So an explicit is one variable is expressed explicitly in terms of another variable. For example, we might have y equals the square root of x cubed plus 1, y equals x times sine of x, or y equals some function f of x. And notice that every one of these is y is equal to something in terms of just the variable x. Implicit means that we have variables are defined implicitly by a relationship between the two variables, or in this example, between x and y. So we might have something like we just did, x squared plus y squared equals something like 25, which would be a circle with a radius 5, or x cubed plus y cubed equals 6xy. In this case, we have x's and y's that can't easily be defined just in terms of one other variable. So what are the steps to solve implicit differentiation? Well, the first thing is you need to identify the implicitly defined function and the independent variable. This is usually going to be x, right? So oftentimes we'll have things in terms of x, though it doesn't have to be. It could be in terms of more than one variable. Like if you have y, it could be in terms of x and z, or if you have z, it could be x and y, something like that. Next, you want to differentiate both sides of your equation, but with respect to x. So you're going to be taking d dx of both sides. Number 3, you're then going to use the chain rule to differentiate any terms that contain y as a function of x within them. You're going to then collect all of the dy dx's to one side of your equation and everything that does not have a dy dx term to the other side of your equation. And then you're going to solve for dy dx, and this will give you the derivative of y with respect to x as an implicit function which has both x's and y's. So it's looking at as x and y change, how does the rate of change change? Let's begin by actually doing the same example we just did explicitly, but now we're going to do it implicitly. So I'm going to rewrite this a little bit differently just for my first time showing how to do this. So we're going to treat this y as the same thing as saying y as some function of x. So you could kind of think of this as this is x squared plus, and then this is some y of x, which is then squared. And you don't have to do this step. I'm just doing this so that you all can kind of see how this y isn't just y. It is y that is defined by the x that we select. So next thing we're going to do is we're going to take the derivative of both sides of our equation with respect to x. So we're going to take dy dx of the left side. So dy dx of x squared plus y of x squared plus d dx of 1. Okay, so now whenever we have a derivative of some function plus or minus some other function, we can just split that into the derivative of the first function plus or minus the derivative of the second function. So this is going to become d dx of x squared plus d dx of y of x squared, and then equals the derivative of constant is just equal to 0. So I'm just going to put 0 here. Okay, so now when we take the derivative of x squared with respect to x, this is just the normal derivative we've been doing. So this is just going to be, based on our power rule, this is going to be 2x to the first power, which is just 2x. Now when we do our yx squared, what we need to do is we first are going to treat this as, just like with the chain rule, sort of think of this as a u, right? We're not going to change it. We're just going to do the derivative of the outside. So this is going to be plus 2, leave the inside alone, so y, I'll call it yx, times, now, just like the chain rule, we have to take the derivative of what's inside that chain, in this case, u. Well, u is y of x. Well, the thing is, that's kind of the whole point of what we've been trying to do, right? We've been trying to figure out what dy dx is. We're taking the derivative of y with respect to x. So we're actually just going to write this as d dx y of x. So now if we look at what we actually have, I'm going to shorthand this down to how we actually usually write it, which is going to be 2x plus 2y y prime equals to 0. So now that we have it in terms of our y prime terms, that's this one, and our not y prime terms, which I'm going to use the set theory notation. I'm going to put a C for complement, which means not y prime. And I'm going to separate them so that I have the y prime terms on one side and the not y prime terms on the other side. So I'm going to subtract 2x from both sides, and I'm going to have 2y y prime equals minus 2x. Now, the last thing I need to do is I need to get this y prime by itself, though, right? I've got all the y prime terms over here, but I don't actually have y prime yet, and that's what I'm actually trying to solve for. I'm trying to solve for what is the derivative of y, which, by the way, is just dy dx. That's why I kind of changed it here. This is dy, right? So d dx of y is the same thing as saying dy dx, which we oftentimes will just write as y prime. So what I'm going to do now is I'm going to divide both sides by 2y. So this 2y is going to cancel with this 2y, and this 2 is going to cancel with this 2, and it's going to give me y prime is equal to minus x over y. So now looking at our circle, this means that my derivative is going to change by the relationship of minus xy, which you'll actually see agrees with what we had previously, because if we actually substituted back in our derivative, or our value of y, we could substitute in y that was equal to the square root of 1 minus x squared, or we could substitute in y equals negative square root of 1 minus x squared. And if we plug this in for the y we have here, you'll see that we either have this is equal to minus x over, so this one, square root of 1 minus x squared, or it could be also equal to, instead, minus over, so negative and negative gives us positive, it could be equal to x over the square root of 1 minus x squared. So see, this actually agrees with what we did. We can do this for either side now, and it's all inside of one equation versus having a separate breakout of every possible equation based on where we need to separate out our original function. So now what we're going to do is we're going to do the same idea, but we're going to change it just a little bit, and we're going to do a problem based on that. So in this example, we're going to do the same idea, except for now our circle is going to be equal to a radius of 5, right? So this means that this goes out to 5 in the right direction, it goes to negative 5 to the left, it goes up to 5 when we go above, and it goes to negative 5 when we go below, right? And these are our y values, these are x values, right? It's 5, 0, 0, 5, negative 5, 0, and 0, negative 5. So what we're going to do is first we're going to solve it implicitly like we did before, very quickly. So this is going to be d dx of x squared plus y squared equals d dx of 5. And then I'm going to split this. So this is going to be d dx of x squared plus d dx of y squared equals derivative of constant equals 0. Derivative of x squared is going to be 2x plus derivative of y squared. Remember, you got to do chain rule. So leave the middle alone. That's your y. So you're going to bring down the 2. So you're going to get 2y to the 1 power. That's your outside of your chain. Now you're going to do the inside of your chain. What is the derivative of y? Well, again, we don't know the actual value, but what we're going to do is we're going to treat it as the derivative of y. So we have that this is equal to 0. We're going to subtract 2x. We're going to divide by 2y, and this is going to give us y prime equals negative x over y. So we have our derivative now. So now what we're going to do is we're going to find what is our tangent line when we have the point 3, 4. So when we come out 1, 2, 3, and we go up 1, 2, 3, 4. So we're going to have the tangent line to right here, which we know should be negative. So if we plug in our 3, 4, let's see what our derivative is equal to. So this is going to be equal to minus 3 over 4, or we have a slope of negative 3/4. And what we want to do now is we want to find the tangent line. So as always, we're going to plug this into our point slope formula. So we have y minus y1 equals mx x minus x1, which just a reminder, when you plug in, right, this y prime is giving your instantaneous rate of change at this point, because that's what we plugged in. So that means that this is going to be, in this case, equal to our slope at the point 3, 4, which again, this slope though is based on x and y. If I were to change x, y also changes by some amount that affects the slope of this line. So now we plug our values in. We have y minus, at this point we have a y value of 4, equals a slope of negative 3/4, x minus, and we have an x value of 3. So solving for this, we have y minus 4 equals negative 3/4 x, and then minus a negative is going to make this plus. So if we did 3 times 3/4, you can think of the 3 as 3 over 1. So we get 3 times 3 is 9 over 4. So this is going to be 9/4. And then we're going to solve for our y. We have y equals negative 3/4 x. So we're adding 4. So this is going to be, because it's fourths, the same thing as adding 16/4. So 16/4 plus 9/4 is going to give me 25/4. Now we have the equation for our tangent line at the point 3, 4 on this circle that has a radius of 5. For our next example, we're going to look at what's called a folium, which we have here. The curve is described by x cubed plus y cubed minus 9xy equals 0. And if you look here, I actually have drawn out what the folium looks like, and I also will show you what it looks like in the slide. But if you look at this, there's no way that we can actually solve this in terms of just some function x, right? Because if I were to do my vertical line test, it would fail here, it would fail here, it would fail pretty much anywhere to the right of, or x equals 0, up to the point of the edge of this like little bowed out area. But the thing is, if you also look at it, it also crosses at 3 different points for all of these, right? Because this goes on forever. So I didn't really draw it that way, but this means that if we actually wanted to solve this explicitly, we would have to have something like this, where we have this part is one function, and then we have another function starting here that goes something like this. And then we have a third function which starts here and would go something like this. And this is not the only way that you could actually split this up. In fact, let me show you really quick on another slide what an example of this might be that uses a different breakdown if you wanted to solve it explicitly. So you can see on this slide, the numbers are a little bit different on this example. I have x cubed plus y cubed equals 6xy, which means that if we had it in the form that we had, it would be minus 6xy. But either way, you can see that the way that it was split in this example is that they had the part coming down, and then they have part of the bowing up, and then the line after the little rounded part as one explicit function. And then they have this little upward part right here as a second part of a function, and then they have just this part of the line as a third part of the function. So you can see that this is 2 different ways that we could split this into 3 different functions to try to solve it explicitly. But honestly, if you tried to do that, that's going to be pretty complicated. So it's easier just to solve this implicitly. So what we're going to do for this problem is we're actually going to show that the point 2, 4 lies on this folium, and then what we're going to do is we are going to find the tangent line to that particular point, right? So we're going to have some point over here, 1, 2, and then 1, 2, 3, 4, and it's going to be something here, which means I would expect that I have a positive slope to my instantaneous rate of change, or, you know, my tangent line right there. Okay, so now what do we actually need to do? Well, just like before, we are going to take the derivative d dx of whatever we have. So this is going to be x cubed plus y cubed minus 9xy equals, d dx of 0. Just like before, I'm going to split my derivative. So this is going to be d dx x cubed plus d dx y cubed minus the d dx of 9xy. But of course, I'm going to use another derivative rule, which is if I have a constant times some function, I'm taking the derivative of that, I can pull that constant out, and it's the same as the constant times the derivative of the variables inside. So this is going to be minus 9 d dx of xy equals derivative of 0. 0 is a constant, so this is just going to be equal to 0. So now let's actually evaluate our limits. So the first one we have is d dx of x cubed. So we're taking the derivative of x cubed with respect to x. So we just do our derivative like we normally do. This becomes 3x squared by our power rule. Now we're going to take the derivative with respect to x of y cubed. Now remember, we don't have x explicitly in this, but y is a function with respect to x. So what we're going to do is we're first going to use the chain rules, right? Think of your y as a u. So we're keeping it constant. So this is going to be plus 3u, which in this case is y. Use the power rule. This comes to so minus 1 gives us second power. But now we have to take the derivative of the inside of our chain, which is the derivative of y. So this is going to be 3y squared y prime. Next, we have the derivative of x times y. So this is going to actually be using our product rule, where our x is going to be our f term, our y is going to be our g term, and we're going to use gf prime plus fg prime. So doing that, this becomes, if we leave our g alone, which in this case is y, we're going to multiply that by the derivative of f. So derivative of x is just going to be equal to 1. So this is just times 1. Plus, now we're going to leave our f alone, which in this case is x, and we're going to take the derivative of our g term, which is y. But just like we talked about earlier, when I take the derivative of y, it's y of x, which means that it'll be dy dx or y prime. I'm now going to distribute this minus 9 into this, and I'm going to have that this is equal to 3x squared plus 3y squared y prime minus 9y minus 9x y prime equals 0. So my next step is now I need to get all of my y prime terms to one side and all of my not y prime terms to the other side. So if we look at the terms we have here, this one does not have y prime, 3x squared, and minus 9y also does not have y prime. So I'm going to subtract 3x squared from both sides, and I'm going to add 9y to both sides. This is going to give me 3y squared y prime minus 9xy prime equals, I'm just going to put the positive term up front, 9y minus 3x squared. But I still haven't gotten my y prime by itself, right? I want to know what y prime is equal to. So what I'm going to do now is I'm going to, the fact that this term has y prime in it and this term also has y prime in it, I'm going to pull that y prime out, and I'm going to get y prime 3y squared minus 9x equals 9y minus 3x squared. And then I'm going to divide both sides by 3y squared minus 9x. This is going to cancel with this, and I'll be left with y prime equals, okay, I'm going to do one actual other step just to simplify things a little bit. If we look at this top, right, this right side, this top terms both have 3 in them. These bottom terms both have factors of 3 in them. So I'm going to pull a 3 out of all of these. So this top one would actually become 3, so 3 times y, minus, pull the 3 out of this becomes x squared, divided by, pull a 3 out from each of these terms, so pull the 3 out from 3y squared, we're left with y squared, minus, pull 3 out from minus 9x will leave us minus 3x. These 3 are going to cancel, and then this means that my y prime is going to be equal to 3y minus x squared divided by y squared minus 3x. Now we have our y prime in terms of both x's and y's. So what we're going to do now is we're going to go back to the original part of the question where we wanted to find if 2, 4 is on this folium and what is the tangent line there. So first things first, we're going to plug this in to our slope to see what our slope would be if we have 2, 4. So in this case, we have x equals 2 and y equals 4. So we're going to plug those in. So this is going to be 3 times 4 minus 2 squared divided by 4 squared minus 3 times 2. So 3 times 4 is 12. 2 squared is 4, so 12 minus 4 is going to be 8. 4 squared is 16, minus 3 times 2, which is 6, gives me 10. So 8 over 10, and then if I were to simplify this, this becomes a slope of 4/5, meaning that on my folium, if I were at the point 2, 4, I have a slope of my tangent line of 4/3. So m equals 4/5, so 4 over 5. Now, last thing we want to do, as always, we want to figure out what the actual equation of our tangent line is. So what I'm going to do is I'm going to use my point slope formula. Trusty point slope formula, can't go wrong with it. We have our y value, which is 4. So this is going to be y minus 4 equals our slope of 4/5 at 2, 4. X minus, and then our x value, which is equal to 2. Solving for this, we get y minus 4 equals 4/5 x, and then minus 2 times 4 is going to give us negative 8/5. We're going to add 4 to both sides. If we think of 4 in terms of fifths, because we're adding them, this becomes 20/5. So 20/5 minus 8/5 is going to leave us with 12/5. So this should be equal to y equals 4/5x plus 12/5. And now we have the formula or equation for our tangent line, as we have a slope of 4/5 as it crosses at that point, touches at that point, 2, 4. I'm going to do things a little bit differently than I normally do. So a lot of times when I'm doing these problems, I'm actually doing them on the fly. And if I make a mistake because I'm going too fast or I'm not paying attention, I go back, I erase it, I edit it. But this one, I'm actually going to show you what the slides would show. So I didn't have these up while I was doing it. So I 100% don't know if my answer is correct until I double check at the end if I make some silly mistake. But if we look here, our solution was that we first had our x cubed plus y cubed minus 9xy equals 0. We took the derivative with respect of x on all of these terms. We then solve this. We get 3x squared plus 3y dy dx plus, minus 9 times x dy dx plus dx over dx, which is just equal to 1, times y. And then we are going to solve for this. Again, we'll get the y prime terms by themselves. We'll get the not y prime terms by themselves. We will solve for y prime, which in this case is dy dx, and we get the same thing we got. Then we plugged in our point 2, 4, and if you look here, we get that it was 8/10, which we simplified to 4/5. And then last, we plugged in our slope of 4/5, our x value of 2, and our y value of 4 into our point slope formula, and we were able to get the exact same thing. And then if you look here on this slide, you can actually see what this tangent line looks like. We've got our tangent line with a 4/5 slope touching at 2, 4, and then of course, if we wanted to, we also could ask for the normal line, which is included on this image if you were interested in that. Which we would solve by first taking our slope and taking the negative reciprocal of it. So if we have a slope of 4/5, if we wanted the normal line, our slope would then become minus 5/4. And then we would do the same thing. We would plug it into our point slope formula, but with our normal slope, which would be negative 5/4. So it'd be y minus 4 equals negative 5/4 x minus 2. Solve for that, and you would get y equals minus 5/4 x plus 13 over 2. So this is something you could definitely do, but you'll notice that by solving this implicitly, instead of having 3 different derivatives and always having to worry about where we are we, if we had some set of equations where we have to say, are we in this one, are we in this one, are we in this one? Instead, we can just use our one implicit differentiation to figure out what the slope would be, regardless of what our which one we're on, right? Because it's the entire thing for our x and our y, because it actually models the relationship of x and y as you go to different parts of this folium. What about if we have higher order derivatives? So in this example, we want to find y double prime, so the second derivative of y. And we have the function, or we have the equation x to the 4th plus y to the 4th equals 16. So just like before, first thing we're going to do, just like we wanted a second derivative previously, we're going to take the first derivative, and then from there, we're going to find the second derivative. So we're going to take the first derivative, solve for y prime, and then we will take the second derivative, also take the derivative of that to get the second derivative. So first things first, we're going to take the derivative of both sides. So d dx of x to the 4th plus y to the fourth equals d dx of 16. We're then going to take d dx of x to the fourth plus d dx of y to the fourth equals d dx of a constant, right, because there's no x in it, means that this is going to be equal to 0. d dx of x to the fourth is going to be 4x cubed plus derivative of y to the fourth is going to be 4y cubed times the derivative of y, which is going to be y prime, equals to 0. I'm going to subtract 4x cubed from both sides. This is going to give me 4y cubed times y prime equals minus 4x cubed. I'm going to divide by 4y cubed on both sides. And I'm going to have that y prime is equal to, so the 4's are going to cancel, so I'm going to have minus x cubed over y cubed. So this is my first derivative. Now, in order to get my second derivative, what I need to do is I actually need to take the derivative of this equation. So let's do that. So we have d dx of y prime equals d dx of minus x cubed over y cubed. So doing this, what do we have to do? Well, this is just going to be the quotient rule to take this derivative, right? Because this is going to be our f term, this is going to be our g term, so we have to use our quotient rule, which is going to be g f prime minus f g prime divided by g squared. So when we take the derivative of y prime with respect to x, this is actually just going to be d dx dy dx, which is then going to become dy dx squared, which is actually going to be dy y d dx. It ends up being d squared y over dx squared. But the thing is, we're just going to call it y double prime. I'll talk later on in another video about how you actually take the derivative of a derivative, and I'll show you how it actually works out to be what we're looking at. But for now, just treat it as y double prime. So now to take the derivative of this inside part, what we're going to have to do is we're going to have to leave our g alone, which in this case is y cubed. So this is going to be y cubed times, now remember, when I take the derivative, I still have to consider my y terms as a chain rule, right? So in this case, I left my y term alone. I take the derivative of minus x cubed. So the derivative of minus x cubed is going to be minus 3x squared. Minus. Now I'm going to leave my f term alone. This is going to be minus x cubed times the derivative of my g term. So just like before, I'm taking the derivative of y cubed. So in this case, it is going to be 3y squared times the derivative of the inside, which is going to be y prime. Okay, so now what I need to do is I need to simplify this a little bit. Oh yeah, I forgot prime. Now I need to divide by my g term squared. So this is going to be y cubed squared. Okay, so now let's simplify this a little bit. So first things first, I'm going to distribute this. So we're going to have y double prime is equal to minus 3x squared y cubed minus a negative is going to give me plus. So this is going to be plus 3x cubed y squared y prime over y to the sixth power to the squared, so the second power, which would be, you multiply them, this becomes y to the sixth. Now that we have substituted in our y prime as negative x cubed over y cubed, I'm going to simplify this a little bit. So first thing I'm going to do is, if I kind of think about this, this term here is the same thing as saying 3x cubed y squared times negative x cubed over y cubed. So in this case, I'm going to bring the negative forward. I'm going to bring to the x terms together, and then I'm actually going to want to get, let me write it first actually. So we'll have that this is y double prime equals minus 3x squared y cubed. Bring the negative forward. This is going to be minus 3 x cubed times x cubed, which is going to be x to the third, plus 3, which is going to be x to the sixth, y squared over y cubed. And then, of course, this entire thing is divided by y to the 6th power. By the way, we do have the derivative now with respect to x's and y's, but again, we're just simplifying it because right now we have a fraction within a fraction, and we don't really like to leave it that way. So the way I'm going to fix this up is I'm actually going to multiply this first term by y cubed over y cubed. So what does this do? Well, in this case, now what this is going to be is this is going to be 3x squared. Y cubed times y cubed is going to be y to the 6th divided by y cubed. And then minus, don't forget your minus. I forgot my minus in the first one. That's why I fixed it as I said it. 3x to the 6th y squared over y cubed. And then this whole thing is over y to the 6th, which you can think of as y over 1. So now we have fractional division, right? We have a fraction divided by a fraction. So what we do is we multiply by the reciprocal, which is the same thing as saying I'm going to pull this into here, and I'm going to pull this one up to here, which that doesn't change it. So we now have that y double prime is equal to minus 3x squared y to the 6th minus 3x to the 6th y squared divided by y to the 9th power. And then I'm going to simplify it just a little more. First thing, both of these have a negative. I'm going to pull that out to the front. So this is going to just be minus. And then I have y to the 6th. I have y squared. So I can actually divide two of these y's. So this is going to leave me with minus 3x squared y to the 4th plus 3x to the 6th divided by y to the 7th power. And I'm pretty sure that's about as simple as we can make this. Well, I mean, I guess if you want to make it a little bit more precise, sorry, I know this is getting kind of convoluted. I could pull, this one has a 3x squared in it. This one also has a 3x squared in it. So we actually could make this minus 3x squared y to the 4th plus x to the 4th over y to the 7th. So I mean, we could simplify it that way a little bit just because it's now if we were actually plugging in x and y's, you know, we can figure out what this term is. But either way, this is how you would take the higher order derivative, is you take the derivative of your original function using implicit differentiation. You solve for y prime. Once you've solved for y prime, you then take the derivative of this and solve it for y double prime, or the second derivative. And anywhere you have y prime, you then want to plug in what you know y prime is equal to in terms of x's and y's. Plug that in, and now you have the second derivative. Of course, we did a bunch of simplification, but once we got to this step, we had the derivative. And then if you wanted to keep doing this, you want to take third derivative, you do the same thing. You take the derivative of whatever you got, right? This is y prime, double prime. You would take the derivative of this to get the third derivative, and then if you have a y prime, you plug in whatever y prime is equal to. If you have a y double prime, you plug that in. You simplify it. You can keep doing this for as many derivatives of higher order as you need to. For our last example, we want to find the first derivatives. We want to find y prime if we have sine of x plus y equals y squared cosine of x. So when we're doing this, we're going to take the derivative with respect to x of both sides. So this is going to be d dx of sine of x plus y equals d dx of y squared cosine of x. So now looking at this, what are we going to have to do? Well, for the left side, we're going to have to use the chain rule, right? We're going to take the derivative of the outside, then we're going to take the derivative of the inside. For the right side, this is going to be the product rule, which technically also with the chain rule because of the y squared when we take the y prime term. So let's do our left side first. We have d dx sine of x plus y. So the first thing we do, leave the inside alone, treat this as your u, and take the derivative of sine. And that gives us cosine of x plus y. Now we take the derivative, d dx, of x plus y. All right, so let me just write that down actually. Let's not skip any steps. So this would be d dx x plus y. For this one, we're going to be using the product rule where y squared is our f term, cosine of x is going to be our g term, right? And it's going to be g f prime plus f g prime. And then let's do that. So this is going to be equal to leave g alone, which in this case is going to be cosine of x. And then we take the derivative of y squared, right? So this is going to be 2y times, remember we got to do chain rule, derivative of y, which is going to be y prime, plus leave f alone, y squared, and then take the derivative of cosine of x. Cosine of x gives us minus sine of x. Okay, so now let's go back to our left side. We have cosine of x plus y, derivative of x plus derivative of y, right? Because we have derivative of x plus y, we can distribute this derivative to derivative of x plus the derivative of y based on our derivative rules. So if we take the derivative of x, this is going to be equal to 1 plus the derivative of y. Well, if we take the derivative of y, this is going to be equal to derivative of y, the outer part would just be 1y to the 0, which is going to be 1, and then we take the derivative of the inside, which is y, and we get y prime, right? It's still kind of a chain rule, but yeah, we're still doing y prime equals. And then I'm going to simplify this a little bit. First, on the left side, I'm going to continue to this side. I'm going to distribute the cosine, so cosine of 1, so this is just going to be cosine of x plus y, plus y prime cosine x plus y. On my left side, I have 2y y prime. I'm just going to pull that to the front. This is going to be 2y y prime cosine of x plus y squared times minus sine. So this is going to be minus y squared sine of x. Okay, so now you'll notice that both sides of this have y and y prime terms. Right, so we have a y prime term here, a y prime term here, a not y prime term here, a not y prime term here. So I need to get my y prime terms to one side of my equation and my not y prime terms to the other side of the equation. So this is going to, I'm going to leave this y cosine of x plus y here, and I'm going to bring this y prime term over by subtracting 2y y prime cosine of x. So this side is going to be y prime cosine of x plus y minus 2y y prime cosine of x equals. So now I have this term left over here, and I'm going to subtract cosine of x plus y. So this is going to be minus y squared sine of x minus cosine of x plus y. Okay, so just as before, I've got a y prime term here, I've got a y prime term here. Pull them out. So I'm going to have this side is going to be y prime cosine x plus y minus 2y cosine of x. I'm going to divide both sides by this cosine x plus y minus 2y cosine of x. So cosine x plus y minus 2y cosine of x. This is going to cancel with this, and I'm going to be left with y prime equals, I have it written differently on the slide. I have the minus cosine term up first, but it doesn't really matter. So I'm going to leave it in the way I have it. Minus y squared sine of x minus cosine x plus y divided by cosine x plus y minus 2y cosine of x. And I think the only reason I did it on the slide that way is I put the cosine of x plus y terms in the front, and then the cosine and sine with just respect to x on the left side. But either way, this is still the same thing, and we have our implicit differentiation to give us y prime. We have that y prime is equal to minus y squared sine of x minus cosine x plus y divided by cosine of x plus y minus 2y cosine of x. So you can see that it does make things a lot easier to be able to do implicit differentiation, because if we had something like this, sine of x plus y, how do we even split that, right? That becomes so much more complicated than just like we did in the beginning when we had a circle where we could just split it easily into two explicit functions in terms of x. So hopefully this has been helpful. This is generally the topic that most Calc 1 students really seem to struggle with. And that's why I wanted to give you like a good variety of examples to kind of walk you through how we could do this based on a lot of different situations. And the key thing is just remember, anytime you're taking the derivative with respect to x on a y term, whatever that y term is, you treat the derivative like you normally would, leaving the y as a constant, right? U-Substitution. But then you take the derivative of the inside, which is where you're going to get your y prime from, or dy dx. Hello everyone. In today's lesson, we're going to be looking at how to use derivatives to find maximum and minimum values. So to begin, let's actually define what an absolute or global minimum and maximum value is. So let C be a number on our domain D of a function f. So we have some function f, and C is some value on that domain D. Fc is an absolute maximum value on f if our function fc is greater than or equal to f of x for all x in D. So that is to say, our fc is greater than or equal to all f of x, so for all x, on our domain D, or in D. This would be a global or absolute maximum. And then if we have that our function at that point C is less than or equal to every value of x, so for all x on D, this would be a global minimum. Now what does this mean? Well, it just means that at this point at some C, that if there is no f of x which is greater than this value, then this would be our global maximum. Now you'll notice that it is or equal to. That means that you could actually have more than one global max, right? For example, if I had like a sine wave which went like this, then each of these would be a global max, because if I looked at this point right here, this might be C1 and this might be C2, these would both be a global maximum because they are larger than any other x value, but they are equal to each other, meaning that this is both a global and a local maximum. Same thing with minimum. If it is less than or equal to any value of f of x on that domain D, then it is a global minimum. So for example, if we have some graph, let's say it looks something like this. Something like this, right? So in this case, we have multiple maximums and minimums we could look at, right? So we have a maximum right here, and if you look, there's no value that is above this point, meaning that this would be a global or absolute maximum. And at this point here, if we were to consider, drawing a line across here, there's no value that is less than this, so this would be a global minimum. Fc is a local minimum on our function f if our fc is greater than or equal to all f of x near C. So for example, if our C is this value, right, let's call this one C1, then near this C1, if there's no other value near it that is higher than it, then this would be a local minimum or maximum. If we had some C2 right here, then at this point around this value here, this would be a local minimum, right? There's nothing around this which is lower than this. Let's suppose you have some function that looks something like this. Then in this case, where would our local minimum maxima be? So for our local maximum, if we look at this point here, let's call this one C1. At this point nearby, there are no other values that are higher than this point. So this would be a local maximum. Similarly, if we look at this point here, there's no values nearby, near this C value, we'll call this one C2, that are higher than it. So this is also a local maximum. So at C1 and C2, we have a local maximum. Now, if we were to compare these with each other, though, if I were to look at this point and go off to the left and off to the right, you'll see that there are no other points that are greater than this. So this one would also be our global maximum. If we were to look at our minimum, we have some value here. Let's call this one C3. Where this nearby, there's no values that are less than this, so this would be a local minimum. Similarly, if we had C4, then at this point nearby, there's no values that are less than this, so this would also be a local minimum. So you might wonder, are either of these a global minimum? Well, of these two, this value is the lower point, so if I go off to the right, you'll see that there's no lower values, but if I go off to the left, I actually do have the fact that this function is going down towards negative infinity, meaning that both of these are local minimum, but they are not global minimum, because the whole point of our definition was that it has to be true for this c to be less than or equal to all values of x within our domain D. So what does this mean? Well, it means whenever you're looking for maximums and minimums, you're going to be looking for where are possible values where this might be true, right? We have something like this. And you also need to check the limits as you go off to infinity. What's happening with my function as I go off to negative infinity? And what's happening with my function as I go off to positive infinity? Because in the end, I may have, when I find these specific maximums and minimums, I may have some behavior where, for example, like over here off towards infinity, I have it converging on some value L. So in this case, this is not going above this maximum. But as I go off towards negative infinity, this function went off down towards negative infinity, meaning that this local minimum would not be a global minimum because there are values that are less than this. So how do we actually find our local minimums and our local maximums? Well, if you look at what I drew here, every time I did this, I drew a line. Now, what do we know that we've learned recently to tell us what the slope of this point would be, which means we have a horizontal line? And that is, if we have some function that is continuous, if my derivative f prime of x is equal to 0, this is going to be a candidate, right? Because if you look at our slope of this graph that I drew, we have a positive slope, and then we have a negative slope. But where the slope is equal to 0, this is a candidate for a local minimum or maximum. When I get to here, I'm going downward, and then now I go upward over here. Again, I have a slope of 0. This one has a slope of 0, and this one has a slope of 0. So one of our candidates that we could look for is f prime of x equals to 0. The other thing we need to consider, let's actually write this down. These are going to be our critical values. And to find our critical values, these are going to be when f prime of x is equal to 0. That's where we have a horizontal slope, meaning that we could be going from upward slope to downward slope, meaning we have a maximum. We could be going from downward slope to upward slope, which means we have a minimum. Or we could be going from upward slope, hitting 0, and then going up. That would mean we have a saddle point, something like this. It's badly drawn, but you get the idea. Or it could be like this, going downward, hit a slope of 0, and then go back down. So this does not necessarily mean you have a maximum or minimum. It just means it's a candidate for a maximum or minimum. We also could have where our derivative is does not exist. So let's consider an example of something like this. If I had the function f of x equals 1 over x, here our x cannot be equal to 0, right? Because at 0, it does not exist as we take the derivative as it approaches. Right? What's going to happen there? Well, as I try to plug in 0, what's happening? I don't know why I drew dotted lines. What's happening with this function? Well, as I approach 0 from the left, meaning I have negative values, right? Like 1 over negative 10, 1 over, and then what's happening is I'm getting smaller and smaller in my denominator, which means the value is getting bigger and bigger, but it's in a negative direction. And if I approach from the right side, it's going to look like this. So what happens at 0? Well, guess what? Now this means that this function does not have a global max or a global min because I have part of my function going off to negative infinity and part of my function going off to infinity, meaning that at does not exist. This would actually show that none of these possible candidates that I could have would be a global or an absolute maximum or minimum. So we do have to consider where our derivative does not exist. And then last, we do need to consider what is the behavior of our limits as x goes off to plus or minus infinity on our function, right? So what's happening with our function as we go off to infinity? We need to see what that behavior is to determine if we have a global or a local maximum minimum for any possibilities that we find based on our critical values. For our first example, let's consider the function f of x equals cosine of x. And we want to determine where our local minimum and maximum values are. So if we were to draw out what a cosine looks like, right, it's going to start at 1 when we're at x equals 0, and then it's going to go down, it's going to go to negative 1, and then it's going to go back up to positive 1, and it's going to repeat this over and over. And of course, it'll do the same thing if we go in the negative direction. So this means that our cosine of x is going to be greater than or equal to negative 1 and less than or equal to positive 1. Now, where are these values occurring, right? Because we know, just by looking at it graphically, that I'm going to have a maximum here and a maximum here, and a maximum here, and then it's going to repeat over and over again. And I'm going to have a minimum here, and I'm going to have a minimum here, and again, it's going to repeat on forever. So let's just look to the right side, and we can also consider it's happening the same way on the left. So I'm going to start at 0, which you can actually think of this as 0 pi. And then this is going to be, so when it hits 0, this is going to be pi over 2. This point here is going to be at 2 pi over 2, which is just equal to 1 pi. This point here is going to be 3 pi over 2. And then this point here is going to be 4 pi over 2, which is just equal to 2 pi. That means that basically every 2 pi, this is going to be a maximum. So in this case, it's going to be cosine of 2 in pi, and this will be when it's equal to 1, right? So if I plug in 0 for n, I'm going to get cosine of 0, and that equals 1. If I plug in 1 for n, I'm going to get 2 times 1 is 2, 2 pi. That's equal to 1. If I plug in 3 for n, I'm going to get 2 times 3 is 6, so 6 pi. So cosine of 6 pi will also be 1. Same thing if I go the other direction. Now for my local minimums, I need to have it where it's going to be every pi, so some odd number pi over 2. So in this case, it's going to be cosine of 2n plus 1 pi. And why is this? Well, because in this case, if I were to plug in 0, I'm going to get 2 times 0 is 0, so I'm going to get 1 pi. Cosine of pi is going to be equal to negative 1. If I were to plug in 1 for n, I would get 2 times 1 is 2, plus 1 is 3, so 3 pi. That would be when I come back around, and I'm going to be back down in the negative again. For our next example, let's describe the minimums and maximums for the function f of x equals x squared. So in this case, I'm going to draw a graph again where I have my xy axis, and what's going to happen as we plug in our values to this? Well, if I have x equals 0, I'm going to get 0. As I plug in 1, I get 1 because 1 squared is 1. If I plug in 2, I get 4. If I plug in 3, I get 9. So what's happening is I go off to the positive direction. It's going to increase faster and faster, exponentially. And of course, if I plug in negative values, because it's squared, it's going to do the same thing, but it's going to make it positive. So I plug in negative 1, I get positive 1. If I plug in negative 2, I get positive 4. So this is going to look like this. So kind of intuitively looking at this, what are my local and global minimums and maximums going to be? Well, it looks like I'm going to have a minimum at x equals 0, which is lower than any other value on this function, meaning that this is going to be a local minimum, but specifically it's going to be a global minimum. If I look at what's happening to the left and the right, this is going to go off towards infinity, meaning that I'm not actually going to have any maximums. So in this case, because x squared has to be greater than or equal to for all values where my function f of x is greater than or 0 for all x. This means that 0, or f of 0, is going to be my minimum. So this is going to be my absolute minimum. And it's also going to be a local minimum, right? Because again, remember, your local minimum just says that near this, there's no other values that are less than this. So it's a local minimum, but it's also an absolute minimum. Now, you might be wondering, why is this so important, local versus global? And a lot of times this is because when you're trying to do any sort of minimization or maximization problems, you're looking for that global minimum. And this is a big problem, especially when you're doing any sort of minimization or maximization algorithms, because a lot of times they can get stuck in a local minimum, right? So I might have something kind of like this, where it goes down, comes back up, and maybe this is the value that I actually want to find. But depending on the algorithm I use, maybe something like Newton-Raphson, if I start over here, right, I might come over here, and then I come over here, and I'm going to home in on this one. So while I will have found a minimum, it won't be the minimum that I want. And there's a lot of ways you can kind of deal with this, but this is an actual thing you might encounter if you get into anything like computer science or machine learning or anything like that. Because a lot of problems, you'll do something like gradient descent or some other method where you're trying to figure out what is this global minimum. And a lot of times, to save on computational power and time and effort, you might use something called like a greedy algorithm, in which case you're going to take the next step, which makes your answer better and better and better until it stops getting better. Meaning you might actually end up getting a local minimum or maximum instead of a global minimum or maximum. And then, of course, how do you deal with that? Well, it might be that you use something like Monte Carlo simulations where maybe you start in different starting points and see what minimums do I end up in, and do I have one that seems to beat out the others? Could be other methods like that. But for now, let's just focus on the fact that, if we have something like this, where in nearby, there's nothing below it, this is a local minimum. But of course, if I were to go outward, you'll see that there are in fact values that are less than it. If I look at this one, this is a local minimum also. But as I go out to left and right, there's nothing that is lower than it, meaning it is also a global minimum. What about if we had the function f of x equals x cubed? So just like before, if I were to quickly draw this, what is this going to look like? Well, as I plug in positive values, they're going to grow exponentially. So it's going to grow like this. As I plug in negative values, because it's now an odd function, this means that it will also stay negative. So therefore, it's going to look like this. So based on this, what is our local minimums and maximums? Well, in this case, if we were to find our derivative, which we'll talk about later when we talk about our derivative rules, and set this derivative equal to 0, we would get that we have a possible candidate right here, where the slope is equal to 0, where it's going from a decreasing change in slope to an increasing change in slope. But as we talked about, one of those candidates could also be saddle points, which is exactly what this is. So based on this function, as we take our limit, as x goes to negative infinity, this is going to go to negative infinity. And as we take our limit, as x goes to positive infinity on our function, this is going to go to infinity. So since infinity and negative infinity are not real numbers, this would mean that no local minimum or maximums exist on this function x cubed. For our fourth example, let's look at this graph here. So we have a function that we don't really know what the function is, but we can look at it visually and we can kind of determine what our local and absolute maximums and minimums would be. So we have the points A, B, C, D, and E. So looking at this, if we wanted to know what the local maxes are, it would be A, C, and E. If we want to look at what our local minimums would be, it would be B and D. Now, are any of these points higher than the others to be our global maximum? Well, in this case, it's kind of hard to tell because this isn't the best drawn image I've ever had. But in this case, C is just a little bit higher than E, meaning that it is our global maximum. For our minimums, we have between B and D. D is lower than any other value, therefore it is our global minimum. Hello everyone, in this lesson we're going to be looking at how derivatives affect the shape of a graph. So to begin with, we're going to start with our mean value theorem. Mean value theorem says if f is continuous on an interval a to b and is differentiable on a or b, then there exists a number c between a and b such that the derivative f prime of c equals f of b minus f of a divided by b minus a. Or we can then rearrange this to f of b minus f of a is equal to the derivative f prime of c times b minus a, right? Because what we're saying is that we have some f prime of c, which is equal to f of b minus f of a divided by b minus a. So all this is saying is that if I have some point a, this is my interval a to b, and I have some point on a, and I have some point on b. What this means is that to find the slope between these two, right, if I have this a here, this is going to be f of a. And if I take this point b here, the y value is going to be f of b. So then if I were to rise over run or change delta f over delta x, this is just going to be f of b minus f of a divided by b minus a. So all this is telling me is the slope. The slope between point A and point B is going to be f of b minus f of a over b minus a. And then what I can do is I can then multiply this. So I take both sides and I multiply by b minus a. And then these, of course, will cancel, and I'll be left with f prime of c times b minus a is equal to f of b minus f of a. So what does this actually mean? Well, what this is telling us is that if I have some point a and b on this interval, and I'm going from a point f of a to f of b, it means that somewhere in this interval, there exists at least one point C where my slope will be equal to the average or the slope between these 2 points, right? So for example, let's say I have something like this. This is my A, this is my B, and let's say that it does something like this. I got my A here and I got my B here. So if I were to figure out my slope, it'd be like this. Well, if my function were to look something like this, what does this mean? Well, if I were to consider my slope at every point, right? So if I pick a point here, I got a slope like this. If I got to pick a point here, I got a slope like this. There's going to be some point where my slope is going to be the same as this slope between the points A and B. Similarly, as I come down here, I've got a negative slope, negative slope, negative slope, but there's going to be another point where I get to here, where again, I'm going to have a slope that is equal to. So at this C1, I have a slope that is equal to the slope between these 2 points. At C2, I have another slope that is equal to this. And then of course, I will also have one here, right? Because as I go from at some max or min, as I go from positive to negative, I'm hitting all the possible slopes between there, meaning that there exists at least one value C where your slope will be equal to this f of b minus f of a over b minus a. And of course, we're just saying that we can rearrange it to try to figure out what our derivative could be based on this relationship. So looking at our slide here, you can see that I have an example of the point A to B, and as it just goes in one nice gentle arc, you will see that at some point as we go from positive slope, positive slope, positive slope, we're going to hit a point where it's the same as the slope between the 2 points, and then it's going to be negative slope. Or if we look at our second graph, you'll see that we have something where it's a point, it goes down pretty sharply, and then up, and then back down pretty sharply. But when it changes from downward to shifting upward, then it's going to have a point C1 where it's equal to the slope between A and B. And then it's going to go up, and then as it curves back downward, it's going to cross a slope again where it's equal to the slope between A and B. Now, let's say, for example, that I have a straight line, right? Let's say that I have something like this. I have some A, and I have some B as my boundaries. And if I just had a straight line between here, then every C would be the same slope, right? Because if I take the derivative at any point, it's just going to be that line. So what it's saying is that there exists at least one C. So we have a continuous function on our interval A to B, then there exists at least one solution where the slope will be the same as the average slope between these 2 points, which means that we can then figure out at least one point that this must be true. Our first example says, suppose that 2 is less than or equal to f prime of x is less than or equal to 4 for all values of x. What are the minimum and maximum values of f of 5 minus f of 3? So we have 2 is less than or equal to our derivative of our function at x is less than or equal to 4. And we want to find all the minimum and maximum values for f of 5 minus f of 3. So looking back at what we have here, right, this is our f of b, meaning our b is going to be equal to 5, and our a is going to be equal to 3. So this is going to give us some idea of what our boundary is, right? So we have some function, and we have 3 and 5. So this is our interval that we're looking at. So what we're going to do is we're going to consider the fact that f of 5 minus f of 3, which is this term, we know is going to be equal to the derivative at some point c times b minus a. So let's write that down. We have f of 5 minus f of 3 is going to be equal to our f prime of x and then b minus a. Well, we already talked about the fact that b is going to be equal to 5 and a is going to be equal to 3. So then plugging this in, right, 5 minus 3 is going to give us 2. So we know that f of 5 minus f of 3 is equal to 2 f prime of x. So now what we're going to do is we're going to go back to this part here. We know that our f prime of x is between 2 and 4. So we have 2 f prime of x. So let's get this in terms of 2 f prime of x. So if I wanted to make this 2 f prime of x, I would need to multiply everything in the inequality by 2. So we have 2 times 2 is less than or equal to 2 f prime of x is less than or equal to 4 times 2. So this means that we will have 4 is less than or equal to 2 f prime of x is less than or equal to 8. So what does this mean? Well, now what we can say is that in our interval, we have 4 is less than or equal to the difference of f of b minus f of a is less than or equal to 8. So what this is saying is that our minimum maximum has to be somewhere between whatever f of a is and f of b, which means that we have our minimum at 4 and our maximum has to be at 8, right? We don't know exactly where they're happening, but we do know that somewhere in this, we have a maximum and a minimum at these 2 points, somewhere within this interval. So in this case, we have a minimum at 4 and a maximum at 8. So next, let's consider what does the behavior of our derivative tell us about our graph? Well, for the first thing, if we have f prime of x is greater than 0, means that we have a positive derivative, meaning we have a positive instantaneous rate of change or a positive slope. So if we have f prime of x is greater than 0 on an interval, then f is increasing. If our f prime of x is less than 0, which means we have a negative slope, it means that our function is decreasing. And if our f prime of x is equal to 0, at that point on f, it either is a minimum, a maximum, or it is an inflection point, right? So this is what I talked about when I have saddle points, where it goes from positive, hits 0, and then continues positive, or it goes from negative, hits 0, and then continues negative. We can use this fact for what's called the first derivative test. So suppose that c is a critical number on a continuous function f. So f prime of c is either equal to 0 or f prime of c does not exist. Then it means that we have a local max if f prime of x changes from positive to negative slope as you go from left to right around that critical value. We have a local minimum if f prime of x changes from negative to positive at c, and we have that f prime of x does not change at sign c, then it's not a local min or a max. So what does it actually mean? Well, let's say that we have some point c where we have a slope of 0. What we're saying is that if we have a negative slope to the left of c, and then we have a positive slope to the right of c, then this c must be a minimum, right? So if we go from a negative slope to a positive slope, this is called the first derivative test. If as I find my critical value and I find that this is a candidate for a local min or a local max, I can look using the derivative to the left and to the right and look at the behavior of the slope. If I'm going from negative to positive, it is a local minimum. If instead my c, I'm going from positive to negative, so positive to negative, this would be a local maximum. And then of course, if I'm going from a positive and staying positive, or if I'm going from a negative slope and continuing it to a negative slope, this would be an inflection point. It's not actually changing, so it's not a min or a maximum. So this is the idea of our first derivative test. We're going to find our critical values to figure out what our candidates are for a maximum and our minimum, and then we can actually use that derivative, look to the left and the right, and we can determine whether we're going from negative to positive or positive to negative. Or if we stay negative to negative or positive to positive, it means that it's not a maximum or a minimum. So let's do an example to try this out. Suppose that we have the function f of x equals 3x to the fourth power minus 4x cubed minus 12x squared plus 5. And we want to find out where this is increasing, decreasing, the minimum values and the maximum values. So the first thing we're going to do is we're going to take our derivative, right? Because our critical values are going to be where our f prime of x is equal to 0 or f prime of x does not exist. So we're going to take our derivative. So f prime of x, this is going to be equal to, I'm going to bring my 4 down. This is going to be 12x cubed minus, I'm going to bring my 3 down, 12x squared, bring my 2 down, minus 24x, and then the constant goes away because there's no x there. So derivative of a constant is 0. So now I have 12x cubed minus 12x squared minus 24x. So I need to see where this does not exist or is equal to 0. Well, based on the fact that I have a polynomial, right, I can plug in any real number, this will exist. So right now, this f prime of x does not exist is not a possible candidate. So now I need to figure out where is this equal to 0. right? So what I'm going to actually do is I'm going to rearrange this a little bit. I have 12x in every single one of these, right? 12x cubed has 12x, minus 12x squared has 12x, and minus 24x has 12x. So I'm going to pull 12x out, and this is going to leave me with x squared minus x minus 2. And I want to set this equal to 0. So as before, what we're going to do is we're going to look at 12x equals to 0, which gives me x equals 0. And we're going to look at x squared minus x minus 2 is equal to 0. So in this case, I'm going to factor this. So I want to find a value that is multiplies to give me -2, but adds up to give me -1. So this is going to be x minus 2, x plus 1. Now, if I were to multiply -2 times +1, I get -2. If I were to add -2 plus 1, I would get -1. So these are my two values. So I'm going to set each of these to 0, right? Because if either of these are 0, this will make the entire thing 0. So I have x minus 2 equals 0, which means that x equals 2. Or I have x plus 1 equals 0, which means x equals -1. So these are my three candidates for minimums and maximums. So what I'm going to do is I'm going to draw a picture, right? I got my number line, and I've got -1, 0, and 2. So at -1, 0, and +2, these are possibilities for minimums and maximums. So now what I'm going to do, I'm going to just make a little table just so we can kind of keep track of everything. So we've got our interval, we have our test, we have our f prime of x, and then, of course, we've got whether it is increasing or decreasing. So first thing we have to do is we want to consider this interval here from -infinity up to -1. So our first interval we're interested in is -infinity up to -1. Our second interval is going to be from -1 to 0. Our third interval is going to be from 0 to 2. And our last interval is going to be from 2 off to infinity. So these are the intervals that we're going to be considering whether we are going downward, upward, and what does that mean for these points, these critical values, whether they are minimum or maximum. Okay, so next thing I'm going to do, I'm going to pick some values to test this. So for the first interval, from -infinity to -1, I need to pick a value that's over here that I can test this with. So what I'm going to do is I'm going to pick a value like -2. For the next one, I need to find a value between -1 and 0. So maybe I would pick something like -0.5. For this one, 0 to 2, I'm going to pick 1, because that's an easy value to work with. And for 2 off to infinity, I'm going to pick, I don't know, let's say 3. So now what I'm going to do is I'm going to take these values that I'm testing, right? So I picked a value here, 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 and here, one of them in each interval, to see what the slope is doing. So I'm going to plug these values into my derivative, my f prime of x, and I'm going to see whether it ends up being positive or negative. So what we could do is you could plug these in, right? We could go to our derivative and we could plug in, let's do 1, just because that's an easy one. Then this would end up being 12 times 1 cubed is 1, so 12 minus 12 times 1 squared, which is, so 12 minus 12, those two cancel. We're left with -24, which in this case would mean that it is negative. Or what I could do to make it even easier is I'm going to go back to this real quick. We had 12x times x squared minus x minus 2. But we said this x squared minus x minus 2 is equal to x minus 2, x plus 1. So my derivative is equal to 12x, x minus 2, x plus 1. Now what I could do is I could just look at, because I have three terms that are multiplied by each other, I could just look at, if I plug this value in, is this going to be a positive or negative? Is this going to be a positive or negative? Is this going to be a positive or negative? So if I did that, if I plug in -2 into 12 times -2, that's going to give me -24. So that's a negative. If I plug in -2 into x minus 2, I'm going to get -2 minus 2, which is -4. That's a negative. And if I plug in -2 times into x plus 1, it's going to be -2 plus 1 gives me -1, so that's going to be a negative. So if I have a negative times a negative times a negative, that's going to give me a negative value. Now let's look at -0.5. If I plug in -0.5 into here, it's going to be 12 times -0.5 is going to be -6, so that's going to be negative. If I plug in negative 0.5 into x, I have negative 0.5 minus 2, so minus 2.5, that's going to be negative. And if I plug in negative 0.5 into x plus 1, so negative 0.5 plus 1, that's going to be positive. So if I have a negative times a negative, that's going to be a positive. And then a positive times positive would give me a positive. Now I'm going to plug in 1. 12x, that's going to be positive. 1 minus 2, that's going to be negative. 1 plus 1 is going to be positive. So a positive times a negative times positive is a negative value. And then last, I'm going to plug in 3. 12 times 3, that's going to be positive. 3 minus 2, that's going to be positive. And then 3 plus 1, that's also going to be positive. So positive times positive will be positive. So this means that on my first interval, I have that it is decreasing. For my second interval, I have that it is increasing. For my third interval, I have that it is decreasing. And for my fourth interval, I have that it is increasing. So basically I have it's decreasing here, it's increasing here, it's decreasing here, and it's increasing here. Meaning that I have a negative slope, then a positive slope, then a negative slope, and then a positive slope. So what we talked about, at this point, negative 1, because I'm going from negative to positive, that means that x equals negative 1 is a minimum. At x equals 0, I'm going from positive to negative, meaning that I have a maximum. So at x equals 0, I have a local maximum. And then at x equals 2, again, I'm going from negative to positive, which means that x equals 2 is a local minimum. So now using our first derivative test, we've actually determined whether each of the negative 1 and 2 are both local minimum. 0, so x equals 0, is a local maximum. Now, if I wanted to know which one of these could be a global minimum or maximum, what would I have to do? I would have to first take each of these values, plug them into the original function. So for example, let's say I plugged in 0. I'd get 0 minus 0 minus 0 plus 5. So the value of this one would be 5. I'd plug in negative 1, I'd plug in 2, but then I'd also have to consider the fact that I'm not on a closed interval, so I have to consider what the behavior is as I go off towards negative infinity and positive infinity. So right now, this first derivative test is just telling us where, based on our critical values, where we have local minimum and local maximum values. Now looking at our slide, you can see here that if we have the function 3x to the fourth minus 4x cubed minus 12x squared plus 5, you see an image kind of like what I drew on my board, which is we go from a negative slope to a positive slope, giving us a minimum, a positive slope to a negative slope, which will give us a maximum, and a negative slope to a positive slope, giving us a minimum. Then what we could do is we could state that from negative 1 to 0, or from 2 to infinity, right? So we have these two intervals. These are going to be where our function is increasing. From negative infinity to negative 1, and from 0 to 2, these would be where our function is decreasing. So we have, again, local minimums at x equals negative 1 and x equals 2. If we were to plug those values in, f of negative 1 is equal to 0. F of 2 is equal to negative 27. So that would be, for those two, based on this behavior, then it looks like f2 is probably our global minimum. But we don't know that because, again, we have to check our limits as we go off to infinity. For our local maxes, if we plug in 0, again, we talked about this one previously a minute ago, this would be equal to 5. So now that means that we have local minimum at x equals negative 1 for a value of 0, and f equals 2, or x equals 2 for a value of negative 27. And we have a local maximum at x is 0, which is equal to 5. So now that we've talked about our first derivative test, where we take the derivative of our function, we look at our critical values where their derivative is equal to 0 or a derivative does not exist, and then we look at the behavior that's happening to the left and to the right of that to determine whether we have local maximums or local minimums at that point, or if it's neither, if it goes from negative to negative or positive positive slope. Now we're going to look at another method we could use called the second derivative test. But before we do that, we first need to talk about concavity. So concavity refers to a bend in a curve. So if a curve is concave up, that means that all of its tangent lines will be below the curve. If the curve is concave down, it means that all the tangent lines will be above the curve. And then points where a function changes concavity are called inflection points. So what this means is something like this. If I have a curve that's going downward like this, if I were to take the derivative at any given point, the derivative would be above the curve when it is concave down. And if I have something like this would be concave up, where if I took the derivative at any given point, it would be below the curve. So this one is concave down. This one is concave up. Now you might wonder, why is this useful to know? Well, if you think about it, this is actually telling us the rate of change of the derivative, or the rate of change of the rate of change. This is what we look at when we get the second derivative. So if the function represents, for example, like position, right? Let's say you have your car and you're sitting at point 0. If I were to move and go forward, I'm at some now positive position. If I were to go backwards, I would end up at some negative position. The derivative is the rate of change. It is the change in position, also known as your velocity or your speed. So you can be going forward, which means you have a positive velocity or a positive rate of change. I could be going backwards, which means I have a negative rate of change. The second derivative tells us the rate of change of the rate of change. So if velocity is my first derivative, my second derivative would be my acceleration, which means that I could be going forward and speeding up, or I could be going forward and slowing down. I could be going backwards and then speeding up, meaning going more forward, or I could be going backwards and going faster in the backwards direction. Concavity describes this behavior, right? Because even though at this point, if I were to just look at slope, what's happening here? Well, this is a positive slope. This is still a positive slope, and then I'm at a certain point here where now I have a slope of 0. And now I have a negative slope, and now I still have a negative slope. But if we look at our concavity, what this is saying is that here, where it's going positive slope, but it's negative curve, meaning that it's like you're going forward, but you're slowing down until you get to a certain point where you stop. And now suddenly you are continuing to slow down, which means continuing to get more negative, meaning you're now going backwards. If I have the concave up, while this is a negative slope, it is like I am increasing. So it means like I'm going backwards, but I'm starting to like speed up in the forward direction. So it means I'm slowing down until I stop and then go forward. And then, so I hit that point where I'm at 0 velocity, and then now I have a positive velocity. So your concavity tells you the behavior of the change of the slope, right? Your second derivative. So concave down means that you have a negative second derivative. Concave up means you have a positive second derivative. And that actually leads us to our second derivative test. So it says, suppose that f prime of c is equal to 0 and f double prime is continuous near c. So is continuous near c. Then we have, if we have f double prime of c is greater than 0, which means that it's concave up, this means that we have a local minimum. If I have my second derivative at c is less than 0, which means that it's going like this, concave down, this would be a local maximum. And if I have f double prime of c is equal to 0, this is inconclusive, right? So with our first derivative, when we said we were going from positive to positive or negative to negative, that meant that we had a saddle point or an inflection point. The second derivative not being equal to 0 doesn't necessarily mean that it's not a max or a min. It just means that it's inconclusive. You'd have to do some other test, maybe your first derivative test. For our next example, we want to sketch a possible graph of our function f that satisfies the following criteria. The first is that we have f prime of x is greater than 0 on the interval negative infinity to 1. We have f prime of x is less than 0 from 1 up to infinity. We have that our second derivative of x is greater than 0 on our interval negative infinity to negative 2. We have that our second derivative of x is less than 0 from negative 2 to positive 2. And we have the limit as x approaches negative infinity on our function f of x equals -2, and the limit as x approaches positive infinity on our function is equal to 0. Okay, so now we're going to draw a graph based on this. So if we kind of look, let's start with our second derivative. So first things first, actually, I'm going to write the fact that for my slope, I have this going from a positive slope to a negative slope. So I have negative infinity to 1, I have a positive slope. From 1 to infinity, I have a negative slope, meaning I'm going positive and then negative for my slope. And this is going to change at x equals 1. For my second derivative, I have a positive concavity, meaning it's curving upward from negative infinity to -2. So -1, -2, meaning it has a positive. And then from -2 to 2, now it's going to have downward concavity. And then finally, we'll look at our behavior as it goes off to infinity and negative infinity. So as my limit is x approaches negative infinity on my function f of x is going to be -2. And my limit as x approaches infinity on my function f of x is going to approach 0. So now let's just pick some point. So we know that before this, so I'm going to kind of think of this, I'm going to put a little dotted line here. So I know that towards infinity, I am approaching this value -2. And it's concave up from negative infinity up to 2. So that means it's going to be like an upward slope. And then starting at -2 all the way till +2, I'm going to have it be concave down. But my slope is not going to change from positive to negative until I get to 1. So what's going to happen is I have a positive slope, but now so if you kind of think of a concavity, it's going like this. It's sloping upward, and then it's going to hit that -2, and now suddenly it's starting to decrease. So it's decreasing, but it's not hitting a slope of 0 until I get to 1. And now it's going to continue to decrease. I didn't draw that very well. And then what's going to happen from there is that as it's decreasing, as it goes off to infinity, it's going to approach 0. So we have something like this, right? As it approaches, the limit as I approach negative infinity would be that it's going to approach -2. As I'm coming from negative infinity, I have a positive second derivative, meaning it's curving upward until I get to -2. Now suddenly I have an inflection point where I go from increasing to suddenly decreasing. But my slope is still positive, but it's decreasing until I get to the point -1. Now suddenly my slope, as it slows down, actually hits 0, and it's starting to have a negative slope, and it's still decreasing. When I get to +2, now suddenly it's going to, still be a negative slope, but it's increasing, and it's going to, as it goes off to infinity, it's going to asymptotically get closer and closer and closer to 0, never touching it. For our last example, we're going to have our function y equals x to the 4th power minus 4x cubed. And what we want to do is we want to discuss what we can say about the concavity, the points of inflection, local minimums, and local maximums. And then we're going to try to sketch what y would look like based on that. So first thing we need to do is we need to figure out where those critical values are. So we're going to take our derivative. So this is going to be equal to 4x cubed minus 12x squared. So now we have our derivative, and we need to figure out where this does not exist or where it's equal to 0. So first things first, as the last couple examples, this is a polynomial, meaning that there's nowhere that this does not exist. There's no value of x that I can put into this that would make it not exist. Like it's not dividing by x, I don't have any negatives and square roots, anything like that. So what I'm going to now do is I'm going to pull out anything they have in common. So they both have 4x squared in them. So this is going to be 4x squared. So if I pull out 4x squared from 4x cubed, I'm going to be left with x. Minus, if I pull out 4x squared from 12x, I'm going to be left with 3. So I need to see where this is equal to 0. So if this first term is equal to 0, it'll make the whole thing 0. If the second term is equal to 0, it'll make the whole thing equal 0. So I have 4x squared equals 0. So in this case, x equals 0. Then I also have x minus 3 equals 0. So x equals positive 3. So if I were to draw a number line, that means that at x equals 0, I have a critical value. At x equals 3, so So 1, 2, 3, I have another critical value. So these are my candidates for my maximum and minimum. So first thing I'm going to do is I'm now going to look using my first derivative test to determine whether these are a max or a min. I'm going to look to the left and I'm going to look to the right of this. So if I were to plug in -1, right? So I'm going to go to this one, 4 times -1 squared, which would be +1. So 4 times 1, that's 4. -1 minus 3 is going to be -4. So 4 times -4 is going to give me -16. So this is going to be negative. If I were to plug in a value between 0 and 3, let's say we pick 1, I'm going to plug in 1. So 4 times 1 squared is going to be equal to 4. 1 minus 3 is going to be -2. So I have a positive times a negative. This is going to be negative. And then I'm going to plug in a value that is greater than 3. So if I plug in a positive value, square it, still positive, times 4, still positive. So this first term is positive. 4 minus 3 would be positive. So I have positive and positive. So that means to the right of 3, I have positive. So based on this, what's happening? Well, I have a negative slope, and then I have a point where it hits 0, and then I have a negative slope. But from at around 3, as I have my negative slope, I hit 3, and then I'm going to a positive slope, which means that x equals 3 is going to be a local minimum. Now, if we did this focusing on concavity, what we would need to do is let's actually do our second derivative test. So if I took my derivative here, I'm going to go back to this one, 4x cubed minus 12x squared. If I were to take my second derivative then, this would be, bring down the 3, this would be 12x squared minus 24x. So what I would need to do here is I need to figure out what is the concavity at my critical values to determine whether I am going concave up or I'm going concave down. So if I plug 0 into this, so y double prime at 0 is going to be 12 times 0 cubed minus 24 times 0 gives me 0. And you remember what we talked about? We talked about the fact that if you have a second derivative that's equal to 0, it means that it's inconclusive. Next, I'm going to plug in this value 3. So if I do y double prime at 3, this is going to be 12 times 3 squared minus 24 times 3, which is going to be 12 times 9 minus 24 times 3. It's going to be 3 times 1 is 2, then so 3 times that is 6, 70. So 72. 12 times 9 is going to be bigger than 72. This means I know that this is going to be a positive value, right? I actually don't care about the number. I only care about the concavity, meaning that we've just shown now with our second derivative test that at 3, it is concave up, agreeing that this is in fact a minimum. At 0, we have inconclusive, which does kind of work with what we have because based on our first derivative test, we had negative to negative, meaning that we couldn't really say using the second derivative test whether this was concave up or concave down. It was inconclusive. So based on what we've done so far, we know that we have a local minimum at x equals 3. But part of the problem also asked, where is it concave up? Where's our function concave down? Where are our inflection points? So what I'm actually going to do is I'm going to go to my second derivative. I'm going to rearrange it by pulling out 12x. So if I pull 12x out, so 12x squared, when I pull 12x out, I'm going to be left with x. And if I pull 12x out of minus 24x, I'm going to be left with minus 2. So what I'm going to do with this now is I'm going to treat this a lot like I would a first derivative test, but on my second derivative. So I'm looking at my rate of change. Is it going from positive to negative around the point where my second derivative is 0, or is it going from negative to positive? And that will help me determine where my inflection points might be. So I'm going to set each of these equal to 0. It's the same idea as doing a first derivative test on the function. We're doing a first derivative test on the second derivative. So in this case, we have 12x equals 0, so x equals 0. And we have x minus 2 is equal to 0, so x equals 2. So these are the 2 points now for my second derivative where I could be changing my concavity, where I'm going from either concave down or concave up. So we have x equals 0 and x equals 2. So what we're going to do, just like we did the first derivative test, we're going to look to the left, we're going to look to the right. So the first value I'm going to plug in, let's say I plug in -1. So looking at this 12x times x minus 2, if I were to plug in y double prime at -1, 12x, so 12 times -1 is going to be -12. -1 minus 2 is going to be -3. So this means I'm going to have a negative value times a negative value, which is going to give me a positive value. So I have a positive value to the left of 0. Then between 0 and 2, I'm going to plug in, let's say, +1. Same thing, 12 times 1 is going to give me a positive value. I don't care about the actual number, I just want to know the direction. 1 minus 2 is going to give me -1, which is going to be a negative value. So positive times a negative is going to give me a negative. So based on this test, what's happening at this point is the slope of our derivative is going from positive to negative. And then let's look at some value to the right of 2. Let's do 3. This is going to give me, if I plug in 3, 12 times 3 is 36, which is positive, times 3 minus 2 would give us +1, which is positive, meaning that to the right of 2, it is going to be positive. So this means if you consider our second derivative, this means that we have that our function is concave up from -infinity to 0, right? From -infinity to 0, it's concave up. And then from 0 to 2, this is going to be where it's concave down. And then it's going to go from negative to positive, which means, again, now it is concave up. So union 2 to infinity. This is where it's concave up and it's concave down. We already talked about the fact that our local minimum is at x equals 3. So this point would be 327. And the last thing is, where are our points of inflection? So our points of inflection in this case are actually going to be at 0. So let's actually think about what this behavior is telling us. Based on our first derivative, we had that it was a slope that was going negative, and at this point, it continued to go negative. But based on our second derivative, we're saying to the left, we have that it is positive, meaning it is kind of curving upward. So it's actually doing something like this. And then after we get to 0, now it's getting concave down, meaning it's going like this. So then based on this, what's happening is that we have a negative slope, but it's curving upward more. It's going to hit that 0, and now suddenly it's curving downward more. So that 0 is actually our point of inflection. And when we plugged in 0 into our original function, 0 minus 0 is going to give us 0. So our inflection point is going to be at 0, 0. Hello, everyone. In today's lesson, we're going to be going over L'Hopital's rule, which will allow us to compare the rates of growth between two functions. So before we do this, we first have to talk about indeterminate quotients. So imagine you're trying to find the behavior of a function, capital F of x, equals something like this, right? We have capital F of x equals the natural log of x divided by x minus 1. And if we were to try to see what this behavior would be at either 1 or infinity, so at 1 or infinity, what would happen with this? Well, if we plugged in 1, first thing that would happen is we'd get natural log of 1, which is equal to 0, divided by 1 minus 1, which is equal to 0, which would give us an indeterminate form of this quotient, right? We have an indeterminate quotient. Or if we were to plug in infinity, we would end up with infinity over infinity. And when we say we have an indeterminate quotient, this doesn't mean that we don't have a solution. It just means that based on what we have in front of us, we don't really know what it's doing, right? We don't know whether this is approaching infinity or whether this is approaching negative infinity, what is actually happening with it. So anytime we end up in the form either 0 over 0 or plus or minus infinity over infinity, this is called indeterminate. And this is something that needs to be true in order for us to use L'Hopital's rule. So in previous chapters, we did talk about some strategies that we could use in order to solve these sort of things, right? We had methods like dividing by whatever parameters in the bottom with the highest power, multiplying by the conjugate. But we're now going to look at a much better method. In fact, this is usually a lot of students' favorite section because it makes all those problems we did previously a lot easier to deal with. And also the fact that sometimes this can actually allow us to solve for things that aren't easily done with those other tricks that we talked about previously. So now let's talk about L'Hopital's rule. So suppose you have some f and g, which are differentiable, and the derivative of g at some point x is not equal to 0 near a. That's our point that we're near. Then if we take the limit as x approaches a, f of x over g of x equals 0, 0, or equals plus or minus infinity, then we can say that that limit as x approaches a, f of x over g of x is equal to the limit as x approaches a, the derivative of f of x over g of x. So this is to say that if we take our limit as x approaches some value a for our function f of x over g of x, as long as g of x, in this case g prime of x also is not equal to 0, if we were to try to solve this by plugging in our limit, and we get either 0, 0, so 0 over 0, or plus or minus infinity over infinity, then what we can actually do is we can say that this limit as x approaches a, f of x over g of x is equal to, then we take the limit as x approaches a, take the derivative of our top function divided by the derivative of our bottom function. And this is actually going to allow us to much more easily solve for this limit. And also later on, we'll actually see some patterns which will allow us to instantly know what the answer is going to be. So let's start with that example we first looked at. We have the limit as x approaches 1, natural log of x over x minus 1. So we're going to start with the limit as x approaches 1, natural log of x divided by x minus 1. And if we talked about, as we talked about earlier, if I plug in 1 into this, natural log of 1 is 0, 1 minus 1 is 0, so this is indeterminate. Which, if it's indeterminate, this means that we can use L'Hopital's rule. So by L'Hopital's rule, this means that this is going to be equal to the limit as x approaches 1, the derivative, so I'm just going to put d dx of the natural log of x divided by d dx of x minus 1. So if we were to take the derivative of natural log, if you remember, what does that give us? That will be the limit as x approaches 1. So the derivative with respect to natural log is going to be 1 over whatever's inside, so in this case 1 over x, divided by, and if we take the derivative of x minus 1, derivative of x is just going to be equal to 1, and the derivative of 1 is going to be 0 because it's constant. So we're left with 1 over x over 1, which, of course, by fractional division, right, because if you think of this 1 as 1 over 1, this 1 comes up to here, this 1 comes up to here, we're left with the limit as x approaches 1, 1 over x. And now if we were to evaluate our limit, we plug 1 in for the x, we get 1 over 1, or 1. For our second example, we're going to take the limit as x approaches infinity, e to the x over x squared. So the first thing we have to do is we first have to actually evaluate this limit, right? Because remember, we can only use L'Hopital's rule if it's indeterminate. So if I were to plug in infinity, I would get e to the infinity over infinity squared. Well, e to the infinity is just equal to infinity, and infinity squared is still infinity. So we get infinity over infinity, which is indeterminate. This means we can use L'Hopital's rule. So then let's do it. So what we're going to do is we're going to rewrite the problem. So a limit as x approaches infinity, e to the x over x squared. And then I'm going to take the derivative of the top function and the derivative of the bottom function. So this will be the limit as x approaches infinity, d dx, e to the x over d dx x squared. So now, evaluating this, right, keep our limit because we haven't evaluated yet, right? Our limit stays until we've done our evaluation. The derivative of e to the x with respect to x is just going to be e to the x. Using our power rule, the derivative of x squared is going to be 2x. Now, let's try plugging in our limit and see what we get. If I were to plug infinity into this, I would get e to the infinity, which is equal to infinity, divided by 2 times infinity, still infinity. It's still indeterminate. That means that what we can do now is just like before, we have this function over this function. We can do L'Hopital's rule again. So this is now going to be the limit as x approaches infinity, d dx e to the x over d dx 2x. Evaluating our first derivative, so we're going to take, right, bring our limit over, limit as x approaches infinity, d dx of e to the x is going to be e to the x, divided by the derivative of 2x is equal to 2, so this is going to be limit as x approaches infinity, e to the x divided by 2. Now, if I were to evaluate my limit, my e to the x, so e to the infinity, goes to infinity, divided by 2, which is just going to be infinity. For problem 3, we're going to look at the limit as x approaches infinity, natural log of x divided by the square root of x, which later on when we're actually evaluating it, we'll just set this as x to the 1/2, but for now we'll just see what happens if we evaluate our limit. If I plug in infinity into natural log, this is going to be equal to infinity. If I plug in infinity into the square root infinity, still infinity, this is indeterminate, meaning we can use L'Hopital's rule. So what we're going to do, again, we're going to set this up. So this will be the limit as x approaches infinity. I'm going to take the derivative of the top, so d dx, natural log of x, divided by d dx, x to the 1/2, right? Like I said, I just changed the square root into x to the 1/2. And now, bring over my limit. So limit as x approaches infinity. When I take the derivative of my natural log of x, this is going to be equal to 1 over x, divided by x to the 1/2 is going to be, using our power rule, 1/2 x to the negative 1/2. So now, looking at this, if I were to plug in my infinity, what happens? Well, first of all, let me actually just kind of rewrite this to make it a little bit easier to visualize. So to simplify this, I'm just actually going to rewrite this. So this is going to be the limit as x approaches infinity, and then I have 1 over x over 1 over 2, and then this x to the negative 1/2 is the same thing as saying x to the 1/2 up here. So this would be, actually, we'll just leave it here. We'll just leave it right here. X to the negative 1/2. Okay, so now using fractional division, this 2 comes up top. These x's go together, so we will have the limit as x approaches infinity, 2 over x times x to the negative 1/2. Now, the fact that I have two x values with different powers multiplied by each other means I would just add the powers. So x to the 1 minus 1/2 gives me x to the 1/2. So this is the limit as x approaches infinity, 2 over x to the 1/2. Or if you wanted to, you could write it as the square root of x. So 2 over the square root of x. And now if I were to evaluate my limit, what happens? Well, square root of infinity would be infinity. So this is going to be equal to 2 over infinity, which means that this is going to go to 0. For our fourth example, let's say that we have the limit as x approaches pi from the left, sine of x over 1 minus cosine of x. Again, if I were to plug in pi in this case, sine of pi, right, if we think about our sine and cosine waves, our sine wave starts at 0, goes up to 1, goes down to negative 1, goes back to 0, and this occurs at pi over 2. It goes to 0 at pi, goes to negative 1 at 3 pi over 2, and then of course it goes back to 0 at 2 pi. If I were to look at my cosine, it's going to start at 1, and then same idea, it's going to go down to 0, it's going to go to -1, and then back up to +1. So what is the values here? Same idea, right? So it's 0 at pi over 2. It is -1 at pi. It's 0 at 3 pi over 2. And it's back up to 1 at 2 pi. So if we were to plug these in now, right, following our sign, if we plug in pi, so we're going to start at 0, go up to 1, and at pi we have 0. If we were to plug in pi into our cosine, we get 1, it goes to 0, and then we get -1. So this bottom becomes 1 minus -1, which same thing as saying +1. So in this case, we get 0 over 2. Remember, we can only use L'Hopital's rule if we get an indeterminate form of 0 over 0, infinity over infinity, or negative infinity over infinity. So this is just our answer. The answer to this, when we evaluated it, is 0. There's no need to use L'Hopital's rule because when we evaluated our limit, we didn't get an indeterminate answer. So now let's talk about what is L'Hopital's rule actually doing. Well, L'Hopital's rule enables us to compare the rate of growth of our two functions. So suppose that you have 4 functions that we're interested in, right? So we have our x-axis, we have our y-axis, and we want to look at the functions. So we want to look at the functions, the limit as x approaches infinity, e to the x, the limit as x approaches infinity, x squared, the limit as x approaches infinity, square root of x, and the limit as x approaches infinity, natural log of x. Now, if I were to evaluate each of these individually, what is the limit as x goes to infinity on e to the x? Well, it's just going to be equal to infinity. If I take the limit as x goes to infinity for x squared, so infinity squared is just going to be infinity. If I take the limit as x goes to infinity, square root of x, the square root of infinity is still infinity. And if I take limit as x goes to infinity on the natural log of x, this would be natural log of infinity, which would just be infinity. So if I were to take any of these, right? So if I had e to the x over x squared, we already looked at that. It gave us infinity over infinity. If I did x squared over square root of x, we'd get infinity over infinity. If I were to take any quotient of these two, I would get an indeterminate answer. But if we actually look at what it looks like when we graph these, we're going to have something like this. So we have e to the x is going to look like this. So we have y equals e to the x, where it starts at 1 and then it increases very quickly. For our x squared, this is going to start at 0 and also increase very quickly, but not as quickly as our e to the x. So this is going to be y equals x squared. If we look at our square root of x, this is going to start at 0, and then it's going to very slowly grow. I know it looks like it went negative a little bit, but it does continue to increase. Y equals the square root of x. And then the last one, if we look at our natural log of x, this is going to start at 1, and then it is going to grow a lot like our square root of x, except for it's going to be less than, so this is going to be y equals natural log of x. So now looking at the rates that these grow, we can actually do a comparison, right? So if I have e to the x divided by x squared, e to the x is growing faster than the denominator, x squared, is shrinking this down to 0. If I had x squared over e to the x, because my denominator is getting bigger faster, that means it's going to go to 0. And it allows us to basically look at any fraction of these, and we'll be able to determine what happens as the limit goes to infinity, right? So for example, if we have the limit as x goes to infinity, like I said, e to the x over, pick any of them, right? Natural log of x. If I were to evaluate this at infinity, then we would have infinity over infinity, which is indeterminate. But if I look at this, my numerator is growing way faster than my denominator is growing. It's also growing, but it's growing slower, which means that this is growing faster than this is shrinking that fraction, meaning that this would go to infinity. If I were to flip it, on the other hand, and take the limit as x goes to infinity, natural log of x over e to the x, Well, again, now our natural log of x is growing towards infinity, but our e to the x is growing much faster, meaning the denominator in our fraction is growing significantly faster, meaning that this is going to get smaller and smaller and smaller, and it's going to approach 0. If we wanted to rank these as how fast they grow, well, e to the x is the fastest to grow. So this would be our fastest growth. X squared would be our second fastest growth. Square root of x would be our third fastest growth. And natural log of x would be our fourth fastest growth. And now it doesn't only have to be these functions, right? For example, if you see something like this, if you see an x cubed divided by an x squared, well, x cubed is going to grow faster as x approaches infinity. Or if you were going towards negative infinity, they would both go towards, in this case, negative infinity over positive infinity, but you still have to look at which one is growing faster. Now let's compare what the rate of growth is between some different functions. In this case, we're first going to look at the rate of change of natural log of x versus x. So if we were to compare these, let's say we take the limit as x goes to infinity, x over natural log of x. Well, if I were to just evaluate my limit, as x goes to infinity, I have infinity. As natural log of x, as x goes to infinity, I get infinity. This is indeterminate. So I don't know what the answer is. I don't know what's happening, right? Right now it just says that I can't evaluate in its current form. If we were looking at both of these, they are both growing to infinity. But which one is growing faster? The numerator, which would make this entire thing grow towards infinity, or the denominator, which would make the entire fraction get smaller, causing us to approach 0. So we're going to use L'Hopital's rule, and we're going to find out. So we'll take the limit as x approaches infinity, d dx x over d dx natural log of x. So carry over your limit as x approaches infinity. Derivative of x is just going to be equal to 1. The derivative of the natural log of x is going to be 1 over x, which again, just like you can think of this 1 as 1 over 1. Using fractional division, this comes here, this goes to here, which gives us the limit as x goes to infinity for x, or x over 1. And then if we were to evaluate this limit, we would get infinity, which means that our x is actually growing faster than our natural log of x, which makes sense, right? Because if you look at our graph here, what would x look like? It would be a 45-degree angle, and it would grow at a constant rate. Whereas in our natural log, while it might start a little bit higher, what's going to happen is that, or rather, no, it's not going to start. What's going to happen now is that as this grows, our natural log is also growing, but it's growing slower. What about if we were to evaluate the functions y equals x and e to the 0.1x? So if we did this, limit as x approaches infinity, x over e to the 0.1x. Again, if we were to evaluate this, right, we're going to get infinity over e to the 0.1 times infinity is still e to the infinity, which is just infinity. We get indeterminate. So now we're going to take L'Hopital's rule. So we get limit as x approaches infinity, d dx x over d dx e to the 0.1x. Evaluating our derivative of x, we're going to get 1. If we were to take the derivative with respect to x of e to the 0.1x, remember we're going to have to use the chain rule here. We first get e to the 0.1x, and then we have to take the derivative of the inside. So when I take the derivative of 0.1x, I get 0.1. So this is going to be times 0.1. So this means that we now have the limit as x approaches infinity, 1 over 0.1 e to the 0.1x. If we were to evaluate at this point, what happens? Well, there's no x in our numerator, meaning it just stays as 1. So we're going to get 0.1 times e to the 0.1 times infinity. Well, 0.1 times infinity is infinity, so e to the infinity. Infinity times 0.1, still infinity, which is going to give us 1 over infinity, which is equal to 0. Next, we're going to compare, as we take the limit as x approaches infinity, square root of x over e to the 0.1x. So as before, if we plugged in infinity, we'll get infinity over infinity. It's indeterminate. So now what we can do is we can take our L'Hopital's rule. So limit as x approaches infinity. So d dx, square root of x, which is just x to the 1/2, divided by d dx, e to the 0.1x. Now we just bring our limit over, limit as x approaches infinity. Remember, you always keep your limit until you actually evaluate it. X to the 1/2, using the power rule, we get that this is equal to 1 over 2 x to the negative 1/2 divided by, we already did this one in the last problem, so this is going to be 0.1 e to the 0.1x. And then I'm going to simplify this by bringing this negative power, right, because this is e to the negative 1/2, I'm going to bring that down to the denominator, and I'm going to turn it back to the square root, just so that we can kind of keep track of it. So we're going to have 1 over, right, so this is going to come into this term, so it's going to be 2 times 0.1, so it's going to be 0.2 e to the 0.1x, x to the 1/2. Oh wait, I said I was going to do a square root, so this is going to be square root of x. Now if I were to evaluate my limit, what happens? Well, the top is just going to be 1 because there's no x in it. If I plug in infinity into the square root of x, this is going to give me infinity. If I plug in infinity to the e to the 0.1x, this is going to be infinity. Infinity times infinity, still infinity. 0.2 times infinity, still infinity. So I would get 1 over infinity, which is equal to 0. What about if I have the limit as x approaches infinity, x over square root of x? So this is, of course, if I plug it in, infinity over infinity, it's indeterminate, so now I can use L'Hopital's rule. So I'm going to take the limit as x approaches infinity, d dx, x over d dx, x to the 1/2. This is going to be the limit as x approaches infinity. The derivative of x is going to be equal to 1. This is going to be 1/2 x to the negative 1/2, which again, the negative power is now going to take this to the top, and the 1 over 1, which if you think of 1, it's 1 over 1, divided by 1 over 2 means the 2 is also going to come to the top. This is going to be equal to the limit as x approaches infinity, 2x to the 1/2 power. Evaluating my limit, this is going to give me 2 times infinity, which is just going to be equal to infinity, which in this case means that x is growing faster than the square root of x. And then finally, let's do one more, and this is going to be the limit as x approaches infinity, square root of x over natural log of x. Now, looking at our graph, we can already see what's going to happen, right? Is that our square root of x is growing faster than our natural log of x. But if we wanted to show it using L'Hopital's rule, we first try to evaluate infinity over infinity. It's indeterminate. We can use L'Hopital's rule. This is going to be the limit as x approaches infinity, d dx, x to the 1/2, divided by d dx, natural log of x. So this x to the 1/2, derivative of x to the 1/2 becomes 1/2 x to the negative 1/2, divided by natural log of x. When we take the derivative of that, we get 1 over x. So as before, right, we could think of this as x to the negative 1/2 over 2, which means it can come to the bottom. So we have 1 over 2 x to the 1/2 divided by 1 divided by x. Using fractional division, this x is going to come to the top. This 1 is going to go to the bottom term. We are going to get the limit as x approaches infinity, x over 2x to the 1/2 power. So then using fractional division, right, because I can think of this top term as x to the negative 1/2 over 2 over 1 over x. The x is going to come to the top, so we're going to have x to the negative 1/2 times x, which is going to be x to the 1 minus 1/2, so x to the 1/2. So this is going to be equal to the limit as x approaches infinity. By the way, in case anyone wants to see what I'm talking about, I'm just going to quickly rewrite this part. So this 1 over 2 x to the negative 1/2, you could think of it as x to the negative 1/2 over 2 divided by 1 divided by x. Using fractional division, right, you're going to multiply by the reciprocal, which means you're going to take this bottom term, you're going to flip it, and you're going to multiply, which means that you're going to multiply this x at the bottom by this top term. You're going to multiply this 1 by this 2. So this is going to end up giving you x to the negative 1 over 2 times x, which is, you can think of as x to the 1, divided by 2. When you have these two x's multiplied, so the negative 1/2 plus 1 is going to give you positive 1/2. So this is just going to be x to the 1/2 divided by 2. So that's where the term came from that I was saying. So we have the limit as x goes to infinity, square root of x over 2, which is going to be equal to infinity over 2 or infinity. So now that we've done all these, we should be able to actually kind of compare how fast they're all growing, right? Because we had that e to the 0.1x was growing faster than any of our other terms that we looked at. X was the second fastest growing of those we looked at. The third fastest was the square root of x, and then the slowest growing function to infinity was the natural log of x. So using our L'Hopital's rule, we were able to compare these growths. And once you understand how these growths are manifesting, you can actually kind of just look at them and instantly know the answer, right? So if I looked at this, I know that square root of x is growing faster than natural log of x, which means my numerator is going to go faster. This is going to infinity. In this case, I know that x is growing faster than the square root of x, so this is going to infinity. In this case, I know that e to the 0.1x is growing faster than square root of x. I know this is going to 0. And I don't actually have to do all the actual calculations to show it, because I understand from that what the rates of growth are when comparing them. Now, sometimes you're not always going to know which function is growing faster, and that's where you use L'Hopital's rule. But there are some patterns that you will notice which do make solving these problems a lot easier, especially if you have the same variable, for example, x, but to different powers. So let's say we had something like this. The limit as x approaches infinity, 4x cubed minus 3x squared plus 2x minus 1 over 2x squared minus 14x plus 12. Something like this. If I were to plug in infinity for this, I would get x cubed is infinity, so 4 times infinity is still infinity. We have infinity squared is infinity, times 3 is still infinity, so infinity minus infinity plus infinity. So this one actually does cause us some issues because we can't really say what's happening if we're subtracting infinity from infinity. So this would still be indeterminate. So let's say that we actually use L'Hopital's rule. What's going to happen? Well, I'm going to take the derivative of the top, so I'm going to have my limit as x approaches infinity. I'm going to bring the 3 down, so this is going to be 12x squared minus, bring the 2 down, this is going to be 6x plus 2, the negative 1 is going to go away, divided by, now take the derivative of the bottom, to bring the 2 down, 4x minus 14. Now again, if I were to plug in infinity, I still would get something indeterminate, so I'm going to do L'Hopital's rule again. I'm going to take the derivative of the top and the bottom. So if I take the derivative of the top, bring the 2 down, this is going to be 24x minus 6 divided by 4. And now if I were to evaluate this, as I plug infinity, I'm going to get infinity over 4, which in this case is just going to be infinity. What about if I had flipped these, right? Let's say I had something of this form. I have the limit as x approaches infinity, 4x squared plus stuff over 14x cubed. Well, in this case, it doesn't matter what's happening, because if you actually look at when we took this derivative for the first one, what happened? The only thing that mattered were these first terms, because as I took the derivative, this term went away, and then this term went away, and then this term went away, and I was only left with the terms that were the highest powers of x. So because my numerator had a higher power of x, it went to infinity. When I have something like this, if I were to take L'Hopital's rule, the power would go down by 1. So I'd end up with the limit as x goes to infinity, bring down the 2, this is going to be 8x divided by, plus whatever other stuff is still there, if there's anything. Bring down the 4, whatever 14 times 4 is, I'm not even worried about the number, x cubed. And then, of course, if I were to do L'Hopital's rule again, then this would be the limit as x goes to infinity. This x is going to go away. I'm going to be left with 8 over whatever this is, 14 times 4 times 3x squared, whatever that value is. When I plug in my infinity, all this stuff doesn't really matter because it's times infinity. So this is going to be 8 over infinity or 0. So if you have x in the top and the bottom, and you have your largest powers, if the highest power is in the numerator, it goes to infinity, or negative infinity if there's negatives in front of things. If it is in the denominator, then the denominator grows faster and it goes to 0. If they are the same power, for example, if I had something like this, limit as x goes to infinity, I'm just going to make up some values. 4x to the 14th minus 12x squared to the 12th power plus, I don't know, 11x to the 8th power plus 2x minus 1. And this one I'm going to do something like, I don't know, 7x to the 14th power plus 2. It doesn't matter what it is. What's going to happen is because none of these terms that aren't the highest power are going to have any impact on this as we take the derivative, right? We might have to do the derivative in this case 14 times, but what's going to happen is all these terms over time will get every time, right? The power goes down by 1 when you're using power rule. So these are all eventually going to cancel out. This is going to cancel out, and I'm only going to be left with these two terms. So as I do my derivative and these x terms go away, I'm going to be left with a ratio of 4 over 7. So this would be equal to 4/7. So if you ever have limit as x goes to infinity, some fraction of this over that, whatever your highest power of x is, if the numerator is the highest, it goes to infinity. If the denominator is the highest, it goes to 0. And if the two highest powers, the top and the bottom, are the same, it converges on whatever value is the fraction between those two. So in this case, it was 4 in the numerator over 7 in the denominator, so we get 4/7. So hopefully that kind of helps you understand why this can be so useful, because if we see how the rates of growth are compared to each other, then we can much more easily solve this. But this is what I was kind of talking about. I could have something like this, the limit is x goes to infinity, with 1,000 terms. As long as I know what the highest powers are, knowing L'Hopital's rule, I can instantly tell you whether it goes to infinity, 0, or converges on some value. Hello everyone. In the last lesson, we looked at a lot of students' favorite section, which was L'Hopital's rule, because it makes something we've done previously a lot simpler. Now we're going to move into what's kind of more one of the dreaded topics that we cover, which is optimization problem. So first, before we actually look at how to do an optimization problem, let's look at the steps we would use to solve an optimization problem. So the first step is you need to understand the problem. And this is one of the things that makes it so difficult, is because sometimes you might not really understand how to set up the initial conditions for your problem. One thing you might be able to do is then step 2 would be, if you can, draw a visual, right? So if you have something like a fence surrounding a field, or you have some tower and there's a ship off in the distance, you need to figure something out, then in this case, draw a picture. It'll sometimes help you understand what you're trying to solve. Third, introduce the variables representing your unknown factors. Step 4, write an equation that represents the quantity to be optimized and an equation relating the other variables together. Step 5 is we're going to use substitution to rewrite the equation of the quantity to be optimized as an equation in just terms of one variable, right? So if I have x and y, then I would want to solve either x or y in terms of the other, and then plug that back into what I want to optimize, which will allow me to figure out what are the possible values. Step 6, we then need to find the domain of the equation, and we need to figure out what are our possible critical values. Because if you remember when we were doing maximization and minimization, our critical values could either be where the derivative is equal to 0, where the derivative does not exist, or if we have a bounded problem, the boundaries of that problem. And then step 7, optimize by finding the min or the maximum value using the closed interval method, and then either your first derivative test or your second derivative test, whichever one you prefer. Let's start by looking at a simple example. Find the two positive numbers whose product is 16 and whose sum is minimum. So we have two things we want to look at. We have the fact that we have two positive numbers, meaning that they can only be greater than 0, and their product is 16. So what I'm going to do is I'm going to take two numbers, x and y, and I'm going to say that x times y is equal to 16. So that's our first condition. But that's not the one we want to optimize. The one we want to optimize is if we were to add these up, we want this to be minimum. So let's call this one S for whatever the sum is. So we have some sum, which is equal to x plus y. And this is what we want to optimize. In this case, we want to minimize it. So this is the one that we want to minimize. So now what we need to do is let's first look at this x times y equals 16. In order to actually minimize or maximize your optimization problem, you need to have this in terms of one variable. So we can either solve for x or we can solve for y. So I'm just going to pick x in this case because it doesn't really matter. So if I were to now solve this for x, I'm going to divide both sides by y. I'm going to get that x is equal to 16 over y. And now that I have this value of x, I can plug this in and replace this, and now I'll have my s only in terms of y. So that means my s is now going to be equal to 16 over y plus y. Now, to make this a little bit easier to take the derivative of, we could do it in this form, right? I could take this as y to the negative 1, and I could use 16 y to the negative 1, take the derivative of that, take the derivative of y. But what I'm going to do is I'm just going to put it all together as one term. So first thing I'm going to do is I'm going to get it all in terms of having the same denominator. So this will be 16 over y plus, if I wanted to get y in the bottom, I would need to multiply this by y over y. So this is going to be y squared over y. And now they both are in terms of a denominator of y, so I can combine them together, and I have 16 plus y squared over y. Okay, so now what I want to do is I actually want to optimize this. Now remember, to find our minimum or maximum, we need to first take the derivative. So we're going to take the derivative of s. So we have s prime is equal to, now if we look at this, 16 plus y squared over y, this is going to be using our quotient rule, where this is our f, this is our g. Now if you remember, our quotient rule was gf prime minus fg prime over g squared. So in this case, we leave our g alone, which is going to be y times the derivative of our f term. So derivative of 16 is going to be equal to 0 because it's constant. Derivative of y squared is going to be 2y. So it's going to be y times 2y minus. Now we leave our f alone, which is going to be 16 plus y squared times. We take the derivative of our bottom term. So derivative of y is just going to be equal to 1. And then we divide the entire thing by our g term squared, so y squared. So now if I were to combine all these terms together, I'm going to get that, so I'm going to distribute this y, so we get 2y times y, which is going to be 2y squared minus 16 plus, minus, right, because I got to distribute the negative, minus y squared over y squared. Simplifying this a little bit more, 2y squared minus y squared is going to leave me with y squared. So y squared minus 16 over y squared. So now that I have this derivative, how do I figure out what my critical values are? Well, my critical values are where either f prime of x, in this case, is equal to 0, f prime of x does not exist, or at our boundaries. So where would this, in this case, s prime, not exist? Well, it would not exist when y is equal to 0. But if you remember from our original part of the problem, we had that x and y are positive values, meaning that y already cannot be equal to 0. So that's not actually one of our options. So that means that there's nowhere where our derivative does not exist. So the next thing we're going to look at is we're going to look at where does this equal to 0. So if we were to set this equal to 0, right? So if we have y squared minus 16 over y squared equals 0, anytime you're doing something like this, you really only care about the denominator or the numerator. And this is because if I multiply both sides by y squared, the y squareds will cancel on the left. 0 times y squared is still equal to 0. Really all we're looking at is y squared minus 16 equals 0, right? Because it only matters we get the numerator equal to 0. It only matters if the denominator, if whatever we do in the numerator also causes that to be to 0, because then we'd have indeterminate. So y of y squared minus 16 equals 0. So I'm going to add 16 to both sides. And I'm going to get y squared equals 16. And then if I were to take the square root of both sides, I get that y is equal to plus or minus 4. Now, if you remember, our x and y can only be positive, which means that the only possible value is y is equal to 4. So now let's test out if we were to have y equals to 4. Let's go back to our original relationship between x and y. X times y equals 16. I'm going to plug my 4 in, so I'm going to get x times 4 equals 16, divide both sides by 4, and I'm going to get x equals 4. So this means that if I were to use y equals 4, that means x has to be 4, which means my s is going to be, s is equal to 4 plus 4 equals, 8. But we're not done yet, because remember, we also have to check our boundary conditions. So we had that the product of x and y is 16. So if we think about what is the biggest or smallest values we can plug in, well, the biggest and smallest values we can plug in would be 1 and 16, right? Because 1 times 16 would give us 16, and 16 times 1 would give us 16. So let's say that we say x is equal to 1 and y is equal to 16. If we did that, we would get s is equal to 16 plus 1 equals 17. And then if we were to do it the other way, let's say that y is equal to 1 and x is equal to 16, we would get s is equal to 1 plus 16 is equal to 17. So both of these are bigger than our s equals 8, which means that this is in fact the values of x and y, x is equal to 4, y is equal to 4, that minimizes this. For our second example, we have a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a river with a straight bank. He needs no fencing along the river bank. What are the dimensions of the field that have the largest area? So pretty much what we're kind of saying is this, right? We're going to draw that picture. So let's say you've got your riverbank, and we know that he wants to put some fencing around his rectangular field, and he has a total of 2,400 feet of fencing. So we need to figure out what is the maximum amount of area that he can get for this field using the amount of fencing that he has. So the first thing we're going to look at is, well, how do we find this area? Well, the area is just going to be the width times the length. So I'm going to call this side length. I'm going to call this width. So if we were to look at the area, it would be just length times width, or width times length, however you want to say it. Now, let's look at the relationship between this width and this length. We said that he has 2,400 feet of fencing. So in this case, how do we figure out how much fencing we're using? Well, we have a width, a length, and another width. So it's going to be length plus 2 width. And now we can actually start to begin to solve our problem. Now remember, what we're trying to do is we're trying to maximize this area right here. So we want to maximize the area of the field. So first thing I'm going to do is I'm going to solve this for either L or W. I'm going to do L, so I'm going to subtract 2W. So I'm going to get 2,400 minus 2W equals L. I'm going to take this L and I'm going to plug it in here. And now this area becomes, so the area of this field is going to be equal to 2,400 minus 2 width times width, right? Because all I did was I took what this L was equal to, plugged that in place of L, and now this is what I'm trying to optimize. I want to maximize this. So first thing I'm going to do, I'm going to distribute this W, and I'm going to get that this is equal to 2,400 W minus 2W squared. Now, the way that we maximize it is we take the derivative, right? We take the derivative, we find our critical values, where either our derivative is equal to 0, our derivative does not exist, and then we also look at our boundaries. So in this case, when I take my derivative, A prime, 2,400W, if I take it with respect to the width in this case, this is going to be 2,400 minus 4W. So first things first, is there anywhere that this does not exist? Well, no, because this is a polynomial, which means that there's no value, there's no real number that I can plug in that makes this not exist. So that's not one of our options. So next what we're going to do is we're going to see if we can find a maximum or minimum point by setting this equal to 0. So if I have 2,400 minus 4w equals 0, then what I'm going to do now is I'm going to add 2400. So it's going to be minus 4w, or sorry, subtract 2400 equals minus 2400. Divide by negative 4. So I'm going to get w equals to positive 600. So that means that the width, if this is our minimum or maximum, in this case maximum, is 600, we can then plug this width back in to our relationship between length and width, and we can figure out what our length would have to be. So in this case, it would be 2400 equals length plus 2 times my width. Well, my width in this case is 600. So I would have 2400 equals L plus 1200. Subtract 1200 from both sides, I get that L is equal to 1200. So this is one of our possible candidates for the largest area. But we also have to check our boundary conditions. Well, our boundary conditions, right, if we think about what is the maximum amount of length that could be on one part, either length or width, I could have a length of 2400, which would give me a width of 0. Or I could have a width of 2400 and a length of 0. If I were to plug these into my area, I would get 2400 times 0, which is equal to an area of 0, right? Because it's just a straight fence. It doesn't actually surround anything. Or I could do 0 times 2400, which again is going to be 0, because again, it's just, instead of the length, it would be the width is all of the fence. So this would be where my area of my field is maximized. It is when my width is equal to 600 and my length is equal to 1200. Now you may have wondered, why am I keeping so focused on this side? It's because I wanted to show you that we could actually do the exact same problem, but instead of solving for L, we could solve for W and we'll get the same exact answer. So first things first, let's write down our original conditions. A equals length times width, and we had 2400 equals length plus 2W. Now last time what I did is I solved for L, but this time what I'm going to do is I'm going to solve this for W. So I'm going to subtract L, so I'm going to get 2400 minus L is equal to 2W. I'm going to divide by 2, so I'm going to get 2400 minus L divided by 2 equals W. Taking this W, I'm going to plug this into, so plugging my W into my area now becomes L times 2400 minus L over 2. If I were to then distribute this L, this is going to be 2400 L minus L squared all over 2, which I'm actually going to just change it a little bit, just to make it a little bit simpler. I'm going to change this to over 2, and this is over 2. And the reason I want to do this is because now my area is going to be 1200 L minus L squared over 2. So the next step, like we talked about previously, if I want to maximize this, I need to take my derivative. So when I take my derivative, A prime, this is going to be equal to, so the derivative of 1200L is just going to be 1200 minus the derivative of L squared over 2. So I'm going to bring down my 2 to get 2 over 2, so that's going to go away. So it's going to be 1200 minus L. So I have the derivative is equal to 1200 minus L. The critical values are where either this derivative does not exist, where it's equal to 0, and then of course our boundary conditions. So in this case, this is a polynomial, meaning that I can plug any real number in and I will get a response out. So this is fine. So it does not exist, it's not one of our options. So next we're going to set this equal to 0. So we get 1200 minus L is equal to 0. I'm going to add L to both sides, and I'm going to get 1200 equals L, which if you look at what we did previously, agrees with what we got, and it would follow through the same steps. We'll then take this L, we'll plug it back into this 2400 equals L plus 2W. So 2400 equals L plus 2W. We're going to plug in that 1200, so that means this 2400 is equal to 1200 plus 2W. I'll subtract 1200, so this would give me 1200 equals 2W, which means W equals 600. So you can see that when we did this, we got the exact same thing. The other thing I wanted to mention, though, is you could instead do the second derivative test, right? Because the second derivative test will tell us whether we have a minimum or a maximum when you plug in the value where your derivative is equal to 0 and see whether it is positive, which means it's concave up, or it's negative, which means it's concave down. So let's just try that just to see what happens. So if I take the derivative of this, so we get my second derivative, 1200, that goes away. I have minus L, which gives me a second derivative of minus 1. So in this case, if I were to plug in any value, if I were to plug in where this is equal to 0, which in this case was 1200, then this would be negative, which means that it is facing downward. So that means it's a maximum. So for our second derivative test, this also agrees that this is a maximum. You would then have to compare with your boundaries, which we did previously, and you would see that it in fact is the same. The last thing I actually wanted to mention is when I did this part, I rewrote it so that I could do a little bit of cancellation and then just use the power rule for both of them. You could have taken the derivative when you were at this step, right? If I had rewritten this as 2400L minus L squared over 2, I could use the quotient rule. If I had something like this, this one would be pretty easy because it's a 2, so one of the derivatives is going to be 0. But this would be f, this would be g. When you do your quotient rule, it would be g f prime minus f g prime over g squared. So in this case, if I were to take my derivative, a prime, I would get 2 times the derivative of this top term, which would be 2400 minus 2L, minus, and then we leave our f alone, so that'd be the 2400 L minus L squared times the derivative of g. So the derivative of a constant is 0. So this is going to be times 0, so this term is going to go away, divided by 2 squared, which is going to be 4. 2 over 4, this cancels down to 2400 minus 2L over 2. I can then cancel this 2 with both of these terms. So I'll be left with 1200 minus L, which you see is exactly what we got here. In this case, you could then set it equal to 0, solve for it. So there's a lot of different ways you can do this. And this is where some of the confusion can lie. Because first you have to be able to figure out what are your initial conditions that set your two variables equal to something or some relationship between them. What is it that you're trying to minimize or maximize? Then you have to figure out your boundary conditions. You have to figure out the derivative. There's different ways you can find the derivative. And then also which variable are you solving for? In this case, length or width. And then from there, once you figure out what the possible lengths and width are, you then figure out which of those either maximizes or minimizes based on what you're interested in. And then last, you figure out what the other value would be, and you check your boundary conditions in your original function to see is it bigger or smaller, compare, and then that will give you your final answer. And last thing, if you're curious what the actual area would be, right, if we just plug these in, area equals 600 times 1200, you would get that this equals 720,000. So we'd have 720,000 square feet is what the maximized area would be for this problem. Suppose you have a box with a square base and an open top, and it must have a volume of 62,500 centimeters cubed. We want to find the dimensions of the box that minimize the amount of material used. So in this case, what we're saying is that we have a box which has a square base, meaning that these sides will all be the same, but we don't have the same restriction on the other parts of the box. And what we have, though, our restriction that we do have for the box is that it must be a volume of 62,500 centimeters cubed. So first things first, let's set up our relationship. If we think about the base here, right, if we wanted to figure out what's the area of this base, it would be, let's call it base. So base times base, because it said that it has a square base, meaning that the two lengths are the same. And then we have the height of our box. If we wanted to get the volume of this box, it would be, if you think about base times width times height, well, in this case, base and width are the exact same thing. So it's base times height. So that means that we have 62,500, and then if you want to keep the units, centimeters cubed. is equal to base squared times height, or height times base squared, whatever you want to call it. The other relationship that we need to have, though, is we're trying to minimize what? Well, we're trying to minimize the actual material used. So if we were to think about flattening out this box, right? So let's say that we took these four sides and we kind of spread them out. We would have our square base, and then we have the four parts, which do not have to be a square, right? They can be rectangular. So let's say it looks something like this. And we're trying to figure out what height and base size would cause us to use the least amount of material while still maintaining that the volume of this open box is 62,500 centimeters cubed. So in this case, this means that if we were to actually figure out what the area of this is, well, the area of our base is going to be base times base. And the area of each of these, right, because they all have that one base part, it's going to be base times height. And there's four of these. So that means that this is going to be, so the area of this one is going to be base squared. The area of each of these is going to be base times height, and there's four of them, so it's going to be 4 base times height. So that means that the total area that I'm using is 4 base times height plus base squared. So now let's go back to our relationship between our base and height. We have that 62,500 centimeters cubed is base squared times height. So I need to solve for one of these, either base or height. I'm going to do height just because that way I don't have to take a square root. Because you could do it, right? You could solve for base by dividing by h, take the square root, knowing that because this is an area, it only counts the positive length because you can't have a negative length for the length of the base of a box. But I'm going to do it for h, which means that I'm going to divide both sides by b squared, and I'm going to get h is equal to 62,500 divided by b squared. I'm then going to take this h, I'm going to plug this in to my relationship that I'm trying to, between base times height, that I'm trying to minimize in this case, right? This is what we want to minimize. So this is going to become 4 base times 62,500. I'm actually going to write these bases as capital B's just so we don't confuse them with sixes. Because I will 100% do that as we get halfway through this problem. So we have 62,500 divided by base plus base squared. Yeah, and then I added my square here because whenever I was changing them to capital B's, I forgot to put my square there. Okay, so now what I'm going to do is one of these bases is going to cancel with this base, and then I'm going to get 4 times 62,500, which is equal to 250,000. And then I have a base in the bottom, so I'm just going to write this as b to the negative 1 plus base squared. The next step is we want to now take the derivative of our area of our box, the thing we're trying to minimize, with respect to whatever variable we have. In this case, it's our base. So if I were to take the derivative of 250,000 b to the negative 1, right, power rule, I'm going to bring the negative 1 down. So this is going to become negative 250,000. This goes to negative 2, so base to the negative 2. And then plus, I do my power rule, this is going to become 2 times base. So if I were to now rewrite this back into our original form, this is going to give us negative 250,000 divided by base squared plus 2 base. Now, we need to figure out what our critical values are, right? Now that we have our derivative. Well, it could be where this does not exist. It could be where our derivative is equal to 0. And of course, we have to look at our boundary conditions. Well, in this case, does not exist. The only place this would not exist is when we have b is equal to 0, right? A base of 0, because this would be negative 250,000 divided by 0, which would be not possible. But if you look back at our original problem, because we're talking about the area of a box, we can't have a 0 base, because if we have 0 base, that means we can't have a base of the box, which means that we can't have a volume, which is equal to 62,500. So realistically, we do have a condition, which is the fact that our base and height have to be greater than 0. So that means that there is nowhere that this does not exist. So now what I'm going to do is I'm going to set this equal to 0. So I have negative 250,000 divided by base squared plus 2 base equals to 0. I'm going to bring over this negative 250,000 over base squared. So I'm going to get 2 times base is equal to 250,000 divided by base squared. And then what I'm going to do is I'm going to multiply both sides by base squared. So I'm going to divide the 2. So I'm going to get base cubed equals 125,000. If I were to then take the cube root of both sides, right? So I take the cube root of this side. I take the cube root of this side. I'm going to get that our base is equal to 50. So if I were to then take this base of 50, go back to my original relationship of what 62,500 equals base squared plus h, this means that I would have 62,500 equals 50 squared times height. From there, I would then get this. So 50 squared is going to be 2,500. And then I would divide this. So I'd divide both sides by the 2,500. And then I would get whatever my height is. And then from that, I would then be able to tell you what is the minimum area for this problem. Right? And then from there, it's just a matter of you check your boundary conditions, you compare them what you have. Well, in this case, we have to have that our base is greater than 0. But the only real boundary we have is that the base and height together have to give you an area of 62,500. So in this case, I would actually use the second derivative test to determine is this a minimum or a maximum. So let's do that real quick. If I have my derivative is negative 250,000 over b squared plus 2b, if I were to take my second derivative, a double prime, I'm going to take the derivative of negative 250,000 b to the negative 2. So I'm going to bring down the negative 2. So this is going to be 500,000 b to the negative 3. And then plus 2b, which is just going to be plus 2. If I were to plug in this 50, right? So I'm going to have 500,000 times 50 cubed plus 2, then this would tell me that I'm going from, but this would give me a positive value, right? Because this is going to be way bigger than, well, it's going to be positive. Because, right, if I think of it this way, let's actually redo it. Let's do 500,000 divided by 50 cubed plus 2. It doesn't matter what this is equal to. 500,000 divided by 50 to any power, even if it goes really small, it's still going to be positive. Plus 2, still positive. So I know that this is going to be positive. Using my second derivative test, I know that this is, in fact, a minimum. If we want to do our first derivative test, what we would do, right, we would look at the fact that at 50, if we look at our derivative, look to the left of it, look to the right of it, determine if it's positive or negative, then we can determine whether we are going from decreasing to increasing or increasing to decreasing. In this case, if I were to plug in a value to the left of it, it is going to be negative. If I plug a value to the right of it, it is going to be positive. So by our first derivative test, we would have that it's going from negative to positive slope, which again would say that we have a minimum. So this is in fact going to be the base, which would then plug into this to give us our height, which would minimize this problem. Hello everyone. In today's lesson, we're going to be going over antiderivatives. For an antiderivative, a function capital F is called an antiderivative of lowercase f on an interval I if capital F prime x equals f of x for all x in that interval I. So that is to say that if f of x is some function, the antiderivative, if you were to take the derivative of that antiderivative, would go back to that function. So if capital F is an antiderivative of lowercase f on an interval I, then the most general antiderivative of lowercase f on that interval I is capital F of x plus c, where c is just some arbitrary constant. And this is because if we took something like 4x squared plus 2, 4x squared, and 4x squared minus 46, if we were to take the derivative of this first term, we would get that this is equal to 8x. If we took the derivative of the second one, we also would get 8x. And if we took the derivative of this third one, we would also get 8x. So when we take the antiderivative, because when we took the derivative, we might lose any information about some constant, our general form of our antiderivative is just that once we find the antiderivative, we add some arbitrary constant c to represent this possible value, in this case 2, 0, or negative 46. So here we can see some of the most common antiderivatives that we're going to encounter. And what I want you to do is I want you to think about what function, if I took the derivative of it, would give me my current outcome. And that would be the antiderivative for whatever undoes the derivative. So for example, for the first one, we have that if we have c f of x, the antiderivative of this is going to be c f of x. So that is to say that if I have some constant times something with, like, let's say x, let's say cx, then when I take the derivative, it'll be, when I take the antiderivative, it will be the antiderivative of that x times the constant c. So whenever I have some constant times my function, when I take the antiderivative, it would just be the constant times the antiderivative. Similarly, if I have two functions added or subtracted to each other, so f of x plus or minus g of x, when I take the antiderivative of this, it's going to be the antiderivative of f of x plus or minus the antiderivative of g of x, just like we had previously with our limits and our derivatives. If I have two different functions added or subtracted, when I take the antiderivative, it's the same as the antiderivative of the first term plus or minus the antiderivative of the second term. For my third common antiderivative, if I have x to the nth power, where n is not equal to 1, then when I take the antiderivative, this is going to be x to the n plus 1 divided by n plus 1. And this is just basically the antiderivative undoing what we would do if we did a power rule. So let's say, for example, we had this x plus n plus 1 divided by n plus 1. Well, if I were to then to take the derivative of this, so I go d dx of this function, what would happen with this? Well, using our power rule, I would bring down this n plus 1, and then I would have x to the n plus 1 minus 1 divided by n plus 1. The n plus 1s would cancel, and the 1 minus 1 would cancel, and I would be left with x to the n. So this is the inverse of our power rule. So when we take our derivative, we do the power rule. If we were to take the antiderivative of it, we would take whatever x we have, take the power up by 1, and then divide by n plus 1. Now you might wonder, why can n not be equal to negative 1? Well, it has to do with the fact that if we were to do this antiderivative when we have n equals negative 1, what we would get is x to the negative 1 plus 1, which would be to the 0, divided by 1 minus 1 plus 1, which would be x to the 0, so 1, divided by 0. So in this case, we can't divide by 0, so n cannot be equal to negative 1. For our next common antiderivative, we have that if we have some constant c, when we take the antiderivative, this is going to be equal to cx. Now the reasoning for this is, let's say that we have this c. You can think of this c as c times x to the 0 power. And using our power rule that we just talked about, what's going to happen when we take the antiderivative of this? Well, this x to the 0, the power is going to increase by 1. And then, of course, we'll divide by that power, so divided by 1. And then based on our first rule, if I take the antiderivative of some function f of x, and it's times some constant c, it's just the antiderivative times c. So we have c x to the 1, which is just x, so cx, and then divided by 1, that doesn't change anything. So this is really just the idea of doing the power rule, but where you have a 0 power for your function. And then also our constant rule. So the next one we have is if we have 1 over x, this is going to be, the antiderivative of this will be natural log of the absolute value of x. And this is because, again, if we think about having this natural log of x, if we take the derivative, so d dx of a natural log of x, this will just give us 1 over x. So you might wonder, why does it have to be the absolute value? And it's because if you think about the shape of a natural log, it's going to look something like this, meaning that we cannot get a negative value. So for example, if I have 1 over a negative value, then I would not be able to take the natural log of that negative value, so I would have to do something else with it. Our next rule is going to be, if we have e to the x, the antiderivative of this will be e to the x, which this should make intuitive sense, right? Because if we have e to the x and we take the derivative of it, then we just get out e to the x. So if we take the antiderivative of it, we also get e to the x. What about if we have e to the constant times x? Well, what this is going to be is this is going to be 1 over c e to the cx. And this is because, again, just like our power rule, using our chain rule, if we were to take the derivative of this, right, we would take e to the cx, and then we would take the derivative of the inside, which would be, so the derivative of c times x would just be c. So then to counter that c, when we do the chain rule, we would have 1 over c, right? So if I had 1 over c e to the cx, and I took the derivative of this, so d dx, this 1 over c is constant, so I can pull that out. Taking the derivative of e to the cx, this is going to be equal to 1 over c e to the cx times, chain rule inside, so c, this 1 over c will cancel with this c, and I'll just be left with e to the c times x. The next one, we have cosine of x. If I take the antiderivative of cosine of x, the way I want you to think about this one is, if I took the derivative of something, what would give me cosine x? And this is going to be positive sine of x, right? If I took the derivative of sine of x, I get cosine x. Similarly, if I want sine of x, the antiderivative is going to be negative cosine of x. Now, why is that? Well, it's because if I have positive cosine of x, when I take the derivative, I get negative sine of x. So if I take the derivative of negative cosine of x, it'll give me negative sine of x, which would be positive sine of x. Number 10, we have secant square of x. The antiderivative of this will be tangent of x. Number 11, if we have secant of x times the tangent of x, this is just going to be equal to secant of x. And then finally, if we have 1 over 1 plus x squared, the antiderivative of this is just going to be the inverse tangent of x. Now these last three, again, just think about the fact that if I have tangent of x, if I take the derivative of it, I would get secant squared of x. If I have secant of x, if I take the derivative of it, I would get secant x times tangent of x. And if I have the inverse tangent of x, and I take the derivative of that, I would get 1 over 1 plus x squared. So the antiderivative is just undoing that derivative to get back to this original term. And this is a lot of times how you can think of an antiderivative. What function, if I took the derivative, would give me what I currently have? Or if you have the original function, then you just kind of do the same idea. You say, okay, well, what function am I trying to get that if I took the derivative of that would get me back to the function that I currently have? Okay, so let's do some examples now. Suppose that we have the function f of x equals sine of x. And I want to know what I take the derivative of. I want to get the antiderivative that gives me this function. So this means that if I'm at sine of x, what function would I have where if I took the derivative of it would give me sine of x? And we talked about the fact that this is going to be negative cosine of x plus, you have to remember to add your constant c, right? Because our original function could be something like this cosine, when we took the derivative of it, could be negative cosine plus 12 or negative cosine minus 14. So when we take the derivative of this, what would we get? Okay, well, if I take the derivative of cosine, I get negative sine. But I have a negative in front, so negative sine gives me positive cosine, or sorry, positive sine. Plus, if I took the derivative of some constant, that constant would go to 0, which would leave me with sine of x. What about if I have a derivative function? G prime of x is equal to 1 over x. Then if I wanted to find out what is the original function g of x, I would take the antiderivative of this. Of course, looking at our list of options, the antiderivative for 1 over x is going to be the absolute value of natural log of x, plus, again, our constant c. We always have to have that constant because while it might be 0, there could be some constant that if you took the derivative of this, you would eliminate whenever you took the derivative. And of course, in this example, though, we do have one restriction. X cannot be equal to 0. And why is that? Well, it's because if I were to take the derivative of this x, I would get 1 over x as my answer, which would be 1 over 0. And again, this has to do with the fact that if we look at the behavior of natural log of x, as we approach 0, it's going towards negative infinity. It never actually gets to 0. So therefore, if we have our natural log and we were to take the derivative, our x cannot be equal to 0. What about if we have the derivative function f prime of x is equal to x to the nth power, where again, n cannot be equal to negative 1. Well, based on our rule we talked about, we're going to use our power rule, so not even looking at the rule. We have f prime of x, and then what we're going to do is we're going to take this x to the n, and we're going to add 1 to it. And then we're going to divide by whatever power we have now, so n plus 1. And then, of course, as always, plus some constant c. What about if we have h prime of x is equal to 4 sine of x plus 2x to the 5th power minus the square root of x divided by x. Now this might look kind of complicated, but we can actually rearrange this to get it in terms of all of the antiderivatives that we've talked about. Now to solve for this, we can directly solve for 4 sine of x, right? We have rules to solve that. But we don't have a way to directly find the antiderivative of 2x to the 5th minus the square root of x divided by x. But what we can do is the square root of x we can treat as x to the 1/2 power. And this x that's dividing this fraction is going to be x to the negative 1. So this will be 4 sine of x plus 2x to the 5th minus x to the 1/2 times x to the negative 1. And then I'm going to distribute this x to the negative 1, because again, I still can't find the antiderivative of this term in its current state. So the first term will stay the same, 4 sine of x. So then we have 2x to the 5th times x to the negative 1. Now remember, whenever you have two x's and you're multiplying them by each other, you just add the powers. So we have x to the 5th minus 1, or plus 2x to the 4th power, minus. Now, x to the 1/2 minus 1, so 1/2 minus 1 would give us x to the negative 1/2. Now, we can actually take the antiderivative of this entire function. Now, if you remember, when we have f of x plus or minus g of x, when we take the antiderivative, it's the same thing as the antiderivative of f of x plus or minus the antiderivative of g of x. So we'd have f of x, g of x, and maybe like h of x. So then taking the antiderivative of this, I'm going to write this as h of x. This is going to be equal to the 4, the constant, we can pull outside, right? Constant, if we have constant times function, when we take the antiderivative, constant times the antiderivative. So what function would give us sine of x? And this would be negative cosine of x. Plus, now, again, we can pull the 2 out as our constant, and we have x to the 4th. So we're going to take our power up by 1, so x to the 5th, and then we're going to divide by that power, so divided by 5. And then minus, we have x to the 1/2, so we're going to take the power up by 1, so negative 1/2 plus 1 would give us positive 1/2, and then we divide by the power, so we divide by 1/2. Now, if you divide by a fraction, 1/2, it's the same as multiplying by 2. And then, of course, cleaning this up, our final answer will be negative 4 cosine of x plus 2/5 x to the 5th minus 2x to the 1/2 power plus c, right? Because you always have to remember to add that arbitrary constant. So if we were now to take the derivative of this, when we take the derivative of cosine, we get negative sine. Negative sine would give us 4 sine. So we got our 4 sine of x. If we were to take the power rule for 2/5 x to the 5th, we would bring down the 5, so the 5's cancel, and then this become x to the 4th. So we'd have 2x to the 4th, which would be right there. which if we brought down the 1/2 would be 2 over 2. Those would cancel, and we'd have -1 in the power, so x to the negative 1/2, which would bring us back to what we had here. And then, of course, we took the derivative of the constant. That would go to 0, and we would be left with exactly what we had for our original term. For our next example, we want to solve the initial value problem. We want to find f, including what c is, if we have f prime of x is equal to e to the x plus 20 times 1 plus x squared to the negative 1, and we have f of 0 equals 2. So first thing we're going to do, we're going to focus on this function, and we're going to take our antiderivative. So if we take our antiderivative of f prime, this would just be f of x, right? Because if I had f of x, took the derivative, I would get f prime of x. Now let's take our antiderivative. So our antiderivative of e to the x is just going to be e to the x. Now, to take the antiderivative of 20 times 1 plus x squared to the negative 1, I first actually need to rearrange this a little bit. So what I'm going to do is I'm going to treat this as 20 times this negative 1 power is the same thing as saying 1 over this. So 1 over 1 plus x squared. Now, if we look at our antiderivative, common antiderivatives that we looked at, 1 over 1 plus x squared is just going to mean that this is equal to the inverse tangent. And the inverse tangent times some constant is just going to be the inverse tangent times that constant. So we have that this is equal to plus 20 inverse tangent of x. And the last thing is we need to now add our arbitrary constant c. Okay, so now that we have our antiderivative, we have some arbitrary constant c. But an initial value problem means we actually want to know what is the value of this c. And this is where that f of 0 equals 2 comes in. So if we were to then evaluate f of x, where x equals 0, we would have e to the 0 plus 20 inverse tangent of 0 plus c. And we have this entire thing is equal to 2. Now, solving for this, when we take e to the 0, this is going to be equal to 1. When we take inverse tangent of 0, this is just going to be equal to 0. And then our plus c, and this is equal to 2. So we have 1 plus 20 times 0, so this term is 0, plus c is equal to 2. So 1 plus c equals 2, which means that c equals to 1. And now we have our c, we can take this c and we can plug it back into our antiderivative, so our function that we found, and we end up with f of x equals e to the x plus 20 inverse tangent of x plus 1. And this would be our final answer with the actual original constant that our function would have if we took the derivative to get this function here. And then for our last example, we actually have the second derivative. So we have f double prime of x equals 12x squared plus 6x minus 4. And we have two initial value statements. They are, on our original function, f of 0, we have 4, and our function f of 1 equals to 1. So the first thing we need to do, we're going to take the antiderivative of our second derivative. And by the way, so this is one thing I want you to think about, is whenever you're taking an antiderivative and you're undoing a derivative, it's kind of like this. If I have some function, f of x, if I were to take the derivative, so let's say d dx, and go this way, this would go to f prime of x. If I were to take the derivative of the first derivative, I would get the second derivative. If I were to take the derivative of the second derivative, I get the third derivative, so on and so forth. The antiderivative just goes the other direction. So basically what this is saying is that if I have the second derivative and I take the antiderivative, I'll get the first derivative. If I take the antiderivative of the first derivative, I get the original function. And then I could take this further. I could continue on to, f of x, and I could continue this in either direction. And if you wanted to kind of think of this in terms of like a more real world example, think of position. So we have some function, which is position. You're sitting in a car, and where are you located in space? If you have some starting point 0, are you forward some amount, let's say 2 miles, or are you backward some amount, let's say 2 miles? If we took the derivative position, which is the change in position, another way we talk about change in position is speed or velocity. So it's how fast are you moving? So between points, A and B, if you're moving, how fast are you moving? That's our derivative. If we take the derivative of speed or velocity, so the change in velocity is acceleration. Are you speeding up or slowing down? So if I'm going forward and I'm speeding up, right, I have a positive second derivative, positive first derivative. If I'm going forward but slowing down, I have a positive first derivative, a negative second derivative. Going backwards and I'm speeding up in the backwards direction, I have a negative first derivative, negative second derivative. If I'm going backwards but I'm slowing down in the negative direction, meaning I'm getting more forward, means I have a negative first derivative, a positive second derivative. And I can actually go between these by using derivatives and now antiderivatives. So if my position function, I can figure out at any given point what is the instantaneous rate of change, meaning how fast am I going at any given point. I could also find, by taking the derivative of the velocity, how much am I accelerating or decelerating at any given point. Likewise, if I have the acceleration function, I could take the antiderivative to get the velocity, and I could take the antiderivative of that to get to the position at any given point. So in this case, because I have a second derivative, I'm going to take my antiderivative, so this would just be f prime of x, and this is going to be, so I'm going to take my power up by 1, so this will be x cubed, and then I'm going to divide by this new power, divided by 3, plus 6 times x, so I have x to the 1, so this becomes x squared, and I divide by 2. And then finally I have minus 4, and remember, if we have some constant, this just becomes the constant times x, so minus 4x. And then I have to also account for that arbitrary constant, that if I had taken the derivative of this first derivative, this arbitrary constant would go away. And now, just to clean this up really quick, 12 divided by 3, this is going to be 4x cubed plus 6 divided by 2, so 3x squared minus 4x plus c. Next thing I'm going to do is I'm going to take the antiderivative of f prime of x, giving me f of x, and I'm going to do the same thing. So this x cubed goes to x to the 4th power. So I have this 4, and then I bring this power down, so I have 4 over 4, plus, same thing here, x, this power goes up by 1, so squared goes to cubed. I divide by 3, so then I get 3 over 3, minus 4 times x to the 1, this goes up to x squared, and then I bring down that power, that 2. Plus, now I have cx, right, because I have a constant. Antiderivative makes it c times x. Now I have some new constant that could have been eliminated when I took the derivative of this, and I'm going to call this one d. So now we need to focus on our initial values. We have f of 0 equals 4, and we have f of 1 equals 1. So the first thing I'm going to do is I'm going to evaluate this function at 0. So f of 0 is equal to, right, so let's just actually clean this up real quick. This is equal to x to the 4th plus x cubed minus 2x squared plus cx plus d. So now if I plug 0 into this, I would get 0 to the 4th power plus 0 cubed minus 2 times 0 squared plus c times 0 plus d, and we have f of 0 is equal to 4. This term goes to 0, this term goes to 0, negative 2 times 0, this term goes to 0, c times 0, this term goes to 0, and I have d equals 4. So now I'm going to plug that back into my original function. So this now means that our function, f of x, is equal to x to the 4th power plus x cubed minus 2x squared plus cx plus 4. Now I'm going to use my second initial value, f of 1, and again, I'm going to solve this, and this will allow me to solve for c. So if I plug 1 into my function now that I know what d is, this is going to be 1 to the 4th power plus 1 cubed minus 2 times 1 squared plus c times 1 plus 4, and this is equal to 1. So plugging this in, 1 to the 4th power is 1, 1 cubed is 1, minus 2 times 1 squared is 1, so this becomes minus 2, plus 1 times c, so plus c, plus 4 equals 1. 1 plus 1 is 2, 2 minus 2, these are going to cancel with each other. We're going to get c plus 4 equals 1. So then solving for c, we subtract 4 from both sides, we get c equals negative 3. And now that we know what c is, we can go and plug this back in for our c, and we will have our final function with both the c and the d constants. So So our final answer for our function is f of x equals x to the fourth power plus x cubed minus 2x squared plus, now we plug our c in, so this would be minus 3. So plus negative 3 is the same thing as saying minus 3 x plus 4. And this will give us our final answer based on our initial values, which allowed us to solve for C and D. Hello everyone. In today's lesson, we're going to start looking at the foundational ideas behind integrals, which will allow us to find areas and distances. So first, let's talk about the area problem. Finding the area of polygons isn't difficult because generally we have some formula we can use. For example, if we have a rectangle, we would just do length times width. If we have a triangle, we would do 1/2 times base times width. If we have some other shape, we generally can figure out, based on some formula, how to find that area. But if we were trying to find the area under a curve, this can be more challenging. For example, if we had something like this, where we have some curve, and we wanted to know what is the area between 2 points under the curve. And this is where it kind of gets a little bit more difficult. And this is where we're going to introduce Riemann sums. So to estimate the area under a curve, we're going to use Riemann sums, which use strips to subdivide an area under the curve into rectangles, and then this will allow us to approximate the area under the curve. So looking at this, for example, what we might do is something like this. We might say, let's split this into 4 sub areas, and they're supposed to be the same width, but because of my drawing. And then we'll have a couple of choices here. We can either look at left endpoints, right endpoints, or midpoints. So if I were doing left endpoints, it would look something like this. For this first interval, I would take this, I would go up to the curve, and then I would create a rectangle for this interval. And then for this interval, using the left endpoint, I would go up to the curve, and I would create another rectangle. For this one, same thing. I'm going to create another rectangle. And then for this last one, and then just pretend they're all the same size. And then from this, I could figure out what is the area of this rectangle using length times width. What's the area of this rectangle? What's the area of this rectangle? What's the area of this rectangle? And from that, I will be able to get an approximate value. Now, of course, this isn't going to be exact because, one, you can see that this doesn't perfectly fit the graph. And I'm going to have this area here where I'm overcounting based on the fact that I decided to use left-hand endpoints. Whereas if I had used right-hand endpoints, my rectangle for the first one would have been here, my second one would have been here, and in this case, each of these would have undercounted by some amount. So you can kind of see that our decision, whether we use right endpoints, left endpoints, or midpoints, can actually determine whether we're overcounting or undercounting in our approximate value, depending on the shape of the curve. So let's look at some examples. We're going to use Riemann sums with 4 subintervals on right endpoints to estimate the area under the curve f of x equals x squared. So we'll start with our function, f of x equals x squared, and we're going to be on the interval from 0 to 1. So we'll put that we're from 0 to 1. So if we were to graph this, what does this look like? Well, for x squared, we're going to start at our origin, and we're going to grow exponentially like this. So we start at 0. Let's say that 1 is right here. So we want to split this into 4 subintervals, which means that we're going to have something like this, a mark here, a mark here, and a mark here, giving us 4 subintervals. And then we want to use right endpoints. So in this case, we will start at for our first interval, which is going to be this one. We're going to go to our right endpoint of that interval. We're going to go up to the curve, and that will be where we draw our rectangle. For the second interval, we're going to go to our right endpoint, and we're going to create our rectangle. Go to our right endpoint, create a rectangle, and go to our right endpoint and create our rectangle. And this will give us, again, our approximate value for the area under this curve. Whereas with this one, we will be overcounting though, because, as I said earlier, this one, because we're using right-hand endpoints, is going to have parts of the rectangle that are above the curve. Now, looking at the slide, you can see here that on our first graph, we actually show the curve, and this is the area we're looking for. We know that our area under this curve has to be between 0 and 1, because if we have that this is 1 in the x value, and if we take 1 squared, right, going back to our original function, we know that this would be to 1, giving us a square of 1 by 1, meaning we have an area of 1. So this means that our area is going to be somewhere between 0 and 1. So when we divide this into our 4 strips, we then can figure out what is the interval, the width of each of these rectangles. Well, the fact that I'm going from 0 to 1, right? If I look at the fact that this is 1/4 of it, this is 1/4 that interval, this is 1/4, and this is 1/4, this means that our change in x is going to be equal to 1/4. So that means that if I start at 0, then this endpoint is going to be 1/4. This one is going to be 2/4. This one is going to be 3/4. And then the last one will be 4/4 or 1. So whenever we actually want to find this area now, all we're going to do is if I take 1/4 and I plug it into this x squared, I'll have 1/4 squared, which will give me an area of my base, which is going to be 1/4, times the height, which I said is going to be 1/4 squared, plus, for the second interval, I'm going to have a width of 1/4, and I'm going to have a height of, if I plug 2/4 into x squared. So this will be 1/4 times 2/4 squared. Plus, the next interval, we're going to have a width of, again, 1/4, and this one we're going to plug 3/4 into our x squared. And then finally, for our last interval, we're going to have a width of 1/4, and we're going to plug in 4/4 or 1 squared. Now, if you actually look, each of these terms has 1/4 in front of it, so we can actually pull that out. So this area is actually going to be 1/4 times 1/4 squared plus 2/4 squared, which is, 1/2 squared, plus 3/4 squared plus 1 squared. So now let's figure out what is the approximate area under this curve. So when I take 1/4 and I square it, that's the same thing as, right, if I have something like this, a over b squared, this is the same thing as saying a squared over b squared. So this is going to be 1 squared over 4 squared. So this will be 1/4, 1/16, plus, again, this term here is 1/2. So again, 1/2, I'm going to square the 2. This is going to become plus 1/4, plus this one, I'm going to square the top term. It's going to be 9 divided by, and then 4 is going to be 16. And then plus 1 squared is going to be 1. And now I can actually solve this. 1/16 plus 1/4 plus 9/16 plus 1, all divided by 1/4, and this will give us an approximate area for under this curve. So let me just plug that in, and we'll see what we get. So 1 divided by 4 times 1/16 plus 1 divided by 4 plus 9 divided by 16 plus 1. And I get a value of 0.4685. Looking at our slide, you can see what we did here. This is actually called our Riemann sum. So we're going to use Riemann sums with 4 subintervals and right endpoints to estimate the area under f of x equals x squared from 0 to 1. So this estimate we will call R4 to represent the 4 subintervals, and we're using right endpoints. And first thing we're going to look at is what are our subintervals. We started at 0, we went to 1/4, so 0 to 1/4, then 1/4 to 2/4, then 2/4 to 3/4, and 3/4 to 1. That gives us our 4 intervals. Because we're doing right endpoints, we used the 1/4, 1/2, 3/4, and 1. If we were using left endpoints, we would use the left endpoint of each of these intervals, 0, 1/4, 1/2, and 3/4. If we decide to do midpoints, it would be one extra step where we'd have to actually figure out what is the midpoint between these 2 points. So for the first one, the midpoint between 0 and 1/4 would be 1/4 plus 0 divided by 2, which would be 1/8. The second one would be between 1/4 and 2/4, which would give us 2/8, 3/8, so on, or something like that. And then from there, we take each of those interval points that we have, plug them into our original function, in this case x squared, and that will give us our height, right? Because what we're doing when we're looking at the height is we're saying at our right endpoint, if we go up to the graph, this is the height at that point, and then we just make a rectangle out of it. Once you've done that, you take the width times height for each rectangle, you add all those up together, so when you sum those up, you will get an approximate area under the curve. So now let's do the same thing, but this time let's use our left endpoints. So we want to figure out what is our left endpoint by subdividing x squared into 4 subsections. So the first thing I'm going to do is I'm going to write down what are my intervals. So if I start at 0, right, so my first one is going to start at 0, I'm going to go up by 1/4, because the way we figure this out is delta x is just going to be your endpoint b, which is going to be your upper boundary, minus your lower boundary, which will be a, divided by n, the number of subdivisions you're using when you're doing your Riemann sum. So in our case, our change in x is going to be 1 minus 0 divided by 4, which would give us that 1/4 that we found when we first were looking at the problem. So again, so we start at 0, we go up by 1/4. Our second interval, we start at 1/4, we go up by another 1/4. So this would be, I'm just going to write it as 2, well, I'll do it as 1/2. I'll do 2/4. For our next interval, we're going to start at 2/4. We're going to go up to 3/4. And then for our last interval, we're going to go from 3/4 to 1 for 4/4. I'll just leave it as 4/4, just keep it consistent for now. Now, because we're using left endpoints this time, we're going to be using this endpoint, this one, and this one, which means we're going to be looking for our heights, which will be based on f0, f1/4, f2/4, which of course is 1/2, and f3/4. And then once we figure out each of these heights, we know that they're all going to have the same width of 1/4. So that means when we're actually looking for this, we can go L4 equals 1/4 times, and then we just plug in 0 into x squared. So we get 0 squared plus 1/4 squared plus 2/4 squared, or 1/2 squared, plus 3/4 squared. And then simplifying this, this will be 1/4. 0 doesn't have, 0 squared is still 0. So 1/4 is going to be 1/16 plus 1/2 squared is going to be 1/4 plus 9/16. And if we plug this in, let's see what our Riemann sum tells us the area under this curve is. So we have 1 divided by 4 times 1/16 plus 1/4 plus 9/16. And we get a total of 0.21875. So based on what we've done, we now have our left hand endpoints using Riemann sum with 4 subintervals. We have an area under the curve of 0.21875. Using our right hand endpoints, we have an area of 0.46875. So you can see that right now there's some pretty big discrepancy between the two. And this is mostly because if you look at the curve we're doing, one of them will always be overcounting. That is our right-hand endpoints. But one of them will always be undercounting, because if we look at our left-hand endpoints, this is what we found. We found this rectangle, which was 0. We found this rectangle, which undercounts. We found this rectangle, which undercounts. And we found this rectangle, which undercounts. So one solution we might use is we might do the same thing, but instead of using the left-hand endpoint or the right-hand endpoint, maybe we use the midpoint. So if we're going to use the midpoint, let's say we do that here. So we have midpoint with 4 subintervals. Our delta x is still going to be the same. So when we do our heights, it's going to be the midpoint of this first interval, the midpoint of this second interval, the midpoint of this third interval, and this midpoint of our fourth interval. So between 0 and 1/4, if I take 0 plus 1/4 is 1/4 divided by 2, this is going to give me 1/8. So for our heights, we're going to be using f of 1/8. Then for 1/4 to 2/4, right? So if we add these together, this is going to be 3/4 divided by 2, which is going to be 3/8. So we're going to take f of 3/8. For 2/4 to 3/4, that's going to be 5/4 divided by 2 is going to be 5/8. And then for our last one, 3/4 plus 4/4 is going to be 7/4, and then we're going to divide that by 2, which will give us f of 7/8. So just like before, when we want to find our M4, this is going to be the width times 1/8 squared plus 3/8 squared plus 5/8 squared plus 7/8 squared. And then I'm actually going to bring this down here real quick, and we're going to solve for what this is equal to. So M4 is going to be equal to, just give me a second, I'll plug that in, and I'll be right back. Okay, so now I've done this, and I got that this would be 21/64, or about 0.328125. So now based on this, you can see that this gives us a value that's in between, because now for this one, what we did is we used the midpoint, meaning that for our first interval, we went to our midpoint, we went up to that point, and we created our rectangle right here. So we overcounted a little bit on the left, we undercounted a little bit on the right. For our second interval, we start here, we go to the midpoint, we create this rectangle. For this one, we go to our midpoint, we create this rectangle, and for this one, we go to our midpoint, and we create this rectangle. So you can see that because this is an upward curve, one of them is going to overcount, one of them will undercount, and the other one will a little bit of over and undercount, which kind of balances out a little bit. If you have something that is going downward, you're actually going to get the opposite case of this. So for example, if I had something that was going down, if I did right-hand endpoints, I would be undercounting. Whereas if I had something that was downward and I was doing left-hand endpoints, I would overcount. So you can't always think of it as something like right-hand endpoints always overcount or anything like that. It depends on the actual curve, which is why I said for a simple curve like this, one will always overcount, one will always undercount. But if you have something more complex with more curves, more parts of the curve to it, then you might have some parts where it's overcounting with the right, but undercounting with the right, things like that. So based on the example we just did, we had that our area was somewhere between 0.21875 and 0.4685. What if instead of doing 4 subintervals though, we did 8 subintervals? Well, in this case, because we're splitting them into smaller and smaller subintervals, what's happening? So now instead of having 4, right, 1, 2, 3, 4, we're now saying, what if I split it into 8 subintervals? So now if I were to do this, it would get even less that is being over or undercounted. So if we were to do 8 subintervals, then we would have that the area is somewhere between 0.273475 and 0.3984375. What if we were to do 50 subintervals? Well, in this case, if we did our left-hand endpoint, we would get 0.3328335, and our right-hand endpoint would get 0.3338335. So you can see that what's happening is as we get more and more and more and more subintervals, our value that's undercounting and our value that's overcounting are getting closer and closer and closer together. So then this is going to be the idea of our integration, is we're going to say, well, what would happen is if we took these Riemann rectangles, these for our Riemann sum, so what if we took these rectangles and we started to make more and more and more rectangles until we approach an infinite number of rectangles? So instead of having a ton of, a bunch of smaller rectangles, which get her closer and closer, we're going to say, what if I just had an infinite number of rectangles that were infinitesimally small for their width? This would give me the actual area under the curve that we're looking for. For example, for our A, if you actually look at the pattern, right, we're getting closer and closer and closer. We're converging on the value of 0.333 repeating, or 1/3. And this would occur as your right-hand Riemann sum and your left-hand Riemann sum approach infinity. So how do we actually find the exact area under the curve? Well, in order to find the exact area under the curve, we need to either find our ln or rn as n goes to infinity. And then at this point, our ln, which would be our left-hand endpoint Riemann sum, and our rn, right-hand endpoint of Riemann sum, would be equal to each other. So let n be the number of rectangles in our interval from a to b, and this is, of course, our interval. And then the width of our interval, which we talked about earlier, is delta x equals b minus a divided by n. So you go your lower bound of your lower endpoint, your upper endpoint. So you have these two boundaries. And then if I want to know how big the width is between all the subintervals, I just take this width of this boundaries and then, or this interval, and then I just divide it by how many subintervals I will have. And then this will let us have our intervals. We're going to start at that lower bound, a, and then we're going to go up to x1. This is going to be based on delta x. And then we're going to go from x1, and we're going to go up another delta x to x2. Then we're going to start at x2. We're going to go up another delta x to x3 to x4, and you're going to do this until you get all the way to xn minus 1, so the second to last point, and then you end at your upper bound, b. So in this case, our x sub I is going to be equal to a, your starting point, plus I, your index, times the delta x, the change in x. Meaning that if I start at some endpoint that's not 0, right, you would start, okay, let's say I'm starting at 2. You'd say, okay, starting at 2, I'm going to go plus, let's say I'm on the 5th subinterval. Then it'd be 5 times whatever the width of each subinterval is. So what way we're going to find our limit, though, is we're going to use, so the area is going to be equal to the limit as n approaches infinity, Rn, or of course Ln, because again, as n goes to infinity, they will converge to the same value. So what this really kind of translates to is we're going to take the limit as n approaches infinity, and it's going to be delta x, because delta x will be the same for every interval, and it's going to be the function at x sub I, whether in this case it'd be right-hand endpoint, but whether it be left-hand endpoint, midpoint, whatever you're using, plus delta x, f of x sub, sorry, this should have been sub 1, this should have been sub 2, plus delta x, f of x 3, plus dot, 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 plus delta x, f of x sub n. And then basically all we have to do is we have to figure out, as our n gets bigger and bigger and bigger, what happens to our width? Well, it's going to get smaller and smaller and smaller. And then we're just going to sum up all these and we'll get the actual area under the curve. So then rewriting this, what we're actually going to have is that our area is going to be equal to the limit as n approaches infinity, the sum as I goes from 1 to n, delta x, f of x sub I, where our delta x, being that it's a constant, right? So if we take the sum of a constant times a function, right, we can actually pull that constant out. So realistically, what we're actually going to be finding is we're going to be finding the limit as n approaches infinity, delta x, sum I equals 1 to n, f of x sub I, right? And that's what we did previously, right? We have delta x times fx1, delta x times fx2, delta x times fx3. Well, all these have delta x, then we pull that out, it becomes f of x1 plus f of x2 plus f of x3, which is this part here, the sum of our f of x terms, where we start with the index 1, that's f of x1, we go to 2, that's f of x2, go to 3, f of x3, until you get all the way through every single one, ending at f of xn. So for this problem now, what we want to do is we want to show when we have y equals x squared on the interval 0 to 1, we want to show that it is actually going to be exactly equal to 1/3. And we're going to use the right-hand limit. So we're going to show our limit as n approaches infinity, r sub n. And we want to show that this is equal to 1/3. So the way we're going to do this is, first things first, actually before we start, I actually need to do one quick little note, because we're going to need it for this problem. So note, if you have 1 squared plus 2 squared plus 3 squared plus dot 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 up to n squared, this is going to be equal to n times n plus 1 times 2n plus 1 divided by 6. And this will actually allow us to figure out that this is equal to 1/3. And I'll show you in a second how this works out. Okay, so what we're going to do is we're going to use the fact that we want this area. Our area is just going to be equal to the limit as n approaches infinity, sum as I equals 1 to n, delta x, f of x sub I. So in order to do this, we first need to know what delta x is. Then we need to figure out what our f of x sub i's are. So what we're going to do is we're going to figure out what is our delta x. This is going to be our width. So we want our width delta x, which if you remember is b minus a over n. Well, in this case, b is going to be our upper bound of our boundaries. So this is going to be 1 minus a, our lower value of our boundaries, 0, divided by n. So this means that every interval will have a width of 1 over n. And then if we wanted to figure out what our actual intervals are, what we're going to do is we're going to start at our a value, which if you look at our interval, our a is 0. So our first interval is going to be from 0 to, then you go from 0 plus whatever our delta x is, so plus 1 over n. So this is going to be 1 over n. And then we're going to go from 1 over n to 2 over n. Then we're going to go from 2 over n to 3 over n. And then we're going to continue to do this until we get to our last interval. Now, a lot of times what you're going to want to do is it's actually easier to figure out what is the final value, which in this case, because it's equal to 1, is going to be equal to n over n. Just keep it consistent with everything being over n. So this point is going to be 1 over n less than this n over n, which means we're going to have n minus 1 over n, right? So if you kind of look at the pattern, 0 over n, 1, 2, 3, 4. So basically whatever this is, if let's say this is like, if we were, let's say n was 20, this would be 20 minus 1 or 19 over n. So now because we're actually trying to find our limit using our right-hand endpoints, that means that these are the values that we're going to be using. 1 over n, 2 over n, 3 over n, so on and so forth up to n over n. So our right-hand endpoints will be 1 over n, 2 over n, 3 over n, up to n over n. This means that if we want to get our heights, these are the values that we actually need to find. We're going to have the function, which in this case is x squared, of 1 over n. Not plus. For our second value, it's going to be our function of 2 over n. For our third value, it's going to be the function of 3 over n. And then you're going to do this all the way until you get to our final function, f of n over n. Now, when we're doing this, we're not actually going to be calculating these individual functions, because if you remember what's happening with our n as we do this problem, well, we're taking n as it goes to infinity. So there's going to be an infinite number of these functions. So we're going to start by setting up our problem. We have right here that the area is the limit as n approaches infinity, the sum I equals 1 to n, delta x, f of x sub I. So first things first, our delta x. We know that our delta x is equal to 1 over n. So I'm going to plug that in. So I have the limit as n approaches infinity, the sum I equals 1 to n, 1 over n. And now I need to consider what is my function for x sub I. So our x values based on some index is going to be x sub I, whatever index it is, right? The first one, the second one, the third one, up to the nth one, over n. So this is going to be x sub I over n. And then if we actually look what our function is doing with this, though, it's going to square it. So if you're wondering how I got this, think about this for a second. If my index is 1, this would be x sub I, which is the first value, over n. So 1 over n. If index was 2, it'd be the second value, so it'd be 2 over n, and then we're going to square each of those. Okay, so now let's actually start to kind of work out what this would look like. So this is going to be equal to the limit as n approaches infinity. I'm going to take the sum of this, so this is going to end up being 1 over n times If we look at our first one, it's going to be 1 over n squared plus 1 over n, that's our width, times 2 over n squared plus 1 over n times 3 over n squared plus, and then of course we would keep doing this until we got to 1 over n over n squared. Now, this is where our pattern is going to come into play. But first things first, just like last time when we were solving this for a smaller interval, each of these has a 1 over n in it. So we're going to pull that out. So this is going to become the limit as n approaches infinity, 1 over n times 1 over n squared plus 2 over n squared plus 3 over n squared plus dot 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 up to n over n squared. So you actually might be starting to see what we're going to be doing here, because now if we look at each of these, if we were to actually take these squares, right, so 1 over n becomes 1 squared over n squared. So we take the limit as n approaches infinity, 1 over n, and then this is going to be 1, I'm going to actually put as 1 squared over n squared, plus this one become 2 squared over n squared plus 3 squared over n squared plus dot 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 plus n squared over n squared. Every single one of these terms is divided by n squared, right? 1 squared over n squared, 2 squared over n squared, 3 squared over n squared, so on and so forth. So I'm actually going to pull this 1 over n squared out. So we're going to have 1 over n times 1 over n squared, which would give us 1 over n cubed. So this is going to be the limit as n approaches infinity, 1 over n cubed times 1 squared plus 2 squared plus 3 squared plus dot 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 up to n squared. So looking at this, we have 1 squared plus 2 squared plus 3 squared plus up to n squared, which looking at our note we had earlier is going to be equal to n times n plus 1 times 2n plus 1 over 6. So I'm going to substitute that in. This is going to become the limit as n approaches infinity, and then so I'm going to have 1 over n cubed times n plus 1 times 2n plus 1 divided by 6. So the next step I'm going to do is I'm going to take this n cubed and I'm going to bring this into this term here, and I'm also going to distribute these terms together. So if I were to actually do this, right, so if I have n, this is going to become n squared plus n. So I have n squared plus n times 2n plus 1, and I'm going to then FOIL this out. So I get first, outer, inner, last. So this is going to give me, let's bring this over here. This is going to be equal to the limit as n approaches infinity. I'm going to have my 6n cubed underneath. So when I take my first terms, n squared times 2n is going to give me 2n squared. Cubed, sorry, 2n cubed. Then I'm going to do my outer terms, which are going to be n squared times 1, so plus n squared, plus, now I'm going to do my inner terms, n times 2n, which is going to be plus 2n squared, and then plus, we're going to get n times 1, which is going to be n. So this n squared and this 2n squared are just going to combine together to give me 3n squared. Now, in order to solve this, what I'm going to do next is I'm actually going to divide everything by n cubed. So this is going to be the limit as n approaches infinity, 2n cubed divided by n cubed. Plus, we got our 3n squared, so 3n squared divided by n cubed plus n divided by n cubed, and this is all divided by 6n cubed divided by n cubed. So this n cubed is going to cancel with this n cubed, give us 1. This n squared is going to cancel with 2 of these n cubes. This n is going to cancel with 1 of these n cubed, leaving us n squared. And then these n cubes are going to cancel. So this is going to leave us with the limit as n approaches infinity, 2 plus 3 over n plus 1 over n squared divided by 6. Now let's evaluate our limit. If I take the limit as n goes to infinity, what happens with that 2? Well, it has no n, so it doesn't change, so it stays 2. What happens with 3 over n? Well, it becomes 3 over infinity, which means that this term goes to 0. 1 over n squared, again, this becomes 1 over infinity, this goes to 0. So we're going to be left with 2 over 6, which is equal to 1/3, which means we have actually shown that if we take the limit of our right-hand endpoints on y equals x squared, and we take our limit as n goes to infinity, it will be equal to the exact area under that curve, which is 1/3. For example 4, it says, let A be the area of the region under the curve f of x equals e to the negative x between x equals 0 and x equals 2. We want to estimate the area using Riemann sums with midpoints and 4 subintervals. So we're going to start with our function f of x equals e to the negative x, and we're going to be in an interval this time from 0 to 2. And we want to do midpoint with 4 subintervals. So this is what we're looking for in the end. I'll put it down here. M4. We want the midpoints and 4 subintervals. So the first thing we're going to do is we're going to figure out what is the width of each of our rectangles going to be. So this is just going to be delta x, which of course is b minus a over n. Our b in this case is our upper bound, which is 2, minus our a is our lower bound, which is 0. And then our n is how many subintervals are we actually going to create. So this is going to be 4. So this will be 2 over 4, or 1/2. Now with this, we can actually find our intervals, because our intervals are going to be starting at your lower bound, which is 0, you're going to go up by 1 over 2, or delta x. So this is going to be 1/2. Then I'm going to start at 1/2 for my second subinterval, and I'm going to go up by another 1/2. So this is going to be 1. And then I'm going to, from there, actually, just to keep it consistent, I'm going to turn this into 0.5. So this is going to be 1 to 1.5, and this is going to be 1.5 to 2. Now you could have kept this in fraction form. It doesn't really matter, right? We could do 1/2. This could be 2 halves we want. This is 3 halves, and then 2 could be 4 halves. But I decided to just do decimals, just kind of keep it simple. If we want to figure out what are our midpoints, this is actually the reason I want to do as a decimal, because if we want our midpoints, what is the midpoint between 0 and 0.5? Well, it's 0.25. So our first midpoint is 0.25. What is the midpoint between 0.5 and 1? It would be 0.75. What's the midpoint between 1 and 1.5? It'd be 1.25. And then what's the midpoint between 1.5 and 2? It would be 1.75. So these are going to be the midpoints that we're plugging into our function to get the heights. So our heights are going to be based on f of 0.25, f of 0.75, f of 1.25, and f of 1.75. So then looking for our area, we're going to have that our area is going to be equal to the sum I equals 1 to 4 delta x f of x sub I. So this is going to be equal to, we have a delta x of 1/2, so this will be 1/2 f of x sub I, which is to say the first x value, which would be this one, 0.25, and our f of x is e to the negative x. So this is going to be e to the negative 0.25. So then we just do the rest of these, 1/2 e to the negative 0.75 plus 1/2 e to the negative 1.25 plus 1/2 e to the negative 1.75. Each of these has 1/2 in front of them, so you could pull this out, figure out what e to the negative 0.25 is, e to the negative 0.75, e to the negative 1.25, and e to the negative 1.75. Just you add up all these e values, and you multiply by 1/2, and you will get an answer that is approximately 0.8557. Our last example says, let A be the area under the curve y equals e to the negative x from 0 to 2. And then using right-hand endpoints, express A as a limit. So what this means basically is that we want to find the Riemann sum using the limit as n goes to infinity, but we're not actually going to solve for what the value is. We just want to set up the problem for what the limit should be. So I've actually left the beginning of the problem here. So we have f of x equals to e to the negative x on the interval 0 to 2, and our width will be delta x, which is going to be b minus a over n. So plugging in our interval values, we're going to get that this is equal to 2 minus 0 over n, or 2 over n. So what this means is that when we actually are looking for our intervals, what we're going to do is, again, we're going to start at our lower boundary. So this is going to start at 0, and we're going to go up by 2n. And then for our second boundary, we're going to start at 2n, and we're going to go up by another 2n. So this is going to be 4 over n. And then we're going to go from 4 over n to 6 over n. And then we're going to continue to do this until we get to our final interval. Now, like I said, the easiest way to do this generally is to focus on the end interval, where what's happening every time we go up? Well, we went up by 2n, 4n, 6n, 8n. So pretty much what's going to happen is, if this is my first interval and it's 2 over n, this is my second interval and it's 4 over n, this is my third interval and it's 6 over n, it's basically going to be 2n over n. And then each of these, if I were to go to the left-hand endpoint of that interval, it's going to be minus 2 over n. So this will be 2n minus 2 over n. Okay, so now we have our intervals. We need to figure out what our right-hand endpoints are. So our right-hand endpoints are going to be 2 over n, 4 over n, 6 over n, so on and so forth, up to n over n. And these are going to be what we're going to plug in to get our heights. So the heights of our rectangles will be our function at 2 over n, our function at 4 over n, our function at 6 over n, our function at, well, I guess I'm going to whatever, 8 over n, up to our function at n over n. So now if we wanted to, we could replace these, right? Because if f of 2 over n, if we're going to plug this in, this is going to be e to the negative 2 over n, right? So this would be e to the negative 2 over n. This one is going to be e to the negative 4 over n. This one is going to be e to the negative 6 over n, e to the negative 8 over n, up to e to the negative n over n. Or 2n, sorry. 2n over n. Okay, so now let's actually express what our area is. So our area is going to be the limit as n approaches infinity, and this is going to be using our Riemann sum. So this is going to be the sum I equals 1 to n delta x f of x sub I. So what are these different values? So first of all, we have our limit. That doesn't change. So limit n equals infinity, or n up to infinity. Sum I equals 1 to n. What is our delta x? Well, that's the first thing we found in the problem. That's going to be 2 over n. So now, looking at the pattern that our heights take, this is going to be whatever index we're at, it's going to be e to the negative 2 times that number over n. So this is going to be times e to the negative 2i over n. And then from there, we can figure out what is the width times height of every single rectangle. So for example, if my index is 1, right, this is going to be e to the negative 2 over n. If I plug 1 in here, I would get e to the negative 2 times 1, which is 2 over n. If I took my second index, this would be e to the negative 4 over n. If I plug in 2 here, it would be e to the negative 2 times 2, which is 4 over n. If I plug in my third index, it'd be 6 over n, 8 over n. You can see that this is equivalent to each of these as we take our index from 1 to n. So this is how we find a Riemann sum, which is actually going to be the basis of integration, because what we're going to do is we're just thinking of whatever curve we have on some interval a to b. If we were to slice it into some number of subintervals and then create rectangles to represent the area of that curve, as you get more and more and more rectangles, which means they're going to get smaller and smaller and smaller, means there'll be less and less that it's over under counting until, as you approach infinity, it starts to converge on the true value. Hello everyone. In today's lesson, we're going to be learning about how to solve indefinite integrals. So the definition of an indefinite integral is the area under a curve f of x is expressed by the limit as n goes to infinity, the sum from I equals 1 to n on delta x times f of x sub I. And this type of limit is also used to find the distance traveled by an object, finding volumes of tumors, cardiac output, blood flow, things like that. We're going to use the integral notation to represent these types of limits. So the area under f of x from some starting point A to some ending point B will be written as, so this is our integral symbol called the integrand. So we have the integral from starting point A to ending point B on our function f of x dx. And f of x in this case is actually our integrand, and a is our lower limit, b is our upper limit, and this symbol here is our integral sign that we're going to be using. So integration using these integrals will give us an exact area, while the Riemann sums using rectangles were giving us an approximation or an estimate of the area. So if f of x takes on a positive or negative value, we're going to calculate the net area of our a1 if it's above the x-axis and a2 below. So in this case, if you have some shape like this, right? So if we have our xy axis, and let's say we had something like this, where this area above the graph, above the x-axis, is going to be positive, and our area below the x-axis is negative. So in that case, if we were taking the integral from a to b, f of x dx, this would be the area above the x-axis, a1, minus any area that is below the x-axis, so minus a2. Meaning if we had a shape like this, we have a1, a2, and a3, this would end up being a1 minus a2 plus a3. So any area that's underneath the x-axis, we subtract. Any area that is above the x-axis, we add when taking the integral from some starting point A to some ending point B. And based on this, we say that the definite integral, so the integral from a to b, f of x dx, exists, then f of x is integrable. And this process of finding integrals is called integration. So when we say solve by integration, we mean take the integral of f of x. Now, before we move on to looking at how to solve these indefinite integrals, I first want to go over some common and useful sums that we might need. So the first one is going to be that if we have the sum from I equals 1 to n, I, this is going to be equal to n times n plus 1 divided by 2. Our second sum is going to be if we have the sum from I equals 1 to n, I squared, this is going to be equal to n times n plus 1 times 2n plus 1 over 6. If we do the same thing, sum I equals 1 to n on I cubed, this is going to be equal to n times n plus 1 divided by 2, and then the whole thing is squared. Our fourth is that if we take the sum from I equals 1 to n, for some constant c, this is just going to be equal to n times c. So an example of this would be if you had the same number repeating 4 plus 4 plus 4 plus 4 plus 4, it would just be 4 times however many of them you had in your sum. For number 5, we have that if we take the sum I equals 1 to n, c times some value a sub I, this is going to be the same thing as c times the sum I equals 1 to n, a sub I. So what this is saying then is that if I have some constant times my sequence of numbers that I'm taking the sum of, then I can actually pull that constant out, take the sequence or series of numbers, sum them up, and then multiply that final product the final sum by whatever c is. And then the last thing is that if we have the sum I equals 1 to n, a sub I plus or minus b sub I, this is the same thing as the sum of I from I equals 1 to n, a sub I plus or minus the sum I equals 1 to n, b sub I. So this is just like when we did our limits and when we did our derivatives and anything like that. Whenever we have the sum of sum A plus or minus sum B, we can actually split it into the sum of A's plus or minus the sum of B's. So for our first problem, let's actually look at how do we write an integral based on what we've done previously. So suppose that you have the limit as n approaches infinity, x sub I cubed plus x sub I sine of x sub I. And we want to do this on the interval from 0 to pi. Well, in this case, right, remember we talked about the fact that when we did our Riemann sums, what we'd have to do is we would take the interval starting at 0 to pi based on some number of rectangles, and as they get smaller and smaller and smaller, meaning our number of subsections is going to infinity, we would then find the area of this shape. Well, whenever we're doing our integral, we don't have to put the x sub I. So this is just going to be x cubed plus x sine of x. And our a in this case, which is our starting point, is 0. Our b, which is our ending point, is going to be pi. So this means that if we wanted to write this definite integral, this is going to be the integral from 0 to pi x cubed plus x sine of x, and then we put dx. So this dx is telling us with relation to what variable are we taking this integral. So if you have dx, it means you're taking the integral with respect to x. If you have dy, you're taking the integral with respect to y. dz, you're taking the integral with respect to z, so on and so forth. Let's suppose that we had the function f of x equals x cubed minus 6x, and we wanted to solve this using our Riemann sums with right-hand endpoints with a equals 0 and b equals 3, and the number of intervals is 6. Well, using our Riemann sums, what we would do is we first need to figure out what is our width. So x bar, remember, is b minus a over n, so this would be 3 minus 0 over 6, which would be 1/2, or 0.5. And then we would need to figure out what are our intervals. So our intervals would be starting at that beginning point, 0. We would go up by 0.5, so 0.5, from 0.5 to 1, from 1 to 1.5, from 1.5 to 2, from 2 to 2.5, and from 2.5 to 3. Once we have our intervals, now we need to figure out what are our right-hand endpoints. So these would be the right-hand side of each interval. So this means that we're going to want to find f of 0.5, f of 1, f of 1.5, f of 2, f of 2.5, and finally f of 3. Now, of course, these will give us our different heights. So these will be equal to, if you were to take 0.5, plug it into x cubed minus 6x, you take 1, plug it into x cubed minus 6x, this would give us negative 2.875, negative 5, negative 5.625, negative 4, 0.625, and 9. And then finally, to actually find our Riemann sum with 6 subintervals using right-hand side inputs, this is going to be the sum I equals 1 to 6 delta x f of x sub I. So remember that when we're taking the sum of some constant times a bunch of different things, we can pull that constant out, which means really we're going to take delta x, which in this case is 0.5, and we're going to multiply it by negative 2.875 minus 5 minus 5.625, minus 4 plus 0.625 plus 9. And then when we do that, we should get that this is equal to negative 3.9375. So this now gives us an approximate answer using our Riemann sums, again with 6 subintervals, of this function x cubed minus 6x. Now what we're going to do is we're going to show, solving it analytically, what the precise answer would be. So starting with the same initial setup, we have f of x equals x cubed minus 6x. Our starting point is a, and our ending point is b. We would write this integral as the integral from 0 to 3 x cubed minus 6x dx. And next thing we're going to do is we're going to solve it just like we did the Riemann sum, except for this time we're going to do it for an infinite as n approaches infinity. So first things first, let's find our width. And I'm going to write this kind of small because there's a lot of steps for this. We have our delta x, which is equal to b minus a over n, which in this case, our b is still 3, our a is still 0, but now we have some number n. So this is going to be equal to 3 over n. So now using that, when we find our intervals, we're going to start at 0, and we're going to go up by 3 over n. For our next interval, we're going to start at 3 over n, and then we're going to go up by another 3 over n, giving us 6 over n. Then we're going to have 6 over n to 9 over n. We're going to have 9 over n to 12 over n, 12 over n to 15 over n, so on and so forth, until we get to... Now what I'm going to do is I'm actually going to write the last point first, and this is going to be 3n over n. So now if I were to divide this out, these n's would cancel, and I would be left with 3, which is our ending point. So what I'm going to do is I'm now going to look at this 3n over n, and I'm going to subtract our delta x to get the prior point. So 3n over n, so 3n minus 3 over n. Okay, so now I have my intervals. So this means that the heights are going to be based on, for using right-hand side, this is going to be f of 3 over n. This is going to be f of 6 over n. This is going to be f of 9 over n, so on and so forth, until we get to f of 3n over n. Now to write this in its general form, we're going to write this as, this is going to be equal to 3i over n cubed minus 6 over 3i over n. And this is going to be based on our final point, but if you think about it, what happens when I plug in 1? I'm going to get 3 times 1 over n. That's going to be 3 over n. If I plug in I equals 2, it's going to be 3 times 2 is going to be 6 over n. That's going to be our second point. If I plug in 3 times, or I equals 3, so 3 times 3 is 9, 9 over n, so on and so forth. It'd be the same for all of them. So this is just taking that and plugging it back in for our original function f of x. So now we can actually start to solve our integral from 0 to 3 and x cubed minus 6x dx. Well, we just said that this function is going to be equivalent to this, so we're going to take our limit as n approaches infinity, the sum I equals 1 to n, delta x, f of x sub I, which is our Riemann sum as we take n to infinity. So replacing this, we will get the limit as n approaches infinity, sum I equals 1 to n, and then we're going to plug this into here. So this is going to be equal to our delta x, which is 3 over n, right? So we had that earlier, times 3i over n cubed minus 6 times 3i over n. So the first thing I'm going to do now is I'm actually going to take the cube, I'm going to put the cube within this, and I'm going to distribute this negative 6. So now this is going to become the limit as n approaches infinity, the sum I equals 1 to n, 3 over n. So then we're going to take 3 cubed, which is going to be equal to 9 I cubed over n cubed minus, and then I'm going to distribute my 6, so this will be 18i over n. The next step I'm going to do is I'm actually going to then distribute this 3 over n in. So this is going to become the limit as n approaches infinity, the sum I equals 1 to n, and then I have 3 times 9. Real quick, this actually should have been 27 because it's cubed, not squared. So I have 3 times 27 is going to give me 81i cubed over, and then this n times this n cubed is going to give me n to the 4th power, minus, now I'm going to have 3 times 18, which is going to give me 54i over, and again, this n is going to enter with this n, this is going to become n squared. Now you might wonder, why did we do this? Well, we did this in order to get it in a form that we can actually use one of our substitutions. So now I'm going to use this first rule we looked, or this last rule we looked at, which is I'm going to split this. We have term 1 and term 2. I'm going to split this sum into the sum of this minus the sum of this. So this is going to become the limit as n approaches infinity, the sum as I equals 1 to n, 81i cubed divided by n to the 4th power minus the sum I equals 1 to n, 54i divided by n squared. The next thing I'm going to do is I'm going to pull out anything that is a constant for this sum. So remember, the sum is only changing the I terms, meaning for this first one, we have that 81 over n to the 4th power is as a constant. Similarly, this 54 over n squared is also a constant. So this is going to be the limit as n approaches infinity, 81 over n to the 4th power, sum I equals 1 to infinity, or sorry, 1 to n, I cubed, minus 54 over n squared times the sum I equals 1 to n, I. And now we can actually use this first one for this. We have the sum of I equals 1 to n on I, which is just going to be n times n plus 1 over 2. And this one is going to be the sum of I equals 1 to n I cubed, which is just going to be equal to n times n plus 1 over 2 all squared. So then substituting that in, we're going to get that this is the limit as n approaches infinity, 81 over n to the 4th power times n plus 1 over 2 all squared, minus 54 over n squared, and then this is going to be times n plus 1 over 2. Now you might wonder, why are we doing this? Again, it'll make sense when we get to the end. So next thing I'm going to do is I'm actually going to pull this constant 2 out of both of these. And I'm going to put n squared within each of these, right? Because if I have, this is squared, so if I put n to the 4th power within, this would be n squared, because n squared squared would give me n to the 4th. So this is going to become the limit as n approaches infinity, 81 over, when I pull the 2 out of here because it's squared, right? Because it's 2 squared, this would become 81 over 4. And then this is going to be n over n plus 1 over n squared minus, oh, forgot my square. Now what I'm going to do is I'm going to do the same thing. I'm going to put this n squared in. I'm going to pull this 2 out. So this is going to be 54 over 2, which is 27. N times n plus 1. And then when I put that n squared in, because this one's not squared, it's just going to be over n squared. And now I have this entire thing that I'm taking the limit of. For my next step, what I'm going to do is I'm going to distribute this n for both of these. So this is going to become the limit as n approaches infinity, 81 over 4, n squared plus n over n squared squared minus 27 n squared plus n over n squared And then I'm going to change it one more way. If I were to then split this, right? So this would be n squared over n squared plus n over n squared. This is the same thing as 1 plus 1 over n. So this would be the limit as n approaches infinity, 81 over 4, 1 plus 1 over n, and this whole thing is still squared, minus 27, 1 plus 1 over n. Now you might wonder, why did I do this? Well, I did this because currently if I had taken the limit here, I'm going to get infinity plus infinity divided by infinity, which is indeterminate. But now I can actually evaluate my limit, because if I were to evaluate my limit as n goes to infinity, this is a constant, doesn't get changed. This 1 over n though, as n gets bigger and bigger towards infinity, this is going to go towards 0. Similarly, if I take the limit of this 1 over n, this is going to go to 0. So this is going to leave us with 81 over 4, 1 plus 0 squared, minus 27, 1 plus 0. So of course, we're then just going, 1 squared is just going to be 1. We have 1 here, so basically we're going to get 81 over 4 minus 27. So 81 over 4 minus, now 27 can be written as 108 over 4, which is going to give us negative 27 over 4, which is equal to negative 6.75. Now this is the exact area of this function x cubed minus 6x when we take it starting at the starting point 0 and ending point 3. Now I know what you're probably thinking. You're probably thinking to yourself, that was a lot just to solve that integral for x cubed minus 6x. And I do promise you that if you stick with me, I'm going to show you a much faster, simpler way to solve integrals like that. But before we do that, let's actually do a couple more examples. So suppose that you had the integral from 0 to 1, square root of 1 minus x squared dx. And we wanted to figure out, what is the area under the curve? Well, what is this? Well, what it is it is a semicircle, but we're only looking at x equals 0 to x equals 1. So what this is going to look like is this. So how do we figure out what the area under this curve is? So now let's look at this 1 minus x squared. We know that the square root of 1 minus x squared has to be greater than or equal to 0 when it's on our interval from 0 to 1. And this is because if I were to plug in 0, I'd get 1 minus 0 squared, which is 0, so 1. Square root of 1 is 1, which makes sense, right? At 0, I have a height of 1. If I were to plug in 1, I would get 1 minus 1 squared, which is 1 minus 1, square root of, which would give me 0. Square root of 0 would be 0. So when I have x equals 1, I have a height of 0. So now what we're going to do is we're going to consider the fact that we have our function y equals the square root of 1 minus x squared. And then I'm going to square both sides of this. So my square root and my square are going to cancel, and I'm going to be left with y squared equals 1 minus x squared, which then I can rewrite as x squared plus y squared equals 1. So pretty much what this means is, like I said, this is a part of a circle. It's a quarter of a circle. And this is our formula for a circle. So in this case, we're going to take this function for our circle, and it's just going to be a quarter of that. So that means that the integral from 0 to 1 square root of 1 minus x squared dx is actually just going to be a quarter of the area of a circle. And our area of our circle is pi r squared. So in this case, it would be pi, and our radius in this case would be from the center of the circle to the edge. So we have an r of 1. So we'd have pi 1 squared. So this is going to leave us with 1/4 pi, which is then just going to be, I'm just going to rewrite this as pi over 4. So previously we talked about having areas above and below the x-axis. So let's do an example like that. So let's say that we have the integral from 0 to 3 x minus 1 dx. Well, in this case, if I were to graph this, what would this look like? Well, when I plug in 0, I'm going to get negative 1, meaning that it'll start here. When I plug in 1, it's going to become 1 minus 1 is 0. So we're going to have it cross here. If I plug in 2, it'd be 2 minus 1, which would give me 2. And if I plug in 3, it'll be 3 minus 1, which would give me 2. So if I were to then draw this, the area from 0 to 1 is going to be negative. The area under the curve from 1 to 3 is going to be positive. So in this case, if we look at this, these are just going to be triangles, where this one has, right, so the area of a triangle is just going to be 1/2 base times height. So in this case, it has a base of 1, it has a height of 1. For this one, because we're going from 1 to 3, it has a base of 2, and it has a height of 2. So this means that our integral from 0 to 3, x minus 1 dx, can be written as the area of this second interval. So this is going to be 1/2 2 times 2 minus the area of our interval that's underneath the x-axis. So 1/2 1 times 1. So this is going to be 1/2 and 2. These two are going to cancel. So we're left with 2 minus 1/2, or 1.5 or 3/2, depending on how you want to write it. When using a Riemann sum to approximate our integral, we can also use, right, we had our left-hand side rule, our endpoints, our right-hand side endpoints. We could also use our midpoints. So we're going to use our midpoint rule with n equals 5 to approximate the integral from 1 to 2, 1 over x dx. So the first thing we're going to do, we're going to figure out our width. So delta x equals b minus a over n, where our b is going to be 2, our a is going to be 1, and our n is going to be 5. So we have 2 minus 1 is 1. This is going to give us a width of 1/5. Now we're going to figure out what our intervals are. So we're going to start at our starting point, this a here, which is going to be equal to 1, and we're going to go up by 1/5, which is just going to be equal to 0.2. So this is going to become 1.2. This is going to be 1.2 to 1.4, 1.4 to 1.6, 1.6 to 1.8, and 1.8 to 2. Now, generally what we've done is we then would look at our left-hand endpoints or our right-hand endpoints. But this time what we're doing is we're using midpoints. So the midpoint between 1 and 1.2, you just take the average of them. So 1 plus 1.2 gives us 2.2. Divide by 2, we get our midpoints of 1.1, 1.3, 1.5, 1.7, and 1.9. So these are our heights are going to be f of 1.1, f of 1.3, f of 1.5, f of 1.7, and f of 1.9, which are just going to be equal to, right, we have 1 over x, so we're just going to plug in each of these for our x. This one is going to be 1 over 1.1. This one's going to be 1 over 1.3. This one's going to be 1 over 1.5. This one is going to be 1 over 1.7. And this one is going to be 1 over 1.9. So now if we want to find our approximate value for our integral, we have that the integral from 1 to 2, 1 over x dx is going to be equal to, remember, it is delta x times f of x1, f of x2, plus f of x3, so on and so forth. They're all times delta x. So I'm going to pull that delta x out. So I'm going to get 0.2 times 1 over 1.1 plus 1 over 1.3 plus 1 over 1.5 plus 1 over 1.7 plus 1 over 1.9. And this is going to give me an approximate value of 0.691908. So up until now, we've been looking at ways we can approximately find the integral by using Riemann sums or using the area of certain shapes that we know the area of, or solving analytically using a substitution to make it something we could actually work with. But now let's actually look at how do we solve integrals directly. So we have a couple rules or properties that we need to define. The first is that if we have some integral from a to b, f of x dx, this is equivalent to minus the integral from b to a, f of x dx. meaning that if our starting point is our ending point and our ending point becomes our starting point, it'll give us the same value as the integral a to b f of x dx, except for it will be the negative of it. So if we got, like, for example, 4 here, if we did it the other direction, it would give us negative 4. The next rule is that if we have the integral from a to a f of x dx, this is going to be equal to 0. So what does this mean? It means that if I'm taking the area under a curve from some starting point to the same exact point, meaning that there is no width, right? So if you think about area, if let's say we do rectangles, we have length times width. Well, there's no width, meaning that in this case, it is 0 because there's no width to it. Pretty much what it means, something like this. If I have some shape and I say, what is the interval from A to A? It's just a line. There is no area. So that's why it's equal to 0. Part 3 says that if we have the integral from A to B, some constant c dx, this is going to be equal to c times b minus a. And this will make more sense whenever we actually start solving our integrals. But basically what's happening in this case is if we just have some constant, so if this is my x-axis, this is my constant c, and I have some starting point A and some starting point B, then the area is just going to be however far I had between A and B, which would be B minus A, times the height C. And that would give us the area of the rectangle that's created by wherever that C value is. Our fourth rule is that if we have the integral from A to B, this one should look familiar, f of x plus or minus some g of x, this is going to be equal to, sorry, I forgot my dx. This is going to be equal to the integral from A to B, f of x dx, plus or minus the integral from A to B, g of x dx. So just like before when we did our sums, we did our limits, when we did our derivatives, if we have the integral for f of x plus or minus g of x, this is the same thing as the integral of f of x dx plus or minus the integral g of x dx. Our next rule is that if we have some constant times our f of x dx, this is going to be equal to, I can pull that constant out, this is going to be c times integral a to b f of x dx. And our last rule we have is that if we have the integral from a to b f of x dx, this is equal to the integral from a to c f of x dx plus the integral from c to b f of x dx. So what this pretty much means is this. If I have on my xy axis, if I have some shape and I want to know what is the area from A to B, what I can do is I could have some c here, find the area from A to C and the area from C to B, and when I combine them by adding them together, I would get the area from A to B, meaning that you could take any curve you have and you could split it up into subparts. And that's kind of what we're doing whenever we do the addition, subtraction above and below the line, right? So when we had something like this, what I'm doing is I'm piecemealing it to this interval, and I'm getting my positive part, and I'm finding this area under the curve for my negative part. And basically what I'm doing is I can do this for as many parts of my curve as I want to. So now let's do some really quick examples using these properties to solve for our integrals. So let's say we had the integral from 0 to 1, and we had 4 plus 3x squared dx. So first things first, I can actually split this integral into the integral of the first term plus the integral of the second term. So this is going to be equal to the integral from 0 to 1, 4 dx, plus the integral from 0 to 1, 3x squared dx. Now this first one, because it's a constant, I can actually solve this one right away because we have here that it's equal to c times b minus a. So this is going to be equal to 4 times 1 minus 0. Plus, for this one, I'm going to use the fact that if I have a constant times some function, I could pull that constant out. So this is going to become 3 times integral from 0 to 1 x squared dx. And now what I can do with this is I can use a property where if I have the integral from 0 to 1 x squared, this is dx, this is equal to 1/3. And I will show you in the next lesson how exactly I know that. Basically what we're doing is we're using our antiderivative, right? Because if we have x squared, if I take the antiderivative of that, what does it become? Well, it becomes x cubed over 3. And that's where the 1/3 comes from. In this case, because it's from 0 to 1, it'll, like I said, I will show this to you in the next lesson. So this one is going to be 1/3. So this then becomes 4 times 1 minus 4 times 0, which is 0. So this is going to be 4 plus 3 times 1/3. And this will give us 4 plus 1 equals 5. What about if we had the integral from 0 to 10 f of x dx is equal to 17, and we have the integral from 0 to 8 f of x dx is equal to 12. Then what we want to do is we want to find the integral from 8 to 10 f of x dx. So this is going to be using this property here, where if I'm going from some a to b, which in this case a is 0, b is 10, what I can do is I can take a to c, take the integral from there, plus the integral from c to b. Well, in this case, I rearranged it, so I'm looking for this c to b. So I subtracted this to the other side, so it'll be the integral from a to b, f of x dx, minus the integral from a to c, f of x dx. So this means what I can do is I can take the integral of the entire interval, f of x dx, minus the integral from 0 to 8, f of x dx, and this is going to give me the integral that's left, whatever's left, right? So I'm taking the entire area of the curve, under the curve, minus the area under the curve from 0 to 8, and I'll be left with what's left under the curve from 8 to 10. So this means that this is going to be equal to 17 minus 12, or an area of 5. So now that we've looked at indefinite integrals and how we can approximate them and looked at rules about them, in our next lesson, we're going to be looking at how can we actually solve them. We're going to do this using antiderivatives. In this case, it becomes much more straightforward for a lot of integrals. Hello, everyone. In today's lessons, we're going to be looking at how to solve integrals using antiderivatives and the fundamental theorem of calculus. So the fundamental theorem of calculus says, let f of x be any antiderivative of lowercase f of x, then a, the area under the graph, equals the limit as n goes to infinity, the sum of the index I equals 1 to n, delta x times f of x sub I, right? So if you remember from when we were doing Riemann sums, this just means you take the width of each interval and you multiply this by the height of that interval, which is represented by f of x sub I. So f of x for that index, right? First rectangle being I equals 1, second rectangle being I equals 2, up to the last rectangle I equals n. And then you would sum these up. As your n approaches infinity, meaning that, remember, your delta x is going to be b minus a over x, so, or b minus a over n, which is going to get smaller and smaller and smaller. What's going to happen is this is going to converge on the actual area under the graph. This is equal to the integral from your starting point A to your ending point B, f of x dx, which you can then solve by capital F of b minus f of a. Now, what does this actually mean? Well, if you remember, when we use the capital letter, this is just saying that this would be the antiderivative of f of x. So what this is saying then is whatever this function f of x is, find the antiderivative, evaluate it at your endpoint b, evaluate it at your starting point a, subtract the antiderivative of a from the antiderivative b, and that will give you the area under the curve. So what is this actually doing? Well, let's say that you have some graph, right? So whatever it is, let's just say it looks something like this, let's say, where a is here and b is here. Well, if you remember when we're actually looking at the areas of individual parts of a graph, let's call this A1, A2, and A3. what we would do is anything that was above the x-axis, we would add. So we have a1 plus our a3. And anything that was below the x-axis, we would subtract, minus a2. So really what we're kind of doing is we're saying, okay, well, what is the area right here? And our ending point, which is going to be here. And this is going to give us the amount of distance that we've changed since this started, meaning that we'll have our parts above and below that kind of counteract each other. So what we're doing is we're looking for how is this actually changed? For sort of like in physics, you might have something like potential energy. You have a potential energy up here, and then it changes to kinetic energy. Maybe it goes down, like you push a ball down a hill, then you roll the ball back up, and now you're back to the original position. So how much did the potential energy change? Well, it didn't, because it's back in its original state. It's the same idea here. We might go up, we might go down, but in the end, our area is going to be the part where it is either above or below based on these antiderivatives. So again, since velocity is the derivative of position, the area under a velocity curve will give us the distance traveled. So speaking of physics problems, this would be something like when we were talking about derivatives, when we had a function that represented like distance. If we took the derivative of this, we would get the change in the position, sorry, not distance, and then that would be velocity. Well, if I then took the antiderivative of a velocity graph, or velocity function, I would get the position function. It's the same idea here, right? Your antiderivative is sort of undoing your derivative. This leads us into our net change theorem. The net change theorem says that the integral of a rate of change, that is the derivative, is the net change so that the integral from a to b on f prime x dx, that is the integral on the derivative of f of x, is equal to the function f of b minus the function f of a. So what does this mean? That just means that, remember what I was just talking about with our velocity from our position? Well, if I have a function, f of x equals position. If I take the derivative, f prime of x, I now have velocity. If I take the integral from some starting point a to some starting point b on the velocity, that's the f prime of x, I could solve this by taking the function f of b minus f of a, right? So our ending point minus our starting point. And this would basically be something like if I went forward 1,000 feet and then came back 300 feet, how much was my net change? Well, I changed by a total of 700 feet. So for example, if nt is the size of a population at time t, then if we have the integral from t1 to t2, n prime of t dt, this would be equal to n, the size of the population at time 2, minus n population time 1, or this would just be the net change in population. What was the net change in population from time 1 to time 2? Now, in order to solve our definite integrals using our antiderivatives, let's first talk about our indefinite integrals. So if you have the indefinite integral f of x dx, this is used to represent the antiderivative of our function f of x. So for example, if we had something like this, the integral of f of x dx, this would just end up being the antiderivative of f of x. And then, of course, remember we talked about this when we did antiderivatives, we'd have to take into account that there could be some constant c that was eliminated. If you have some original function take the derivative, you would lose that constant. So we have to kind of consider that we may have some constant added to it. So we do plus c, which this c could be 0, which means that there wasn't a constant. If we wanted to look at a definite integral, so this would be an integral where we have our boundaries or limits of integration from a to b, f of x dx, then this would be equal to the antiderivative of f of x, and we write it this way. Draw this line, and we're going to evaluate it from a to b. This means that in order to solve this, we just have to figure out what is the antiderivative, and then we figure out what is the antiderivative when we plug in b, minus what is the antiderivative when we plug in a. And this is how we actually can use the definition of an indefinite integral to solve for a definite integral, which would make things a lot easier than when we did it previously using our Riemann sum approach, which was a equals the limit as n approaches infinity, sum I equals 1 to n, delta x, f of x, which is just the same thing as saying the integral, and if of course we had some boundaries, we had a to b, f of x dx. Well, now instead of doing all of the different number of intervals, and then considering what happens when we did it analytically as n went to infinity, now what we can do is we can actually just use the antiderivative, and it becomes pretty trivial for a lot of problems. So now let's look at some common indefinite integrals, which, if you remember, these are really just going to be the same thing that we kind of talked about when we did antiderivatives. So first of all, we're going to let c, some arbitrary constant for these, be equal to 0. But remember, anytime you would do these antiderivatives, you would need to include this plus c, because this might not be equal to 0. For this, we're just looking at what is the main antiderivative of each of these functions, and then we would know add plus c. So the first one is that if we have the integral of x to the n, right? So remember, what we want to do is we want to kind of, in this case, consider that we have the inverse of our power rule, right? And we did derivatives, so if we had x to the n and we did the power rule, we would bring that n down, we would subtract 1. Now what we're going to do is we're going to add 1 to that n, and because we would have brought that n plus 1 down, we would need whatever eliminated that, because there's no n plus 1 here, so this would be over n plus 1. For our second indefinite integral, if we have the integral of e to the x dx, just like when we took the derivative of e to the x is e to the x, antiderivative of e to the x is still e to the x. Well, e to the x plus c, but like we said, in this case, c is going to be equal to 0. So this would be equal to e to the x. If we have the integral of some constant a to the x power dx, this is going to be equal to a to the x divided by the natural log of a. And this is because if we were to kind of consider, remember when we were doing derivatives, we had our exponential functions. So some constant to a power, it would be that constant times the natural log of that, whatever the base was. Well, now if we want to do the opposite, we would have to consider that we have to divide out that natural logs. We're left just with the exponential, which means that's why it's a to the x divided by natural log of a. For number 4, if we have the integral for 1 over x dx, this is going to be equal to the natural log of the absolute value of x. Now you might wonder, why is it the absolute value of x when I could, in fact, plug in negative numbers here? Why does it have to be a natural log of absolute value of x? And this is because if we were to graph the natural log, it looks like this. So it's approaching negative infinity as you go towards 0, and then it's going to hit 0 at x equals 1, and it's going to do something like this, meaning that we can't have negative x values in our natural log. So that means we can only really take into account if, with a positive x. So this would be the integral for 1 over x dx is equal to the natural log of the absolute value of x. Next, if we have the integral of e to some constant k times x dx, this is going to be equal to e to the kx divided by k. And again, think of it in terms of the derivative. If you were taking the derivative of e to the kx, what would you do? You'd use the chain rule. You would have e to the kx, and then you would take the derivative of the inside. The derivative of kx would just be k. So if we wanted to undo that, we would have to divide by k to eliminate that k that's multiplied by it, right? So for example, let's say that I have e to the kx. If I take the derivative, this would become e to the kx times k. So to undo this, what I have to do is I'm going to have my e to the kx, but then because this is times k, I would have to divide by k, which would eliminate it, getting me back to e to the kx. That's the reason we divide this one by k. For our next one, if we have the integral of 1 over x squared plus 1, this is going to be equal to our inverse tangent of x. Right, and this is one we covered when we were doing antiderivatives. So our next ones are going to focus mostly on trig functions. So for number 7, if we have the integral of sine of x dx, right? You'd have to think about, if I took the derivative of what would give me sine of x? Well, cosine would give us negative sine of x, which means that it would need to be negative cosine of x. Right, so if I had a cosine of x, if I took the derivative, I would get negative sine of x. I need positive sine of x, so that means I would have to take negative cosine of x. If I have the integral of cosine of x dx, same thing. What would I take the derivative of to get cosine of x? Well, it would just be sine of x. For number 9, if we have the integral of cosecant of x times cotangent of x dx, this is going to be equal to negative cosecant of x. Again, think about when we were doing derivatives. If you have cosecant of x, you're going to get negative cosecant x cotangent x. So pretty much to undo it, same idea. And then lastly, we have number 10, which is if I have the integral of secant x tangent x, this is just going to be equal to secant x. And if you kind of look at it, what all of these are doing is we're pretty much saying if I had this function and took the derivative, what would get me back to this original function I'm taking the integral of? So that's all a lot of times what you're going to think about is, okay, if I were to undo this with a derivative using, for example, my power rule or my exponential rules or anything like that, what would I need to include that would cancel out any sort of k, right? So when I do the power rule of this, you bring down the n, which means I would need to bring down n plus 1 in the denominator to cancel out the n plus 1 that I bring down, right? So if I took the derivative of this x to the n plus 1 over n plus 1, right? So let's say we did dx dy of x to the n plus 1 over n plus 1. Using our power rule, I have n plus 1. I would bring this down, so I'd get n plus 1 over n plus 1, and then I would subtract 1 from my power, so x to the n plus 1 minus 1. The n plus 1's cancel, the plus 1 minus 1 cancels, and I'm left with x to the n, which is exactly what we would expect. So now let's do some examples. So as a reminder for this one, if we have the function f of x is equal to e to the x, that means that the antiderivative is going to be f of x equals e to the x plus c. So if we were to take the integral from 1 to 3 e to the x dx, this is just going to be equal to, first things first, let's figure out what our antiderivative is. Well, we just said that our antiderivative is e to the x. So we have e to the x. And we want to evaluate this from 1 to 3. So 1 to 3. This means that the area under this curve, e to the x, from 1 to 3, would be equal to the antiderivative at 3 minus the antiderivative at 1, which would be e to the 3 minus e to the 1, which of course we could write as e cubed minus e, which if you're curious, that would actually end up being approximately 17.3673. Now you might wonder, why did I not include the plus c? And that's because when you do the antiderivative, you do include that plus c. But when we have our limits of integration, it actually takes that into account. So by setting the boundaries of it based on the rate of change, you don't need to include the plus c because it's actually included in our calculation. So our second example says we want to find the area under the cosine curve from 0 to b, where 0 is less than or equal to b, and b is less than or equal to pi over 2. So we have that 0 is less than or equal to b, which is less than or equal to pi over 2. So if we look at what is happening with a cosine wave, it starts at, when x equals 0, at 1. And then it goes down, goes to -1, comes back up to 1. And this is happening at pi over 2. This is happening at pi, or 2 pi over 2. It's hitting 0 at 3 pi over 2. And then it's back up to 1 at 4 pi over 2, which would just be 2 pi. So this problem is specifically saying that our b is somewhere between 0 and pi over 2, meaning that it is only this part of the cosine function. So that means that it could be anything in this, right? So b could be right here in the middle, b could be at the end, b could be right at the beginning. So what are our possible values? Well, let's evaluate. If we have the integral from 0 to b, and we said that we're using cosine of x dx. Well, the first thing is we need to figure out what is the antiderivative. So the antiderivative of cosine of x would be sine of x. And this is because if I have sine of x and I were to take the derivative, I would get cosine of x. So that means my antiderivative of cosine of x is sine of x. And we want to evaluate this from 0 to b. So plugging this in, we're going to plug in b, right? We use our upper limit of integration. So this is going to be sine of b minus sine of 0. Okay, now what is sine of 0? Well, again, if we're graphing what a sine wave looks like, it's going to start at 0 and go like this. So basically at 0, it has a y value of 0. It's equal to 1 at pi over 2. It's equal to 0 at pi. It's equal to negative 1 at 3 pi over 2. And it's equal to 0 again at 2 pi. So what this is saying is that in this case, sine of 0 is just going to be equal to 0, meaning that the area under a curve is going to be equal to the sine of b. So what does this actually mean? Well, it means that based on where b is, what's happening to the area of my curve as my b gets further from 0? Well, when b is close to 0, so let's say it's at 0, then I'd have sine of 0, I would get 0. But as b gets further towards pi over 2, that means that I'm going to have this area like this. This would be equivalent to having the sine of b. So as b gets further to the right, closer to pi over 2, that means that the area will be also getting bigger following a sine wave. Meaning that if I want the area from 0 to b, depending on what b is, it's, again, if b is between 0 and pi over 2, then it would just be equal to the sine of whatever that b is. So if I said that b was equal to pi over 2, then it would be sine of pi over 2, which is equal to 1. For our next example, we want to solve the indefinite integral of 10x to the 4th power minus 2 secant square of x dx. So whenever we have an indefinite integral, but we're still going to follow the same steps. We're going to take the antiderivatives, but then what we're going to do is we are going to consider that there is some constant that we may not have been taking account, which we'll have to add that plus c. But first thing I'm going to do is I'm actually going to use one of our integration rules we talked about, which is when I have the integral of some function f of x plus or minus g of x, I can rewrite this as the integral of f of x plus or minus the integral of g of x. So this is going to be equal to the integral of 10x to the 4th dx minus the integral of 2 secant square x dx. And then what I'm going to do is I'm going to use another rule of our integrals, which was that if I have a constant times my function, I can pull that function out. So this is going to be equal to 10 integral of x to the 4th dx minus 2 integral secant square dx. And now we just need to figure out what are the antiderivatives of each of these terms. So for this first one, x to the 4th, we're doing the inverse of our power rule. So this x to the 4th is going to become x to the 5th over 5. And then we have our 10. So we have 10 times x to the 5th over 5 minus 2. And now we need to take the antiderivative of secant square x. This is going to be equal to tangent of x. And then, of course, because we don't have limits of integration, we have to take into account that these antiderivatives have some constant. So we're going to do plus c. Now, one thing I want to point out is that when we're taking the antiderivative of this x to the 4th, it could have an plus c. When we're taking the antiderivative of secant squared, we also could have a plus c. But what we do is we just combine them together, right? So it's some arbitrary constant. So a constant plus constant just gives us some other arbitrary constant. That's the reason why we can just do plus c. And then last thing I'm going to do, I'm just going to clean it up a little bit. This 5 is going to cancel with part of this 10, and we're going to be left with 2x to the 5th power minus 2 tangent of x plus c. So I mentioned before that we had two examples we did where we've used Riemann sum and also analytically solved for the integral of x cubed minus 6x. Well, now we're going to do the same thing, but we're going to show how easy it is using this approach. So we have the integral from 0 to 3 x cubed minus 6x dx. So as before, what I'm going to do is I'm first going to split this into two different integrals. So we have the integral from 0 to 3 x cubed dx minus the integral of 6x dx, where then I can just pull this 6 out. So I'm just going to do that like this. And now we have the integral of 0 to 3 x cubed dx minus 6 integral x dx. So using our antiderivatives, x cubed becomes x to the 4th divided by the new power of 3 plus 1, or 4, which is going to be divided by 4. Minus 6 times, we have x, which you can think of as x to the 1st power. So we're going to add a power to that. This is going to become x squared divided by 2. And in this case, we're actually evaluating it from 0 to 3, so we don't have to add our plus c. So now quickly just kind of cleaning this up, this 6 over 2 is just going to be equal to 3. So this is going to be x to the 4th over 4 minus 3x squared, and we're going to evaluate from 0 to 3. Now, the way you could do this, remember, is we want to do, when we have something like this, integral from a to b, f of x dx, this is going to be the antiderivative at b minus the antiderivative at a. You could do that for your first term, do it for your second term, and then remember to distribute your negative in this case. Or what you could do is you could plug b in for both of these terms, f of b being this, minus f of a being this. So I'm going to do it that way for this one. In class, I think I did it the other way, but either one is going to give you the right answers as long as you keep track of your positive, your negative sign as it distributes. So if we were to plug in b, in this case is 3, this is going to be 3 to the 4th power over 4 minus 3 times 3 squared minus, now we plug in 0. 0 to the 4th power over 4 minus a negative is going to be plus 3 times 0 squared. Now, these two 0 terms, 0 to the 4th power is 0, divided by 4 is still 0. 3 times 0 squared is 0. So really, it's just going to be these two terms here. So this is going to be equal to 81 over 4 minus 27, right? Because 3 squared is going to be 9. 9 times 3 is going to be 27. Okay, so now what I'm going to do is I'm going to rewrite this in terms of by combining them. So what I would do is I would multiply this 27 by 4 to get it over 4. And this is going to give me minus 27 over 4, which is approximately equal to, or which is equal to negative 6.75. Which, if you go back to our lesson when we did this analytically and solving it using our Riemann sums, this is exactly what we got. But notice how much easier it was. And I'm doing extra steps so that everybody can follow along the steps. But realistically, I could have just looked at this and said, okay, this is going to be x to the 4th over 4 minus 6x squared over 2. The 6 and the 2 are going to cancel to 3. So it'd be x to the 4th over 4 minus 3x squared. And then from there, all I had to do was plug in 3, plug in 0, subtract that from it, and I have my answer. For our next example, we want to take the integral from 0 to 2, 2x cubed minus 6x plus 3 over x squared plus 1 dx. So as before, first thing I'm going to do, I'm going to split this into 3 separate integrals to make it easier to evaluate. So this is going to be equal to the integral from 0 to 2, 2x cubed dx minus the integral from 0 to 2, 6x dx, plus the integral from 0 to 2, 3 over x squared plus 1 dx. And just like before, I'm going to consider the fact that I have these constants in front of each of these terms. I can pull these out. So this first term is going to become 2 times the integral of 0 to 2 x cubed dx minus, I'm going to pull the 6 out, 6 integral from 0 to 2 x dx plus, and now this you could think of as 3 times 1 over x squared plus 1. So I'm going to pull this 3 out. 3 integral from 0 to 2, 1 over x squared plus 1 dx. Okay, so now I just have to figure out what is the antiderivative for each of these. Well, this one, first thing first, I got my 2, times. This is going to become x, so this x cubed, we add plus 1, so this is going to become x to the 4th over 4, minus 6, x to the 1, we add 1 to it, so this is going to become x squared over 2. For this one, we have plus 3, and then we take the antiderivative of 1 over x squared plus 1, which if you remember is the inverse tangent of x. And we would then evaluate this from 0 to 2. So now quickly, I'm just going to clean this up really fast. This 2 over 4 is just going to be 1/2. So this is going to be x to the 4th over 2 minus the 6 over 2 is going to leave me with 3. So minus 3x squared and then plus 3 inverse tangent of x evaluated from 0 to 1. So now what I'm going to do, I'm going to do my f of b, so my antiderivative at b. So I'm going to plug 1 in. So this is going to be 1 to the 4th power over 2 minus 3 times 1 squared plus 3 inverse tangent of 1 minus, now we're going to do our a terms. We're going to plug in 0. So this is going to be 0 to the 4th power over 2 minus 3 times 0 to the 4th power, 0 squared plus 3 inverse tangent of 0. Real quick, actually, let me correct real fast. This was supposed to be ending at 2. I don't know how I went to 1. So this should have been 2 to the 4th power, 2 squared, and inverse tangent of 2. Okay, so 0 to the 4th power over 2, that's going to go to 0. 0 squared times 3, that's going to go to 0. Inverse tangent of 0, 0. So, okay, cool. So we're left with 2 to the 4th power over 2 minus 3 times 2 squared plus 3 inverse tangent of 2. So 2 to the 4th power is going to be 2, 4, 8, 16. 16 divided by 2 is going to be 8. Minus 2 squared is going to be 4. 4 times 3 is going to be 12. And then we have plus 3 inverse tangent of 2. So 8 minus 12, this is going to give me negative 4 plus 3 inverse tangent of 2, which will be approximately equal to negative 0.67855. If we want to evaluate the integral from 1 to 9, 2t squared plus t squared, square root of t, minus 1 over t squared dt, how would we solve this? Well, first things first, we don't really have a way that we can solve something in this form. So I actually need to do some rearranging or simplification first. So what I'm going to do is I'm actually going to split this into being 2t squared over t squared plus t squared square root of t over t squared minus 1 over t squared, right? Because if I have something like this, if I have a plus b over c, I can make this a over c plus b over c. It's sort of like whenever you have like bases, you can combine them. You can also split them. So doing this, what's going to happen is we are going to get the integral from 1 to 9, 2t squared over t squared plus t squared square root of t over t squared minus 1 over t squared dt. And then these t squares are going to cancel. These t squares are going to cancel. And this is going to leave me with the integral from 1 to 9, 2 plus square root of t, which I'm going to write this as t to the 1/2 power, right? Because I'm going to need it in terms of a power to do my inverse power rule, minus 1 over t squared, which we could think of as t to the negative 2, dt. Now, normally what I would do at this point is I would just say we're going to split it and all that kind of stuff, and we can, but the one thing I want to consider right here is this 2. So if we were to split it, we have the integral from 1 to 9 2 dt plus the integral from 1 to 9 t to the 1/2 dt minus the integral from 1 to 9 t to the negative 2 power dt. So this 2, right, we talked about the fact we can pull a 2 out, which might be a little bit confusing. So what I want you to do is think about when you have this 2 here, this is the same thing as 2 times t to the 0. And the reason is because whatever to the 0 power is going to be equal to 1. So that would be 2 times 1 is equal to 2. Now, why do we do this? Well, it's because remember when we did our antiderivatives, we talked about the fact that the antiderivative of a constant is a constant times whatever variable you're using. So in this case, this is going to be 2t. So that's what this one will end up being. The antiderivative of 2 times t to the 0, right? T to the 0, add 1 to the power, becomes t to the 1. Divide by that power, divided by 1, so 2 over 1, still 2. T to the 1 is equal to t. So this is going to be equal to 2t. Okay, now we need to figure out what is the antiderivative of this t to the 1/2. Well, just like before, we're going to use our power rule. So this is our inverse power rule, if you want to think of it that way. So we're going to take our t to the 1/2, and we're going to increase the power by 1, which means 1/2 plus 1, which is going to give us t to the 3/2. Now, what we need to do is we need to divide by this. Well, what happens when we divide by 3/2? Well, we have fractional division, right? So it's the same thing as we multiply by the reciprocal. This becomes 2 over 3 times t to the 3/2. And then last one, minus, we have t to the negative 2. Same thing. We add 1 to the power. So this becomes t to the negative 1. And we divide by that power. So in this case, we have a power of negative 1. So we're going to divide by negative 1. The negative 1 and the negative become positive. So then just rewriting this really fast. Also, we're evaluating this from 1 to 9. So rewriting this real fast, we have 2t plus 2/3 t to the 3/2 plus t to the negative 1, evaluated from 1 to 9. Okay, so now let's do that. Let's plug in 9 for each of these. Let's plug in 1 for each of these, right? Because every example we've done so far, we've had a 0 as our a value, and so it basically canceled out. But it's not always going to cancel out. So this is going to be 2 times 9 plus 2/3 times 9 to the 3/2 power plus 9 to the negative 1 power minus, right, because now we're doing our a terms. This is going to be minus 2 times 1 minus 2/3 1 to the 3/2 power minus 1 to the negative 1 power. Okay, so now let's solve it. So 2 times 9 is going to be equal to 18 plus, for this next one, we have 2/3 9 cubed, and it's the square root of 9 cubed, right? Because that's what this 3/2 means. It means that this is 9 cubed, and then we're taking the square root of that. So this is going to end up being, so I'm actually going to cheat to solve this. What I'm going to do, by the way, you could just plug this into a calculator, is I'm going to think of this 9 as 3 squared. So this would be 3 squared cubed, and we take the square root, the square and the square root will cancel. This is just going to leave us with 3 cubed, which is going to be equal to, so we'll have 2/3, I'll just write it as 3 cubed for now, plus 9 to the negative 1 power is the same thing as saying 1 over 9 minus 2 minus, so 1 to the 3/2, 1 cubed is still 1, square root of 1 is still 1, so this is going to be minus 2/3. And then finally, minus 1 to the negative 1/2, that just puts it in the denominator, so still minus 1 over 1, so this is going to be minus 1. Okay, so let's actually solve this now. We have 18 plus 3 cubed is 27. 27 divided by 3 is 9. 9 times 2 is going to be 18. Plus 1 over 9 minus 2 minus 2/3 minus 1. Okay, so we have 18 and 18. That's going to give me 36 minus 2 minus 1. That's going to give me 33. Minus, and we have 2/3, which we can actually multiply this by 3 to give me 6/9. So 1 minus 6/9 would be minus 5/9. And then if we want to solve this as an improper fraction, it would be 32, sorry, as a proper fraction, and this would be equivalent, or roughly 32.444, like repeating. So now let's go back to our fundamental theorem of calculus. It states that if f is continuous on an interval a to b, then the function g is defined as g of x equals the integral from a to x ft dt, where x is some value between a and b. And this is the antiderivative of f. That is to say that g prime of x will just be equal to f of x for some x between a and b. So what does this actually mean? This just means that if we have some function g of x, which is based on some other function, in this case f of t, maybe it's f over time, where time can be from some starting point a to some ending point x. That means that, again, our x can be somewhere between a and b, right? Just like we did with that integral from 0 to b, where b could be anywhere on the cosine from 0 to pi over 2. Then if we were to take the derivative of that g of x, then what we would do is we would get the derivative of our integral from a to x ft dt, which would just give us f of x. And our x would be somewhere between those values a and b. So we actually already kind of encountered this when we did that cosine problem. So now let's do an example using this graph here. So this graph here is based on our time t, let's say. So if we wanted to get g of 0, this would just be starting at 0 and going to 0. So we get 0 to 0, f of t dt. Well, remember we talked about this. If you ever have an integral from a to a, from some starting point to the same point, it's always going to be equal to 0. So this means that g at 0 would be equal to 0. What about g1? Well, g1 would be the integral from 0 to 1 f of t dt. Now, because we don't know what f of t is, what we're actually doing is we're looking at, as I go from 0 to 1, what is the area under the graph? Well, this is a triangle, so we have a base of 1, we have a height of 2, so this is going to be 1/2 base times height, so 1/2, 1 times 2. The 2's will cancel, and I'm going to be left with an area of 1. Now, if we want to do g2, this is going to be the integral from 0 to 2 f of t dt. So what this means is now we're looking at what happens as I go from 0 to 2. Now remember, I can always take, if I have the integral from a to b, I can, on some f of x dx, I can split this into the integral from a to c f of x dx plus the integral from c to b f of x dx. So what does that mean? Well, that means that what I could do is I could figure out what the area of this first part of the graph is, which I did, it's equal to 1. And then I could figure out what is the area of the second part of the graph, and then just add them together. So this one is a rectangle, so it has a width of 1, it has a length of 2, so width times length, or 2 times 1. So this is going to be 1 plus 1 times 2, or 1 plus 2, which is equal to 3. Now, if we want to get g3, this is going to be the integral from 0 to 3 ft dt, which now is going to be starting at 0 up to this point right here. So again, I'm going to take the area of the first part of my graph, the area of the second part of my graph, and now the area of the third part. So this is going to be, so this first two parts are 3 plus, again, we have a triangle with a base of 1 and a height of 2. So 1/2 base times height is going to be the same thing as this one, so plus 1. So this means that the area from 0 to 3 is equal to 4. Now, if I wanted to do g of 4, this would be the integral from 0 to 4 f of t dt. So now what we need to do is we need to consider what happens as we come out to here. So now we're going to have the area of the first, 0 to 1, 1 to 2, and 2 to 3. And then we're going to have the area from 3 to 4. But remember, because it's below the x-axis, we're going to subtract this. So this is, again, a triangle with a height of 1 in this case and a width of 1. So this is going to be 4 minus 1/2, 1 times 1. So 4 minus 1/2, which is going to give us either 3.5, or you could write it as 7/2. And then finally, if we want to know what is the area G5, this would be the integral from 0 to 5 f of t dt, which is now just going to add in this part, which has a base of 1, and it has a length and width of 1 and 1. So because it's square, 1 times 1 gives us an area of 1. So then we would have 7/2 minus 1, right? Because this 7/2 represents all of this and this part here. So we're going to take that 7/2, we're going to subtract the area of this part. So 7/2 minus 1, which is going to give us 5/2. And that would be the total distance traveled if this were distance based on this function g of x over time, right? We went, forward, went up to some point, and then we started to go backwards, moving back towards making our value smaller. Example 2 says that if g of x is equal to the integral from a to x ft dt, where a is equal to 1 and ft is equal to t squared, we want to find the formula of gx and calculate the derivative of gx. So just based on our fundamental theorem of calculus, we had that gx is equal to the integral from 1 to x ft dt, where we're going to plug in our ft, which we said was t squared. So this is going to be equal to the integral from 1 to x t squared dt. Okay, so now just like before, what we're going to do, we're going to take the antiderivatives. The antiderivative of t squared, we're going to take that square power, we're going to go up to cubed. So this is going to be equal to t cubed over 3. And we're going to evaluate this from 1 to x. So if we were to do that, we're going to get x cubed over 3 minus, plug in my 1, this will be 1 cubed over 3. Both of them have a like base, so I'm just going to combine this to x cubed minus 1 over 3. So now we know what our g of x is equal to. So if we wanted to find our g prime of x, if you remember, our fundamental theorem calculus said that it's just going to be the derivative of whatever we have. So this would be d dx of 1 over 3 x cubed minus 1 over 3. And this is going to be equal to, take the derivative of x cubed. So what you're going to do, bring down the 3. So this is going to become 3 over 3x, and you subtract 1 from the power. 3 is going to cancel. Derivative of a constant is equal to 0. So this is just going to be equal to x squared. And that's using our fundamental theorem of calculus with our g of x based on some function of t, which was equal to t squared, and starting at point 1 up to some point x. Meaning that if we take the derivative, the rate of change of our g of x, it would be based on x squared. For our next example, we want to find the derivative of a function g of x equals the integral from 0 to x square root of 1 plus t squared dt. So just like before, we are first going to have to figure out what is our antiderivative. But if this is our ft, right? So this is our ft. Then if we know that ft is equal to the square root of 1 plus t squared, if we were evaluating this from 0 to x, what's going to happen? Well, we're going to take the antiderivative of this with respect to x minus the antiderivative with respect to 0, which is just going to go to just going to cancel out basically. And then what's going to happen is when we take the derivative of this, it's going to go back to the original term in terms of x's, right? That's what happened in our last one. So from our last example, we do know that if I were to take the derivative of this g prime of x, what's going to happen is when I take the antiderivative of this square root of 1 plus t squared, take the square root of the whole thing. When I take the antiderivative of that, when I take the derivative of that with respect to x, I would just be left with the same thing, but now in terms of x. So this would be 1 plus x squared. Now, the reason we're not actually finding this right now is because if we were to try to find this, for example, if we were to set this up, the integral from 0 to x, 1 plus t squared to the 1/2 power dt, we would actually have to use something outside of the tools we've currently looked at, right? And this would involve actually using something called U-Substitution. For right now, though, just know that whenever you're doing your fundamental theorem calculus, if you have some function ft and you're going from 0 to x, when you take the derivative of that g of x, you will get back the same thing as the ft, but now in terms of x. Now, later on, when we talk about U-Substitution, we could then actually solve this using that method. What about if we wanted to take the derivative with respect to x of the integral from 1 to x to the 4th power secant t dt? So in this case, we are going to do a simple U-Substitution and just sort of kind of look at what we would do for something like this. So think about when we were doing our chain rule. What we would do is we would set our u equal to something. So in this case, it's going to be equal to this x to the 4th power. So we're going to have u equals x to the 4th. So then what this is going to become is this d dx integral from 1 to x to the 4th secant of t dt is going to become d dx from 1 to u secant of t dt. Now you might wonder, why did we do this? Well, now what we can do is we can actually take the derivative with respect to u. So this would be equal to d du integral from 1 to u secant t dt, and then we take du dx. So then by the chain rule, so if we were to take the derivative with respect to u of the integral from 1 to u secant t dt, the derivative of the integral is going to then replace this t. So this is going to become secant of u, and then we have du dx. Now we can actually substitute back in using our U-Substitutions. We're going to undo our U-Substitutions. So this u is equal to x to the 4th power. So this would be secant x to the 4th power times, now this du dx. This is saying the derivative, so du dx is like saying d dx of u. So we're taking the derivative with respect to x of this x to the 4th power. So based on power rule, this is going to become 4x, and then you subtract 1 from that, you get 4x cubed. So this is going to be times 4x cubed. So the last thing I want to talk about today is the mean value theorem of integrals. So if f is continuous on an interval a to b, then there exists a number c in that interval a to b such that the function at c is going to be equal to the average of our function, which is just going to be equal to 1 over b minus a integral from a to b f of x dx. Or we actually could rearrange this. So instead what we have is we have the integral from a to b f of x dx is equal to, we're going to take that b minus a, we're going to multiply it, and this is going to become b minus a times f of c. So what does this actually mean? Well, basically what this means is this, that if we have some a and b, and let's say we have some function doing something, right? So if we're in this interval, that means that somewhere in this interval from A to B, there exists some C which would be equal to the average of this function, right? So somewhere in this, at least one location, kind of like when we were doing for the derivative, right? We had from some starting point, ending point. If we had whatever the graph was doing, if I just created the average rate of change, somewhere in that graph, it would be equivalent to what it was from A to B. It's the same idea here, right? So if I'm going from B to A, right? So if I want to figure out, basically what we're looking at is this, is if I took the distance from B, which is going to be B minus A, so we're taking everything to the left of B, taking everything to the left of A, subtracting that off, and this will give us the distance from A to B. So that's what that B minus A is. It's saying if I were to take this area, which is the 1 over B over A, right, the area of this, wherever C is in here, if I were to take, this would just give us the average, right? So we're saying if I traveled from here to here, on average, right? So how do you take an average? You take the number of points divided by the distance traveled. So in this case, B minus A. So that means that if I were to take my function, f of C, whatever this function would be, f of C, if I were to multiply by the distance B minus A, this would be equivalent to the integral start from A to B, so the area under the curve from A to B, f of x dx, which just is to kind of say that if I took the average over the entire thing, it will be equal to the area under the curve. So what does that actually mean? Well, the way I kind of explain it when I'm teaching a class like statistics, for example, is that if I have the values, I don't know, let's say 2, 3, and 4, right? So if I were to take the average of these, this would be an average of 3, right? So if I took the, x bar equals 3. Well, what this is basically saying is that instead of having 2 and 3 and 4 and then taking the average, if I took the average of 3, 3, and 3, I would still get, 3 plus 3 plus C, 9 divided by 3 equals 3. It's the same idea, is that if I figure out what my f of C is, then somewhere in this, there is a C value that gives me a value where if I were to find the area of f of C times B minus A, so this rectangle right here, it would be equivalent to the area under the curve, right? Because you have some above, some below. So there's some C within this interval where if I take that height times the width of B minus A, if I were to take those two together, it would be equal to the value of the actual area under the graph from A to B. Hello everyone. In today's lesson, we're going to be talking about the substitution rule for integration, or specifically what we call U-Substitution. The substitution rule states that if U equals gx is a differentiable function whose range is an interval I, and f is continuous on I, then we have the integral of f of g of x times the derivative g prime of x dx. This will be equal to the integral of f u du. So what this means then is that if we know what our function is, we can figure out some g of x within that function, some function within the function, and the derivative of that, we could substitute u in and solve for that to get the same integral as this original integral of f of x. So this concept is actually easiest to see if we do some examples, kind of jump right in and see how this works. So suppose that we have the integral of x cubed cosine of x to the 4th power plus 2 dx. How would we solve this, right? This doesn't really work with the rules we've looked at previously. So what we're going to do is we're going to let u be equal to this x to the 4th plus 2. So much like when we were doing our chain rule for derivatives, we're going to let this be equal to u. So based on that, if we were to take the derivative of this u, which would give us du, this would be equal to, right, do the derivative, use your power rule, bring the 4 down, subtract 1 from the power, so we get 4x cubed. This is what the derivative of this is, But we have to take into account this was originally in terms of x, so this would be 4x cubed dx, right? Because we have to do our chain rule, right? Just like when we did d dx of y, we would do y prime, or dy dx. Same thing here, we have dx. And then if we were to look at this dx term here, we have this here. We have x cubed dx within our integral. So x cubed dx. So if we look at this now, we have x cubed dx. And what we want to do is we want to get this into terms of this du. Because whenever we do our U-substitution, we have to now take the integral with respect to u. So how does this relate? Well, we have that du is 4x cubed. So what would make this equivalent is if it was equal to 1 over 4x cubed dx, meaning that this would be equal to 1 over 4 du. So this means now that we can substitute this x cubed dx with 1/4 du. So now that we have that, we can go back to our original integration. So we're going to have our integral of x cubed cosine of x to the 4th plus 2 dx. This is going to be equal to the integral of cosine. Remember, now it's going to be the cosine of u. So we have the cosine of u. And then we just said that our dx, which is going to replace this x cubed dx, is going to become 1/4 du. Now, using our integration rules, we know that this constant can be pulled out. So this is going to now become 1/4 integral of cosine of u du. So now solving this using integration, right, we find the antiderivative. What's the antiderivative of cosine? It's going to be sine. So this is going to become 1/4 sine of u plus our c, because we took the antiderivative and this is an indefinite integral. And the last step, now we're just going to take that u and we're going to substitute it back in place of the u that we put in to substitute for it. So this is going to become 1 over 4 sine of x to the 4th power plus 2 plus c. For our second example, we want to evaluate the integral of the square root of 2x plus 1 dx. So just like before, this isn't one that we can solve directly, because even if we change this to 2x plus 1 to the 1/2 power, we still don't really have a way we can directly solve this right now. So what we're going to do is we're going to substitute this 2x plus 1, and we're going to write that as our u. So we're going to have this is going to be our u term. So we'll have u equals 2x plus 1. And now based on that, if we were to look at our du, right, we take the derivative of this, we're going to get that this is going to be equal to 2 dx, right? Now, what we need to do is we need to figure out what would make this dx go away based on this. So we're just going to divide both sides by 2. And we're going to have that dx is equal to 1/2 du. So now we can just do our substitution. So this integral, the square root of 2x plus 1 dx, is now going to be the integral of the square root of u 1/2 du. And then just like before, what can we do? Well, this 1/2 is a constant, so this can be pulled outside the integral. And I'm going to rewrite this u as u, the square root of u to the u to the 1/2 power. So this is going to be 1/2 the integral of u to the 1/2 power du. And now, just like before, we can find the antiderivative of this u to the 1/2 power by doing the inverse of the power rule. So this is going to leave us with 1/2 times. So we have u to the 1/2. What do? We bring the power up by 1, so this becomes 3/2, and then we bring that 3/2 to the denominator, which becomes flipped, so it becomes 2/3. So this will be 2/3 u to the 3/2 power. And then, of course, we have to add our plus c because this is an indefinite integral. So plus c. This 2 here is going to cancel with this 2 here. and this will just end up being 1/3 u to the 3/2 power plus c. Now we can substitute our u back into this, so we're going to be left with 1/3 times 2x plus 1 to the 3/2 power plus c. And then if we want to just get it into the same form we had at the beginning, we can just change this back in terms of square roots. This is going to be 1/3 square root of 2x plus 1 cubed plus c. For our next example, we want to find the integral of x divided by the square root of 1 minus 4x squared dx. So just like before, we have to figure out what we can do U-substitution for. Now, I will state right now that sometimes finding something you can do U-substitution for is not always straightforward, right? When we're in this section of the book, the problems are specifically made so that something substitutes in nicely to make this very easy to do. But there will be later methods that you're going to learn, for example, like doing calculus 2, stuff like that, where what do you do when even this fails? But for now, let's focus on the fact that we're going to use 1 minus 4x squared as our u. So we have u equals 1 minus 4x squared. So next we need to figure out what is our du. So we take the derivative of this, derivative of constant, equal to 0. We have minus 4x squared. So we take the derivative of x squared, we bring down the 2. So this is going to be minus 8x. Subtract 1 from the power, we're going to get minus 8x. And then we need to also include our dx. So now what we need to do is we need to consider the fact, though, that when we do this substitution, we're going to have the square root of u. We're still left with an x and dx. So we need to figure out if we have x dx, how is this related to our u, which we said, or rather our du, which is du is equal to minus 8x dx. So right here, if you look, we have x dx. So what we need to do is we just would divide both sides by -8. And this would give us that our x dx is equal to minus 1/8 du. So now we can actually plug all this back into our original integration. So we had our original integration, which was x over the square root of 1 minus 4x squared dx. And this is going to be equal to, I'm just going to pull that constant out like we end up doing in the second step anyway. So this is going to end up being minus 1/8 integral of 1 over, we have the square root of, this became u, so square root of u du. Now, if we want to actually figure out what this is, we're first going to rearrange this 1 over square root of u in terms of a power. So this is going to be equal to minus 1/8, the integral. So square root of u is u to the 1/2. But putting in the denominator, this becomes a negative power if we want to put it back in the numerator. So this is going to be u to the negative 1/2 power du. And now we can solve this using our antiderivative. So what is the antiderivative of u to the negative 1/2? Well, we're going to add 1 to this power. So this is going to be minus 1/8. So this negative 1/2 becomes plus 1, so it becomes u to the 1/2. And then we divide by 1/2, which is the same thing as multiplying by 2. So we have negative 1/8 times 2 times u to the 1/2 power. So then rewriting this in terms, plus rc. So then rewriting this, we're going to have that this is equal to, this 2 is going to cancel with part of this 8, leaving us 4. So we're going to have minus 1/4 square root of u plus c. And now we're going to substitute our u back into this, and this is going to give us minus 1/4 square root of 1 minus 4x squared plus c. For our next example, we're going to take the integral of e to the 5x dx, and we're going to evaluate this. So generally when you're doing U-substitution, you want to replace the thing that's causing difficulty with your u. Well, finding the antiderivative of e is easy. It's just e. So it's going to be this 5x that's going to be causing us any issues. So what we're going to do is we're going to set our u equal to 5x. And then, of course, if we solve for the derivative of u, we're going to take the derivative of 5x, just going to leave us with 5. So we're going to have 5 dx. So looking at what we have here, we have dx, but we don't have anything else. So we really just need to isolate dx by itself. So what I'm going to do is I'm just going to divide both sides of this by 5. And this is going to mean that we have 1/5 du equals dx. And that's going to be what we substitute in to our dx here. So now our integral e to the 5x dx is going to become the integral of e to the u. We have our 1/5, so times 1/5 du. And just like before, this 1/5 can be pulled out, giving us 1/5 integral e to the u du. So now we just got to figure out what our antiderivative of e to the u is. Well, our antiderivative of e to the u is just going to be e to the u. So this is going to be 1/5 e to the u plus c. And then the last thing we do, we plug our u back in. We said that our u originally was 5x. So this is going to be equal to 1/5 e to the 5x plus c. For example 5, we want to find the integral of tangent of x dx. Okay, so how do we do this? Well, this one we're actually going to be using the fact that if we have the tangent of x, this is equal to the sine of x over cosine of x. So what we're going to do is we're going to let u be equal to cosine of x. And you might wonder, why did I choose cosine? Well, it's because now when I take the derivative of this cosine, what does this become? Well, the derivative of cosine is going to be negative sine of x. So we have du equals negative sine x dx. So now let's actually look at this tangent over here, right? So we have cosine, we just said is going to be equal to u. So what are we left with in our integral? Well, we've got sine of x dx. So right now we have negative sine of x dx is equal to du. So all I have to do is I just have to bring the negative to the other side, and I will have that negative du equals sine of x dx. So this means that now this is going to become, so this integral tangent of x dx can be rewritten as the integral of, actually let's first write it this way, sine of x over cosine of x dx, which is going to be equal to negative, I'm going to pull that negative out front, integral of 1 over u du. And now what we need to do is we just need to figure out what the antiderivative of 1 over u is. Now, if you remember from our antiderivative rules or our indefinite integral rules, this is just going to be equal to the natural log of the absolute value of this u. So this is going to be equal to a negative, right? So we have our negative here, natural log of the absolute value of u plus c. And then what we're going to do is we're going to substitute our u back into this, which remember is cosine of x. So this is going to give us a final answer of negative natural log of the absolute value of cosine of x plus c. So this actually concludes all of our material from Introductory Calculus 1. If you're interested in learning more, I am going to have more videos I'll be posting on the supplementary calculus lessons, and eventually I will come back and do Calculus 2, Calculus 3, things like that. But I actually have some plans first to move back into statistics for a while, doing mathematical statistics, probably probability, statistical learning, things like that. But overall, we've now covered all the material from Calculus 1, and I really do hope that it's been helpful on your journey as you try to learn and understand and start to implement calculus. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.